Hello guys, I'm Ali Tabaza and today our video will cover the material required for the chemistry final. I'll be starting with chapter 1, question 1, and the first question says, when checking the reliability of certain measurements, define both precision and accuracy. I'll give you time to solve. Okay, so precision is about how consistent your values are with each other. Let's say you get 22 and 22.5, 23. Those values are pretty precise. Accuracy, on the other hand, is how close your values are to the actual results. So let's say you get 22.5 and the actual value is 23. That's pretty accurate. The second question asks us about the difference between random errors and systematic errors. So I'm going to give you time to answer. Okay, so random errors mean that they have an equal probability of being high or low. That means that the error happened maybe due to an incorrect reading or you took too much volume. Something that's not wrong with the system itself, and it can be higher or lower than the actual value. Systemic errors, on the other hand, happen from things that are wrong with the system. Let's say you take a scale and it determines the weight to be more than it actually is every single time. So the results you get are going to be higher every single time. The next question asks us to find the number of significant figures in the following values. So I'm going to give you a bit to solve. Okay, so for part A, we have 600 point. According to the rules, because there is a point, the zeros before count. So we have 1, 2, 3 significant figures. In the next one, because there is no decimal point, we just count the 4 as a significant figure. So we only have one significant figure. In part C, we have 7.0. Any zeros trailing after the decimal count. So we have 1, 2 significant figures. Now I'm also going to give you time to solve the last 3. So in part D, these zeros don't count because they come before the actual digits. However, these ones do. So we have 1, 2, 3, 4, 5 significant figures. In part E, we have 28 students, but because we know that it's exactly 28 students, the value is not measured, it's counted, so we have infinite significant figures. Now in part F, we don't have a decimal point, so the zeros don't count. So the significant figures we do have are the 6, the 4, and the 5. So we have 3 significant figures. So in number 2, we are given certain values and we are required to find other values. So in part I, they ask for the volume of the flask. I'll just give you a bit to solve. Okay, the mass of the water is equal to the mass of the flask filled up with water minus the mass of the empty flask. So that's 321.01 minus 121.01, and so we get 200.00. And the density is given to be 1.00 grams per centimeter cubed. So now we need to find the volume. Well, we know that density is equal to mass over volume. So we know that the volume is equal to the mass over the density, which is equal to 200.00 over 1.00. And so we get 200 point. We make sure that it's 3 significant figures as the density has 3 significant figures and we need to have the answer to the least number of significant figures. I'll give you guys a bit to solve part II. So part II says, find the mass of the carbon dioxide in the flask. So we have the mass of the flask filled up with carbon dioxide, which is 123.2 grams. And we have the mass of the empty flask, which is 121.01. So all we have to do to find the mass of the carbon dioxide is to subtract these, but be careful to take the answer to the least number of decimal places. So we get 2.2 grams. I'll give you guys a bit to solve part III. Part III asks us to find the number of moles. And we know that the formula to find the number of moles is the mass over the molar mass. So all we need to do is find the mass that we found in part II, which is 2.2, over the molar mass of carbon dioxide, which is 44, and we get 0.050 moles. Make sure to keep it to 2 significant figures. Part IV asks us to find the pressure of CO2. So I'll give you guys a bit to solve it. So in part IV, we have to find the pressure, and so we use the formula PV equals to nRT. We have the temperature given, we found the number of moles, R is a constant, and we found the volume. So all we need to do is substitute to find the pressure. So the pressure is equal to 0.050 times 0.082 times 300, all of this over the volume that we found, which was 0.2. So now we just need to calculate, and we end up getting 6.2 atmospheres. Make sure to keep it to 2 significant figures, as we need it to the least number of significant figures. Now we move on to the top questions. And top question 1, part A, asks us to find the mass of the dry air in the closed flask. They gave us the density and they gave us the volume, so we know that the mass is equal to the volume times the density. Make sure to keep your volume in liters, and so I'll give you a bit of time to solve it. So we get 1 times 1.19, which is equal to 1.19 grams. Part B asks us to find the mass of the completely empty closed flask. So we are given that the mass of the flask with the dry air is 157.70 grams. And we found out in part A that the mass of the air is 1.19 grams. And they want us to find the mass of the closed flask. I'll give you guys a bit to solve. Okay, so what we need to do is to subtract these two, and what we end up getting is 156.51 grams. Part C, they ask us to find the mass of the unknown gas in the closed flask. So we are given that the mass of the flask with the unknown gas is 158.08 grams, and we found out in part B that the mass of the empty flask is 156.51 0.51 grams. And now they want us to find the mass of the unknown gas. So I'll give you guys a bit to solve. So all we need to do here is to subtract these two masses from each other. And what we end up getting is 1.57 grams to 2 decimal places. Part D asks us to find the molar mass of the unknown gas. So to find the molar mass, we first need to find the number of moles in the gas. And to find the number of moles, we use the formula PV equals nRT. But for the given, we need to convert all our units into the correct SI units for the formula. We get that the absolute temperature is equal to 298 Kelvin. The volume is equal to 1 liter. And the pressure 850 over 760 atmospheres. So all we have to do is substitute into the equation PV equals nRT, and we know that the number of moles is equal to the mass over the molar mass, and so we can substitute that into the equation here. Now all we need to do is find the molar mass. We get the molar mass to be 34.3 grams per mole to 3 significant figures. Part E asks us to find the percentage error in the calculations, knowing that what we have is hydrogen chloride, whose molar mass is 36.5 grams per mole. Remember, what we got was 34.3. So I'm going to give you guys time to solve this. Okay, so all we need to do is put 36.5 minus 34.3 over 36.5 times 100%, and we get the percentage error to be 6.0%. Part F gives us two scenarios to explain why there is a percentage error in our solutions. So I'll give you a bit of time to think about it. Okay, the first scenario is that the HCl did not replace all the dry air, and therefore some dry air was left in the flask. We know that the molar mass of HCl is greater than dry air. So if we have some dry air and some HCl as opposed to all of it being HCl, then we will get a lower molar mass. So this does explain why this scenario is possible. The second scenario does not explain it, because if we look at the formula PV equals nRT, we can see that if the temperature decreases, the number of moles increase. It's that the calculated mass, and so the calculated molar mass, would also increase, which is why we can conclude that the second scenario is wrong. Part G asks us to demonstrate how we can prove that the volume is actually 1000 milliliters. So all we have to do is use a 1000 milliliter graduated cylinder to measure 1000 milliliters of the liquid, transfer the liquid into the flask, and check if the measured volume fills the flask to its rim. So in question 2, part A, it asks why the students heat the crucible only 3 times. I'll give you a second to think of your answer. Okay, we can see that after it was heated for the second time, the mass was 48.280 grams, and after it was heated for the third time, the mass was 48.281 grams. We can conclude that there was barely any change in the mass, which means all the water has evaporated. Part B asks us to deduce the formula of the hydrated copper sulfate. So what we need to do first is to find the mass of the water that evaporated. I'll give you guys a second to answer. So what we need to do here is to subtract the mass of the crucible with the sample, which was 48.659. You subtract that with the mass of the crucible after the third heating, which was 48.281. And the mass we get is 0.378 grams of water evaporated. Now we need to find the number of the moles of the water evaporated. So we just divide the mass by the molar mass. N is equal to M over capital M, which is equal to 0.378 over the molar mass, which is 18, and we get 0.0210 moles to three significant figures. Now we have to find the mass of the copper. So we take the mass of the crucible plus the sample, which was 48.659, and we subtract that with the mass of the crucible, which was 47.599, and we get 0.682 grams to three significant figures. And now we have to find the number of moles of the copper 2 sulfate. So N is equal to M over M, which is equal to 0.682 over 159.61, which is the molar mass of the copper 2 sulfate. And we get 4.27 times 10 to the minus 3 moles, and we keep it to three significant figures. Now to find the number of moles of the water as compared to the copper 2 sulfate, we have to find the ratio of the moles. So you write that N is equal to the number of moles of water over the number of moles of copper 2 sulfate. And what we get is 4.91, which is approximately 5. So we know that there is 5 moles of water for every mole of copper 2 sulfate. So we can conclude that the formula is CuSO4.5H2O. Part C says that in some groups, heating the solid led to some of the solid splattered out. How will this affect the calculated mass of the evaporated water? I'll give you guys a second to think about the answer. So if some of the solution splatters out, we will consider it all to be water, and as a result, the calculated mass of the evaporated water will be greater than the actual mass of the evaporated water. Now they perform a second experiment. In part D, they ask us to list the steps needed to find the mass of BaSO4 formed. So I'll give you guys a minute to think about this. To find the mass of BaSO4 formed, we need to perform filtration. So what we need to do first is to filter the precipitate. Then we wash the residue with water, and we leave it to dry completely. After that, we can calculate the mass of the residue by difference. In part E, they say that the mass of BaSO4 formed was 5.50 grams. Now they want us to find the percent of CuSO4 by mass in the original mixture. I'll give you guys a minute to solve. So what we do here is we say that the number of moles of CuSO4 is equal to the number of moles of BaSO4 which is equal to 5.50 over the molar mass, which is equal to 233. So we find out that the number of the moles is 0.0236 moles to 3 significant figures. Then to find the mass of the copper 2 sulfate, we just multiply the number of moles with the molar mass. So 0.0236 times 159.6, which is equal to 3.77 grams. Now to find the percentage, we just put the mass we found, which was 3.77 grams, over the original mass that was given to us, which was 5.42 grams, times 100%, and we see that the percent difference is 69.5% to 3 significant figures. Now we can move on to chapter 2. And the basic question in chapter 2 lists the following elements: Ne, Li, Al, Cl, and Ca, and asks us to find out several things. I'll give you a bit to solve part A, B, and C, and then I'll solve it with you. Part A asks us to find which of the above elements is most commonly found as a negatively charged ion. Well, we know that Ne is inert, so we can rule that one out immediately. Then we know that Li, Al, and Ca all form positively charged ions. That leaves us with Cl, which we know forms negatively charged ions, which means that Cl is the answer. Part B asks us which of the following elements has the same electron structure as Mg2+. Now we know that Cl forms negatively charged ions, so we can remove it. Ne is inert, so we can remove it. That leaves us with Li, Al, and Ca. We know that Li is in group 1, so it forms +1, and Al is in group 3, so it forms +3. That leaves us with Ca, which forms 2+, which is the same electron structure as Mg. Therefore, we know that Ca2+ has the same electron structure as Mg. Part C asks us which of the above elements forms a diatomic gas in the uncombined state. We took that elements in group 7 form diatomic molecules, so we know that Cl, being in group 7, will form a diatomic molecule, and we know that it's a gas. Now we move on to chapter 3, basic question 1. And the question says a sample of chloride consists of 1 times 10 to the 6 atoms of 3517Cl and 1 times 10 to the 5 atoms of 3717Cl. And they want us to find the average mass of the atom of chlorine. So I'm going to give you guys a minute to solve this question. Okay, so what we need to do here is multiply the total number of atoms by the molecular masses of each one. 1 times 10 to the power of 6 times 35 plus 1 times 10 to the power of 5 times 37 over 1 times 10 to the 6 plus 1 times 10 to the 5. And so we get 35.18 grams per mole. Basic question 2 asks us about the same concept but in a different way, where we have two isotopes 6Li and 7Li, and the average atomic mass is 6.9. So they want us to find the percent abundance of each isotope. I'll give you guys a minute to solve. All we need to do here is to choose one to be x and the other to be 100 minus x, as we're finding a percentage. Then we can write it to be 6x plus 100 minus x into 7 over 100 is equal to 6.9, and we solve for x. We get x to be 10% for the one with 6 Li and 90% for the one with 7 Li. In grid question 1, we are given that a hydrocarbon produces carbon dioxide. They give us the number of grams of carbon dioxide, and they want us to find the percent by mass of the carbon in the hydrocarbon sample. So I'll give you guys a minute to solve. Okay, so the first thing we need to do is find the number of moles of carbon dioxide, which is equal to M over capital M, which is equal to 5.5 over 44, which is equal to 0.125 moles. For every mole of carbon in the hydrocarbon, we produce 1 mole of carbon dioxide. So we know that the number of moles of carbon is equal to the number of moles of carbon dioxide. So the number of moles of carbon is equal to 0.125 moles. Now we have to find the mass of the carbon, and the mass is equal to the number of moles times the molar mass, which is equal to 0.125 times 12, which is equal to 1.5 grams. To find the percent by mass, we just need to divide the mass of the carbon we got over the mass of the hydrocarbon sample and multiply it by 100%. We get 1.5 over 3, which is equal to 50%. In basic question 1, they gave us the percent by mass of the carbon, the hydrogen, and the oxygen, and they want us to find the empirical formula of X. So I'll give you guys a bit to solve. So what we have to do first is divide each element's percentage by its molecular mass. Then we have to divide the values we get by the smallest number we get. So we get these values, and thus we can determine the empirical formula. If one of the numbers turned out to be a decimal, let's say we got 2.5 for C, we're going to have to multiply all the values by 2, and we get 5, 12, and 2. But we didn't have a case like this in this question, so we don't need to worry about that. Question 2 says that 0.78 grams of potassium react with enough oxygen to form 1.1 grams of a product A. They want us to find the formula of A. I'll give you guys a bit to solve. Okay, so what we need to do first is find the mass of oxygen, and we can do that by subtracting 1.1 by 0.78. And so we get 0.32 grams of oxygen reacting. Now that we have the mass, we have to divide it by the molar mass to find the number of moles reacting for the K and the O. So if we do that, we get 0.02 moles reacting for K, 0.02 moles reacting for oxygen. We can conclude that equal number of moles of K and O react, meaning that our final formula would be KO. So in basic question number 3, we have a hydrocarbon burnt in excess oxygen to give carbon dioxide and hydrogen and water. The hydrocarbon is 0.56 grams, 1.76 grams of carbon dioxide was produced, and 0.72 grams of water was produced. They want us to find the empirical formula of X, which is the hydrocarbon. So I'll give you some time to solve. So what we need to do is find the number of moles of carbon dioxide formed and the number of moles of water formed. So let's start with carbon dioxide. We have 1.76 over the molar mass, which is 44, and that is equal to 0.04 moles of carbon dioxide forming. With water, we have 0.72 over 18, which is the molar mass, and that is equal to 0.04. But because that's H2O, and we want the number of moles of hydrogen reacting, we multiply that by 2 to get 0.08 moles. Knowing that the number of moles of hydrogen is double the number of moles of carbon, we can determine that the empirical formula would be CH2. Basic question number 4 says that a sample of hydrated copper 2 sulfate with a mass of 25 grams was heated until all the water was removed. The sample was then weighed and found to have a mass of 16 grams. And they want us to find the formula of the hydrate. So I'll give you guys a bit to solve. Okay, so we know that the mass of the hydrated CuSO4 is 25 grams. And the mass of the anhydrous CuSO4 is 16 grams. If we subtract the two, we get 9 grams, and that's the mass of the water in the hydrated CuSO4. Knowing that, we can find the number of moles in the water and the number of moles in the copper 2 sulfate. So we just divide the mass of the water by its molar mass, and we get 0.5 moles. And we divide the mass of the CuSO4 over its molar mass, and we get 0.1. Now we know that there's 5 times as many moles of water as there is CuSO4. We can then write the formula to be CuSO4 dot 5H2O, meaning that there's 5 times as many moles of water as there are CuSO4. Basic question number 5 says that a sample containing 0.198 grams of a hydrocarbon was burnt in excess oxygen to give 0.324 grams of water. And they want us to find the empirical formula of the hydrocarbon. I'll give you guys a bit to solve. Okay, so the first thing we need to do is find the number of moles of carbon reacting and the number of moles of hydrogen reacting. So first, we can find the number of moles of hydrogen reacting by dividing the mass of the water produced by the molar mass. And so we get 0.018 moles, but that's the number of moles of water forming. They want us to find the number of moles of hydrogen. So we multiply it by 2 because it's H2O. And so we get 0.036 moles of hydrogen. We can use that to determine the number of moles of carbon reacting. So because hydrogen's molar mass is 1, we know that the mass of hydrogen reacting was also 0.036 grams. We can subtract 0.198 by 0.036, so we get 0.162 grams of carbon reacting. Now we divide that, which is the mass, over the molar mass to find the number of moles of carbon reacting. And so we get 0.0135 moles of carbon reacting. Now we divide the number of moles of hydrogen by the number of moles of carbon to find the ratio. And so we find the ratio to be 8 to 3, meaning that the formula would be C3H8. Okay, so in basic question number 1 for section 3.10, we are given the following reaction and are asked to calculate the pressure in the container after the reaction finishes. I'll give you guys a bit to solve. Okay, so we are given the number of moles of the CH4 reacting and the number of moles of the O2 reacting. We can deduce from the reaction ratios that 0.5 moles of carbon dioxide form and 1.0 moles of water form. You can see that because 1 needs 0.5, 2 needs 1, and so we can say that 1 will need 0.5 and 2 will need 1.0 moles. Knowing this, we can calculate the total number of moles reacting in the beginning, which was 1.5 moles, and the number of moles reacting at the end, which was also 1.5 moles. Now, because the number of moles didn't change, the volume didn't change either, the temperature didn't change, and R is a constant, we can conclude that P will remain constant. We are given that P initial is 1.0 atmospheres, so we know that P final will also be 1.0 atmospheres. Basic question number 1 says that 9 grams of H2 react with 2 moles of N2 to give 20.4 grams of NH3, and they want us to find the percentage yield. So we need to find how many grams of NH3 should form under this reaction. And to do so, we need to know whether H2 or N2 is the limiting reagent. So we have the reaction N2 plus 3H2 to give 2NH3. So the coefficient of H2 is 3 and the coefficient of N2 is 1. So we need to find the number of moles reacting in each one, and then we need to divide it by the coefficient to find the limiting reagent. So we have 2 moles of N2 reacting and 9 over 2, which is equal to 4.5 moles of H2 reacting. I just divided the mass by the molar mass of H2. Then we need to divide it by the coefficient, so we get 1.5 for H2 and 2 for N2. Because H2 is less than N2, we know that H2 will be the limiting reagent. Now we know that 4.5 moles of H2 react. By the ratio, we can see that 3 moles of NH3 form. Now we just have to calculate the mass that should form. N is equal to M over M. If we substitute it, we get 3, is equal to m over 17, and so the mass should be 51 grams. Now to calculate the percentage yield, we should put the actual mass that was formed over the mass that we got and multiply that by 100%. And so we find the percentage yield to be 40%. In top question 1, we are given the following reaction, and we are given that 5 moles of N2 react with 9 moles of H2, and they want us to find the diagram of the mixture after the reaction. I'll give you guys a bit to think about it. So the first thing we need to do is find the limiting reagent. We have the number of moles, so all we need to do is divide it by the coefficient, and we get 5 and 3. We then know that H2 is the limiting reagent and N2 is in excess. Because 9 moles of H2 react, by the ratio, we know that 3 moles of N2 will react with the H2 to form 6 moles of NH3. Because we inserted 5 moles of N2 into the container and 3 moles reacted, we know that we will have 2 moles remaining. For H2, because it's the limiting reagent, it will completely get consumed. And for NH3, we will have 6 moles forming. So what we need to find in the container is 2 moles of N2 and 6 moles of NH3. The molecule for N2 will look like this because it's 2 atoms together. The molecules of NH3 will look like this because it's one big atom, which is the N, with 3 small atoms, which are the H. So we need to find 6 of these into the container and 2 of these in the container. If we look, we will find out that the second one is actually the correct one.
Okay guys, let's move on to chapter 4 now, types of chemical reactions and solution stoichiometry. We'll start with the first question in the course event sheet. I'll give you guys a few seconds and then we'll check together. Okay, let's start with part A. What mass of H2SO4 is needed to prepare 500 cubic centimeters and 2 molar solution? So they want the mass. We have the volume and the concentration. So first step immediately is number of moles is equal to CV. So we make it into liters, so 0.5 into 2. So that's 1 mole. Right? And now if you want the mass from this, that's equal to the number of moles times the molar mass. So it's 1 times what's the molar mass? It is 98. So it is 98 grams. 2 significant figures because of the 2.0 molars. Part B. 25 cubic centimeters of a 0.4 molar salt solution were evaporated to dryness. 1.11 grams of the salt was left over as a residue. Calculate the molar mass of the salt. So in this case, we want the molar mass. Let's just see all the formulas we can get from the mass, right? Because we have the mass which is given. Well, we know that the mass is equal to the number of moles times the molar mass, which is then equal to the concentration times the volume times the molar mass. From this, we get that the molar mass, isn't it equal to the mass over the concentration times the volume? So it's equal to 1.11 over 0.4 times 25 over 1000. And doesn't that equal 111 grams per mole, because that's the unit of molar mass. And from this we've done parts A and B. You guys can quickly copy this and then I'll get rid of this to make space for C. Let's move on to part C now. What volume of 2 molar HCl solution contains 3.65 grams of solute? Okay. What is the volume? we have the mass and we have the concentration. Let's use the same formula as before. M is equal to number of moles times molar mass, which is also equal to CV molar mass. So our volume isn't it equal to mass over concentration times molar mass, which is, let me just continue here, 3.65 over 2 times, what's the molar mass of HCl? 36.5. and that gives us 0.05 or 50 dot centimeter cubed. The dot is for the two significant figures. Alright, let's move on to number 2. 2.12 grams of Na2CO3 sample was dissolved in 500 cubic centimeters of solution. Calculate the concentrations of all ions present in the solution. Alright, how do we get, first let's talk about what's the concentration of Na2CO3, right? What is the reaction first? It's Na2CO3, which gives 2Na plus and CO3 2 minus, right? So the ratio is 1 to 2 to 1. So if I can just get the concentration of Na2CO3, I am done with Na and CO3. The concentration of Na2CO3 is, first let's get the number of moles, which is 2.12 over the molar mass. The molar mass being 106. So this is the number of moles. And to get the volume, we divide the whole thing by the, to get the concentration, we divide the whole thing by the volume, which is 0.5. And the answer we get is 0.04. I'm not going to bother with significant figures as of yet. So we have 0.04 molar. So the ratio is 1 to 2, so it's 0.08 molar and 0.04 molar. And now let's list the concentrations of the ions. So Na plus is 0.08. Let's see how many significant figures. 3 significant figures. So 0 molar, and the CO3 2 minus is 0.0400 molar, and that's your answer for number 2. Quickly copy it so that we can check number 3. Let's move on to number 3. A sample containing 25 cubic centimeters of 0.2 molar NaCl solution was mixed with 75 cubic centimeters of a 0.02 molar CaCl2 solution. Calculate the concentrations of the Cl minus ions in the solution. No reaction takes place when the solutions are mixed. I'll give you guys a few seconds and then we can check together. Okay, let's check together. The very first thing we should do is, I'm just gonna do it up first, is write the dissociation reactions. So NaCl gives us Na plus and Cl minus. So the ratio is 1 to 1 to 1. So if you can just quickly find the number of moles of NaCl, that's C times V, right? This is C, this is V. So that's 0.2 times 0.025, which gives us 5.0 times 10 to the minus 3 mole. So now this is 5 times 10 to the minus 3. This is the very same thing because the ratio is 1 to 1, and this is the exact same thing. So for the first reaction, we're done. Let's go for the second one, CaCl2. CaCl2 is Ca2 plus and 2Cl minus. The ratio is 1 to 1 to 2. Now let's find the number of moles of CaCl2 now, volume, concentration. So again it is 0.02 times 0.075, which gives us 1.5 times 10 to the minus 3. So again, if we write this 1.5 times 10 to the minus 3, we got the same thing here, but for Cl minus it's 3 times 10 to the minus 3. Now that we have that, I'm just going to erase this so we can continue with our question. Let's continue here. So our total number of moles of Cl minus was 5 times 10 to the minus 3 from before, from the NaCl, and 3 times 10 to the minus 3 from the CaCl2 solution, giving us 8 times 10 to the minus 3 moles total. And now what they're asking us, the concentrations. So C is equal to N over V, 8 times 10 to the minus 3 over. Now what's our volume? We have 25 cubic centimeters and 75, giving us 100. So that is 0.1, giving us 8.0 times 10 to the minus 2 molar. And this is the concentration of chlorine ions. Part 4 now, number 4. A lab technician is asked to prepare a 500 cubic centimeters 0.5 molar H2SO4 solution from a 6 molar H2SO4 stock. Explain how the technician can do this. I'll give you guys a few seconds and then we'll check together. Okay, let's check together. One thing we should know is the H2SO4 moles from here that we need to convert here, the moles are equal. So we can do N before equals N after, C1V1 equals C2V2. So let's do that. C1V1, this is, we're considering C1. So it's 6 times the volume is equal to 0.5 times 0.5, giving us the volume equals 0.0417 decimeter cubed. But this is not the final answer. Like, the question is asking us something else. They don't just want the volume. They're asking us explain how the technician can do this. So I'll read out the answer and then you guys can copy it down. So we use a burette to transfer 0.0417 cubic decimeters or 41.7 cubic centimeters of 6 molar acid, so this one, into a 500 cubic centimeter volumetric flask containing about 50 ml of water. Add enough water till the bottom of the meniscus is tangent to the mark on the neck, and then we shake to combine. If we remember, when we've been doing these lab in school, like, when we fill the volumetric flask, we have to wait, like, see it until the solution reaches the bottom of the meniscus is tangent to the mark of the neck. And that's how we do number 4. Alright guys, let's move on to the next part. Question 1 of section 4.7. 150 milliliters of 0.2 molar solution of lead 2 nitrate is added to 125 milliliters of 0.1 molar sodium chloride solution. Assume no change of volume in the solution. The chemical reaction that takes place is represented by the following equation. PbNO3 2 solid plus 2NaCl aqueous to give PbCl2 solid and 2NaNO3. There are 3 parts in the question. I'll give you guys a few minutes and then you can solve, a few seconds, and then we'll check together. Okay, let's start. A. List an appropriate observation that provides evidence of a chemical reaction between the 2 compounds. What this question is asking us is, how do we know the reaction has taken place? Well, we can't know if NaNO3 has been produced since it's aqueous. We can see there's a precipitate. And what's the color of PbCl2? It's white. So we can write white precipitate forms. And that's part A. So if we see a white precipitate forming, we know that the reaction has taken place. B says find the mass of the precipitate, and C says calculate the molar concentration of all ions left in solution. Now B and C, they can be done together. So this is not D, this is C. B and C, they can be done together, the calculations will be the same. So let's start. First, let's try to find NaCl, right? So NaCl gives Na plus and Cl minus, right? Yeah. Now we need to find the number of moles, so it's 0.125 and 0.1. We have to multiply them together and we get 12.5 times 10 to the minus 3 moles. The exact same here, Why? Because the ratio is 1 to 1 to 1. PbNO32 gives Pb2 plus and 2NO3 minus, right? And now this is again 0.2 times 0.15, which gives us 30 times 10 to the minus 3 moles. The same for Pb2, but for NO32 minus is 60 times 10 to the minus 3. Now immediately what we can do is find the concentrations of the two ions that don't become into the precipitates. We can find the Na and the NO3. So let's just start with our answer. So we have the Na plus is the number of moles over the volume. The number of moles is this, and the volume is actually 150 ml plus 125 ml, which is 275 ml. This is V total, right? And now if we do the math, we should get a number of approximately 0.0455 molar. Let's move on to the NO3 minus. It is 60 times 10 to the minus 3 moles, and if we divide this by 275 milliliters, we should get 0.218 molar. So far we've gotten the concentration of Na plus and NO3 minus at the end of the reaction. Now let's find the precipitation reaction. We have Pb2 plus 2Cl minus to give PbCl2. Alright, now let's just find the limiting reagents and the excess reagents, right? We have the number of moles of Pb2 plus, and we have the ones for Cl minus 12. Oh, it's a little slow here. Okay, we divide by the coefficient over 1 over 2. This is definitely the smaller one, so this is the limiting reagent and this is the excess reagent, right? Yeah. Now what does it mean to be the limiting reagent? Well, what that means is by the end of the reaction, Cl minus will be completely used up, so the molar concentration of all ions left in solution for Cl minus will be 0. Let me just erase this and we'll continue on. So we had that Pb2 plus 2Cl minus gave us PbCl2, and we had clearly determined this was the limiting and this was the excess reagent. So now if you want to find the number of moles of excess reagent left over to get the concentration of ions, well, we have to do is number of moles of ER, well, that's 30 times 10 to the minus 6 minus, times 10 to the minus 3 minus, now what do we subtract? We have to subtract 6.25. Now I'll tell you why. Minus 3. If we remember, the Cl minus was 12.5 times 10 to the minus 3 moles. Then why aren't we subtracting this? Well, for every 1 molar of Pb2 plus, 2 moles of Cl minus are reacting. So if it was a 1-to-1 reaction, then for 12.5 times 10 to the minus 3 moles of Cl minus, we would need 12.5 times 10 to the minus 3 moles of Pb2 plus. But since it's a 1-to-2 reaction, for 12.5 times 10 to the minus 3 moles of Pb2 plus, Cl minus, we only need half that for Pb2 plus, because every Pb2 plus ion is reacting with 2 Cl minus ions. And this should give us 23.8 times 10 to the minus 3 moles. Right? Now we still have to find the mass of the precipitate. Very simply, that is very simple stoichiometry here. Let's see. So 2 moles of Cl minus gives us 1 mole of PbCl2, or 278 grams of PbCl2, where X is the now new concentration, and 12.5 times 10 to the minus 3 is what we have currently. Solving for X, we get X equals 3.48 grams. Let me just make sure of that number, just a second. So 278 times 12.5 times 10 to the minus 3 divided by 2. And sorry, this is not the answer. This is 1.74 grams. So there's a mistake in the sheet. The sheet assumes it's a 1 mole 1 to 1 ratio. It's actually a 2 to 1 ratio. So it's a 1.74 gram. Alright, that's the answer. And now let's write the molar concentration of all ions left in solution. So we only have 3. The Cl minus is negligible because it is all used up. So we had the Na plus, the NO3 minus, and the Pb2 plus. Let's just remember what our figures were from before. This was 0.218 molar. This was 0.0455 molar. And this. We have this much moles of Pb2 plus left over. We divide it by the volume, which is again 275 milliliters. And we get an answer of around 0.0864 molar. And that's the answer for number 1. Alright guys, let's move on to section 4.8, the first basic question. What volume of 0.5 molar HCl is needed to neutralize exactly 20 centimeter cubed of a 0.02 molar CaOH2 solution? I'll give you guys a few seconds, you can solve and we'll check together. Alright, let's check together. The first thing to do is, we should write the equation of the reaction. So HCl plus CaOH2 to give CaCl2. So we gotta put a 2 near the HCl and 2H2O. Alright. So the ratio is 2 to 1. We have number of moles of acid and number of moles of base. If we cross multiply, we get that number of moles of acid is equal to twice the number of moles of base. And this will be our formula. Since number of moles is C times V, so we get the concentration, which is 0.5 V, or let's call this V acid, is equal to 2 times 0.02 into 0.02, right? And we got that Va is equal to, let's just make it into centimeter cubed to make it easy, 1.6 cubic centimeters. So if you had kept the volume in cubic centimeters and not converted it into liters, the answer would have automatically come in cubic centimeters. What I did was I just got the answer and multiplied by 1000. Let's move on to the next question, which is a grid question. A sample of 25 centimeter cubed of a certain NaOH solution was needed to neutralize exactly 20 cubic centimeters of 0.2 molar HCl solution. Calculate the concentration of the base. Okay. For this one, if you want, you can write the reaction, but like it's not really required since the ratio is 1 to 1. Let's just write it anyways. And ACl and H2O. The ratio is 1 to 1, so the number of moles of acid and A equals the number of moles of base. So we have, let's see, I'm just going to keep it in centimeter cube for this one, it doesn't matter much. 20 into 0.2 is equal to 25 concentration of base, and we got that the concentration of the base is equal to 0.16 molar. That's the answer for the next grid question. I'll give you guys a few seconds to copy and then we will move on. Alright, let's move on. Section 4.9, Oxidation and Reduction Reactions. The first basic question. Assign oxidation numbers for each element in the following chemicals. I'll give you guys a few seconds, solve all of them, and then we'll check together. Alright, let's check together. Let's work with the first one, H2O2. First, let's just do it normally, then I'll tell you about the rule. So, hydrogen is always plus 1. and we know that the sum has to equal 0 because there is no net charge. So let's see, 2 plus 2x equals 0, x is minus 1. The rule says that oxygen in any peroxide, so x2 O2, x being anything, O has to be minus 1. That's the rule. Next, OF2, F is always minus 1. So x minus 2 equals 0, x is plus 2. And this is the second rule, where if it's like OF2 for instance, the oxidation number of oxygen is plus 2. That's the second rule. Let's just write minus 1 here. Moving on. Na2O2. Does this look similar? It does. It's the exact same as X2O2, without a doubt, plus 1 minus 1. Let's just make the dividers. Alright. HOCl. Okay. H is always plus 1. The O, it's not in any of these rules, so there's no exception. It's going to be a minus 2 because, oxidation numbers are the number of the charge. Now let's see. 1 minus 2 plus x equals 0. X is very obviously plus 1. Let me just write that better. Plus 1. Right. CO3 to minus. In this case, the sum of all of them has to equal minus 2. We know that oxygen is minus 2. So we say x minus 6 equals minus 2. X is plus 4. See, for these ones, all I have to do is work slowly. You'll get them all correct for sure. Alright, let's move on. For this one, SO4. SO4 has to equal to minus. Why? Because you can see, right, the charge is like, it cross multiplies, like CrSO4. Like the charges cross multiply, that's how you get the numbers at the bottom, right? So for SO4 is 2 and for Cr is 3. So Cr automatically we get 3 plus. Right? Yeah. Now SO4. We know that oxygen is minus 2. So we get x minus 8 is equal to minus 2. X is plus 6. And that is indeed what x is. Okay, the last one, CuNH3 Cu is automatically plus 2. Reason being, the 2 cross multiplies. NH3 is NH3 minus, while H3 is plus 1. Now N. So it is x plus 3 equals 0 because there is no cross multiplication happening, right? NH3 is, nothing. And that is minus 3. Now let's move on. Number 2. Consider the following reaction. 5Fe2 plus aqueous plus MnO4 minus aqueous plus 8H plus aqueous to give 5Fe3 plus aqueous, Mn2 plus aqueous and 4 water. The mass percent of iron in a soluble iron 2 compound is to be calculated using a titration based on the balance equation above. I want you guys to solve part A and then we'll check together. Alright, let's check. They're saying identify the oxidizing and reducing agent. First, let's talk about what an oxidizing or reducing agent means, right? An oxidizing agent is an agent that oxidizes other things, right? It causes other substances to get oxidized. That means it itself is being reduced. Now, in reduction, what does reduction mean? It means your oxidation number goes down. And oxidation, that means the oxidation number goes up. And reducing agent is obviously it causes other things to be reduced or it itself is being oxidized. So let's look at this Fe2 plus for a minute. What's the oxidation number? Plus 2. This same Fe2 plus is becoming Fe3 plus. This new oxidation number is 3 plus or plus 3. So the reducing agent or Ra is Fe2 plus. We cannot say Fe3 plus is the reducing agent because it is not being oxidized. We have to say Fe2 plus is the reducing agent. Now let's look at the oxidizing agent. We have to look at either what is oxidizing others, which is kind of hard to know, or what is reducing others, or what is being reduced itself, sorry. Let's have a look at this MnO4 minus. Let's find the oxidation numbers. O4 is minus 2, so X minus 8 equals minus 1, Mn is plus 7, quite a high oxidation number. While the same Mn has become Mn2 plus, which makes it an oxidation number of plus 2. The oxidation number has decreased from plus 7 to plus 2, thus making the MnO4 minus the oxidizing agent. Now let's move on to part B. First, let's read this small given above. The mass of a sample of iron 2 compound is carefully measured before the sample is dissolved in distilled water. The resulting solution is acidified with H2SO4. The solution is then titrated with MnO4 minus. B says, describe the color change that occurs in the flask when the end point of the titration has been reached. Explain why the color changes at that point. I'll give you guys a few seconds and then we'll check together. Alright, let's check together. As we can see from the reaction above, we can see that Fe2 plus was there in the beginning. So what is the color of Fe2 plus? It's a greenish color. And as you can see, Mn2 plus is coming. What is the color of Mn2 plus? It's a pink color. So at the point of end, like the color changes at the end point from a greenish color or a pale greenish color to a pink color. Now, what is happening at the end point? We have both Fe3 plus and MnO4 minus, because all the Fe2 plus has become Fe3 plus. But the thing is, the MnO4 color dominates over the Fe3 plus. That's why we have pink, not any other color. Now let's look at part C, which is the last part. What effect will adding less aliquot have on the experimental determined value of the mass percent of iron in the compound? Justify your answer using mathematical reasoning. Let the variables G, M and V be defined as follows. We can see all the definitions. So I'll give you guys a few seconds to think of an answer and then we'll check together. Alright, let's check together. So if we add less aliquot, first let's see what aliquot is. Aliquot, I think, is the MnO4 minus. So when we add less aliquot, we are having less number of moles. But how can we talk about number of moles when they're asking us to talk about G, M and V? We can say that the volume is too small, is smaller. From the volume being smaller, and since N is equal to Cv, if V decreases, N decreases, the number of moles of MnO4 minus is smaller, or the number of moles needed is smaller. And then that can tell us that the mass calculated of Fe2 plus gets smaller. What does this mean? Well, what this means is, since this is a titration, we usually use C1 V1 equals C2 V2, since the ratio is the same, right? Since, let's call this the number of moles of MnO4, and let's call this the number of moles of Fe2 plus. If this decreases, won't this decrease? It will decrease for sure, right? That's why the mass calculated, if the number of moles decreases, mass decreases, is too small. That is why the percentage mass of iron Fe calculated is smaller or goes down, and that's how you explain. Alright guys, let's do the last two questions of chapter 4. Section 4.10, balancing oxidation reduction equations. One says balance the following redox reaction that takes place in acidic medium, very important. Cr2O72 minus plus Fe2 plus H plus to give Cr3 plus Fe3 plus in water. I'll give you guys a few seconds and then we'll solve. Alright, let's check them together. I'll work on the bottom half of the page. So step 1 is to basically write the half equations, half reactions. Cr2O7 2 minus gives us Cr3 plus, and Fe2 plus gives us Fe3 plus. Second step is basically just balance them to Cr3 plus, that's it. Next we have to balance the oxygens. There are 7 oxygens here, so we have to add 7 H2O, and there are no oxygens in the bottom reaction, we don't care about that. Next we balance the hydrogens. So basically what you have to do is, let me just put this as an arrow, you have to add 14 H pluses. Why 14? Because 7 times 2 is 14. Alright, nothing has been done to the bottom reaction. The second last step is to balance the charges by adding electrons. For the second one is easy, we just add 1 E minus. For the first one, okay, 14 minus 2 is 12, and we have 6 here, so we have to add 8 electrons. Oh wait, sorry. It's 14 minus 2 is 12, but we have 2 of the 6, so it's 6 electrons. Let me just write that, making sure 14, 12, 6, perfect. Now the last step to do is to balance the equations by making sure the number of electrons are the same, so we can cancel, so we multiply by 6, and let's make this a 6. Now all you have to do is add to get the final. The electrons cancel out, we get Cr2O7 2 minus plus 6 Fe2 plus, giving us plus 14S plus, sorry about that, there's no eraser, okay, 14S plus, you know what, let me just rewrite it, it's a bit messy. Alright, 14H plus 6 Fe2 plus Cr2O7 2 minus gives us 2 Cr3 plus 6 Fe3 plus 7 water, and that's our balanced redox reaction in an acidic medium. Right, now we go to the last question. What volume in ml of a 0.1 molar potassium permanganate solution KMnO4 is needed to completely oxidize 10 milliliters of 0.3 molar copper nitrate solution CuNO3? They've given us the reaction, we have to just find the volume. So I'll give you guys a few seconds and we'll check. Alright, let's check together. So what we can see here is that the ratio is 5 to 1. So 5 over n of Cu plus and n of, let's just call it MnO4 minus, equals, if we cross multiply, we're getting n of Cu plus is equal to 5 number of moles of MnO4 minus. So the concentration is 0.3 times 10, I'm going to keep it in milliliters because they want in milliliters, I don't want to convert in the end, is equal to 5 times, they have 0.1 and we have to find the V. Very simple, V is equal to 3 over 0.5, which gives us, let's just make sure we have the correct answer, wait, 3 divided by 0.5, 6. It has to be to two significant figures, so 6.0 milliliters. That's our final answer. And with this, we have completed chapter 4.
So for number 1, you have 25 centimeter cubed and 0.20 moles of NaCl. You also have 75 centimeter cubed of 0.020 moles of CaCl. And you need, actually CaCl2, and you need to calculate the concentration of Cl minus. So because no reaction takes place, you can just use the equation C equals N over V. V is already given, you need to calculate N to get the concentration. The equation for NaCl is Na plus with Cl minus gives you NaCl, and the ratio is 1 to 1 to 1. So you can just you use the given and calculate the number of moles for NaCl, and you'll get the number of moles for Cl minus in NaCl. The equation is N equals C times V. C is 25 from centimeter cube to meter cube times 10 to the power of minus 3 times V, which is 0.2, and you will get 5 times 10 to the power of minus 3 moles. Now the equation for Ca is Ca with 2Cl gives you CaCl2. The ratio is 1 to 2 to 1. So you can calculate the number of moles of CaCl2 multiplied by 2, and then you'll get the number of moles for Cl. So the equation is N equals 2 times C times V, which is 2 times 75 centimeter cube to meter cube times 10 to the power of minus 3 times V, which is 0.020, and you'll get 3 times 10 to the power of minus 3. So the number of Cl minus in total is 3 times 10 to the power of minus 3 plus 5 times 10 to the power of minus 3, which is 8 times 10 to the power of minus 3. And so we said at the beginning that the equation is C equals N over V. V is already given, 2575 times 10 to the power of minus 3, because from centimeter cube to meter cubed, and the total number of moles for the Cl minus is 8 times 10 to the power of minus 3. Using that, you'll get 8 times 10 to the minus 2 molar.
A solution is formed by mixing 1.0 liters and 1.0 molar of KCl to 1.0 liter and 1.0 molar of PbNO32. Part A says, calculate the mass of PbCl2 that will form assuming complete precipitation. Okay, so first we write the given, which is concentration of KCl is 1.0 molar, with the volume being equal to 1 liter. And now for PbNO32. Our required to find is the mass of PbCl2. Okay, so first we need to find the number of moles of everything. Okay, first we start off with the number of moles of KCl. When the formula N is equal to Cv. Concentration is 1.0 multiplied by 1.0, which gives us 1 mole. And now for the number of moles of PbNO32, which is Cv, which is 1.0 multiplied by 1.0, which is equal to 1 mole. Okay, for the concentration of, for the number of moles of K plus, it's 1 mole. And the number of moles of Cl minus is also 1 mole. And then the number of moles of Pb2 plus is 1 mole. And the number of moles of NO3 minus is 2 moles. Total volume is equal to 1 liter plus 1 liter, which gives you 2 liters. Okay, and now let's also find the concentration of NO3 minus, which is N over V, which is 2.0 over 2 liters, which is 1.0 molar. And now for the concentration of K plus, which is 1.0 moles over 2.0 liters, which will give us 0.5 molar. Now let's work on finding the limiting reagent. Let's write down the equation. Pb2 plus aqueous plus 2Cl minus aqueous gives PbCl2 solid. Let's write the number of moles for each, 1 mole and 1 mole, and then we divide by the coefficient. Here the coefficient is 1, so we divide by 1, and here it's 2, which gives us 1 and 0.5. And obviously 0.5 is less than 1, so Cl minus is the limiting reagent. Now let's find the number of moles of the excess reagent, which is Pb2 plus, which is 1 minus 0.5, which is 0.5 moles. And now let's find the concentration of Pb2 plus. Which is 0.5 over 2.0, which is 0.25 molar. And the concentration of Cl minus is negligible since it is consumed and it is the limiting reagent. Okay, now let's start with finding the mass of PbCl2. Okay, aqueous gives us PbCl2 solid. Let's start by writing the given. So there is 1 mole, and the molar mass of PbCl2 is 278. And we have also 0.5 moles of Cl minus, and this is required to find, which gives us the mass of PbCl2 to be 139 grams, or 1.4 times 10 to the 2 grams. Now, for part B, list the ions remaining in the solution in the order of decreasing concentration. Okay, so we already got the concentration of K plus, which is 0.50 molar, and the concentration of NO3 minus, which is 1.0 molar. Now let's find the concentration of Pb2 plus. Okay, so from the last question we got that the number of moles of Pb2 plus is 0.5 over the total volume, which is 2 liters, which gives us 0.25 molar. And now let's list them all in decreasing order, the highest being NO3 minus, followed by K plus, followed by Pb2 plus, followed by Cl minus, and that's it.
Let's do number 3 now. What volume of 0.50 molar HCl is needed to neutralize exactly 20 centimeter cubed of a 0.020 molar of CaOH2 solution? I'll give you guys a few seconds and you guys can solve it. Okay, let's solve it together. Let's first write the equation that's going on. So we have CaOH2 plus HCl to give CaCl2 plus H2O. Is this balanced? Definitely not. So we have to put a 2 here, and then you have to put a 2 here as well. Now this is balanced. We have 1 mole here, like I'm taking the coefficients here, and 2 mole here. Now we have the number of moles, I'm using stoichiometry right here, of CaOH2, number of moles of HCl. Cross multiply, what you get is N number of moles of HCl is equal to twice the number of moles of CaOH2. All I've done is cross multiply. So now we finally get into substituting. N is equal to Cv, so Cv HCl is equal to 2Cv of, let me just put the 2, I forgot the 2 here, of CaOH2, right? Now the concentration is 0.5, V equals 2 into 0.020 into 0.020 again, and the volume should be equal to 0.0016 centimeter decimeter cubed, because what I've done is I've converted 20 into 0.020. And now let's go to number 4. Flasks 1 and 2 are each filled with a different gas and connected to each other with a tap, preventing the mixing of gases. Pressure in flask 1 is P1 and pressure in flask 2 is P2. The tap is open, the gases are allowed to freely mix for some time until equilibrium is reached, and total pressure is measured as P total. Let me just call this A, B, C. Solve parts A to C. And this is flask 2. Let's solve it together. A says find the new pressure of the gas previously in the flask 1 after mixing. Now you should realize one thing, that I have not added more gas. All I've done is increase the volume. I've in fact doubled the volume, 2 times V, right? So since they're inversely proportional, pressure and volume, isn't P1, P of flask 1, new, is equal to P1 old over 2. Because you've doubled the volume, so you have to half the pressure. Same goes for part B, you're doubling the volume. So P2 new, pressure in flask 2 new, is equal to pressure to old, or just pressure 1 old over 2. And C is easy, find the total pressure. All I have to do is P total equals P1 new plus P2 new P1 over 2 plus P2 over 2, and that's it. Let's move on to number 5. I've split the question in 2 parts, parts A and B, and then the second part will have part C. Let's do the first part. 5 says, in the first of 2 experiments, a student is assigned the task of determining the number of moles of water in 1 mole of MgCl2.xH2O. The student collects the data shown below. We have 5 measurements. And then part A says, explain why the student can correctly conclude that the hydrate was heated a sufficient number of times in the experiment. B says, use the data above to 1, calculate the total number of moles lost, water moles. Part B, I says, determine the formula of the hydrated compound. And triple I says, a different student spills some of the hydrate before heating the solid in a covered crucible. This loss will have what effect on the calculated mass of the water lost by the hydrate? Justify your answer. So I want you guys to do parts A and B, and then we'll check them in a few seconds. Let's do part A first. So how can the student correctly conclude that the hydrate was heated a sufficient number of times? As we can see, in the first initial mass is 24 grams. When you heat it the first time, you lost around 1 gram because now some water has evaporated. Second time, you've lost a little more mass, but the third time, you've barely lost any mass. That means basically no additional mass was lost in the third heating, which leads to all water of hydration had been driven off or had been evaporated, because the change of mass is what, 0.001 grams. That's nothing. So basically no additional mass was lost during the third heating. That's why you can say all water of hydration had been driven off or evaporated. And that's the part A. Now moving on to part B, it says use the data above to calculate the total number of moles lost when the sample was heated. So now if you can just see what the mass, the initial mass initial is 24.086 grams, right? Mass final after losing water is 23.162 grams. What's the difference of mass lost? The mass lost, ML, is MF minus MI, which gives us 0.924 grams. So we can say that 0.924 grams of water had been evaporated. They want moles, so we divide by the molar mass, which is 18, which gives us around 0.0513 moles of water. Always take care of significant figures. We have 3 significant figures, that's why we use 3. Double I. Determine the formula of the hydrated compound. So now we know that 23.162 grams is the mass of the anhydrous, because now that the water is gone, it's called anhydrous. Hydrous means with water, anhydrous means the water is gone. MgCl2 and the container. There's a container plus flask, you could say. Now what's the mass of the flask? Mass of the flask or empty container is equal to 22.347 grams. How do you get the mass of anhydrous MgCl2 only? Well, you should obviously know that it's M initial, or the whole, M final, sorry, because the water shouldn't be there, minus the M flask. And you should get an answer of 0.815. Basically what's going on is, here is you have a container, you had some MgCl2 and water mixed. I evaporated the water, and the mass that's total left behind after the water is M final. Now the mass of the empty container is M flask. So if I want the mass of the MgCl2, I have to do this mass minus this mass, right? So now I have this many grams left. Now number of moles of that would be 0.815 over 95, which is the molar mass, 0.00858 moles. But this is not the complete formula of the whole thing, because remember it was MgCl2 dot X H2O, right? So now if we continue, well, to find that X, all you have to do is divide the number of moles of water over the number of moles of MgCl2. Excuse me. Because they have to find a relationship between the number of moles. So it is 0.0513 over 0.00858, which rounds to approximately 6, because we want a whole number if preferable. So 6 is the answer we got was extremely close to 6. That's why we take it to 6. So the final formula for the compound is MgCl2 dot 6H2O. So we find the number of moles of MgCl2. Then to get the X, we do number of moles of water over the number of moles of MgCl2. Coming to part triple I, the last triple I part. A different student spilled some of the hydrate before heating the solid in a crucible. This loss will have what effect on the calculated mass of the water lost by the hydrate? Justify your answer. Well, when you lose some of the hydrous HCl, MgCl2 is MgCl2 dot 6H2O currently, right? Some student who was not handling it properly lost some of it outside. Now we have less left. Do you think we only lost H2O in that? No, right? We lost MgCl2 and we lost H2O. But in our calculations, all we've assumed is we're only losing H2O. We haven't, taken into consideration that MgCl2 was also lost in this, based on what we've been doing so far. So, the mass of water lost after evaporation because we are checking how much was lost, or after being driven off, will be too large. Let me just clarify here, calculated mass. Because we will assume that only H2O was lost, when in reality MgCl2 was also lost. That is why the calculated mass of water lost after being driven off would be too large, because we will have no way of knowing how much MgCl2 was lost when that student carelessly lost some of the solution. Let's do part C now. In a second experiment, another student is given 1.47 grams of a mixture containing anhydrous MgCl2 and KNO3. To determine the percentage by mass of MgCl2 in the mixture, the student uses excess AgNO3 to precipitate the chloride ion. Do parts I and double I, and I'll wait for a few seconds. Okay, let's do it together. Part I asks us, starting with the 1.47 gram sample of the mixture dissolved in the water, briefly describe the steps necessary to quantitatively determine the mass of the AgCl precipitate. To help us, let's use an equation of what's happening. So AgNO3 we're adding. I'm just going to use the states to help me understand better. Plus, let's see, MgCl2 to give AgCl plus MgNO3 we do this thing and then the outside, right? NO3 and to balance 2, right? This is going to be a solid and this is going to be aqueous. So what's happening is we're precipitating this, right? So the first step has to be obviously to add excess AgNO3. The reason why we're adding excess AgNO3 is because we have to make sure that every single mole of MgCl2 is being cancelled, is being used up. That's why I have to add excess. So we have to keep adding until there's no more precipitate being formed. Then number 2, we filter the solution and we separate the AgCl, which is the precipitate. Number 3, we wash and dry the AgCl to make sure there's no water left over, so we know the mass exactly. And then part 4, we determine the mass, either by weighing the precipitate or just by subtracting the mass of the total before minus the current mass, and whatever is gone is the mass of AgCl. Going to part II now. There's 2 parts in II, so I'll just call them part 1 and part 2. Part 1 asks us what's the number of moles of MgCl2 in the original mixture. Let's go back to our initial equation, which said MgCl2 plus 2 AgNO3 to give 2 AgCl plus MgNO3 right? So what we're supposed to do is we have to find the number of moles of MgCl2. Well, isn't the relationship between MgCl2 and AgCl 1 to 2? So isn't this equal to number of moles of AgCl over 2? Well, since we don't have the number of moles of AgCl, it's mass of AgCl over molar mass of AgCl, right? Because number of moles is mass over molar mass, right? Now, since we had the mass of the precipitate, it was given in the second part to be 2.74, and we can easily get the molar mass, which is 143.32, all of that over 2. We should get the final answer in number of moles to be 0.00956 moles. And we have answered the first part of part II. So what we did was we did the ratio. It was 1 to 2, so it's this over 2, and then mass over molar mass. We can easily get that, and then we got the number of moles of MgCl2. Now going to the second part where they asked us the percentage of mass of MgCl2 in the original mixture. We have N of MgCl2. It's 0.00956 moles. We can easily get the mass. It's number of moles times molar mass, which is 95.2, which is the molar mass, times this thing, which gives us 0.910 grams of MgCl2. Percentage is obviously 0.910 over the weight of the whole thing, or the mass of the whole thing, which is 1.47 grams, the sample. You do times 100% and you should get 61.9% MgCl2 by mass. So the mass of MgCl2 is 61.9% of the mass of the complete sample. Start part number 6 now. A rigid 8.2 liter flask contains a mixture of 2.50 mole of H2 and 0.5 mole of chlorine and sufficient argon so that the partial pressure of argon in the flask is 2 atmosphere. The temperature is 127 degrees Celsius. Let's do part A now. You guys can solve it for a few seconds before we check together. Let's first state the given. Let's do it together now. We know that the volume is 8.20 liters. We know that NH2 is equal to, let's see, 2.5 moles. For Cl, we have 0.5. We know that the temperature is 127 degrees Celsius or 400 Kelvin. You just have to add 273. And we know that the pressure of argon is 2 atmosphere. We are looking for total pressure. Now, does anyone know what is the equation that relates number of moles, volume and temperature? PV equals nRT, right? And since we're looking for the pressure, it's nRT over V. Now, we don't know what's the volume for the hydrogen. What is it? When you have a container like this that's rigid, any gas, the volume for it is the volume of the entire container, because the gas is within the container, so the volume of each gas is 8.2 liters. So let's see, for P of H2 it's N, which is 2.5, R is 0.082, temperature is 400, all of that over 8.2, and we should get something around exactly 10 atmospheres. Continuing with chlorine, P of Cl2, now the number of moles is 0.5, R is the exact same, and temperature is also the same, volume again being the same, and we should get 2 atmospheres. Let's move on. Now we have the pressure of hydrogen, we have the pressure of Cl2, we have the pressure of argon. Isn't this the whole thing is P total? So 10 plus 2 plus 2, which is very easy, 14 atmospheres. And that's part A complete. Let's do part B now. Part B says calculate the mole fraction of H2 in the flask. Mole fraction of anything. So mole fraction is X with the gas represented as Y. That's the number of moles of Y over the total number of moles, and total, let's call it. We have the number of moles of hydrogen. We have it for chlorine. We do not have it for argon. So again using PV equals nRT, but this time N argon is equal to PV over RT, which is the pressure of argon is 2 times 8.2 over 0.082 times 400, and we should get 0.5 moles. Now that we have that, we can easily do X of H2, because they're asking us for the mole fraction of hydrogen, which is 2.5, because that's how many moles of hydrogen we have, over 2.5 plus 0.5 plus 0.5, which is 2.5 over 3.5, giving us an answer of around 0.714. That's the mole fraction of hydrogen. And the last one is part C. I'll read it out. The mixture in the flask is ignited by a spark, and the reaction represented below occurs until one of the reactants is completely consumed. The reaction they're showing us is H2 gas plus Cl2 gas to give 2HCl. It's completely balanced, no need to check for that. So now what you have to do is find the mole fraction of all species at the end of the flask, in the flask at the end of the reaction. Now we know that one of these gases, be it H2 or Cl2, let me use red, will become 0. There will be no more moles left. So now we have to consider 2HCl, right? So now to see which one is going to be used up, we have to see which one is the limiting reagent, right? So we have 2.5 moles of H2, 0.5 moles of Cl2, and if you divide by the coefficients over 1/1, this is definitely bigger. So this is the excess reagent, limiting reagent. So we know that Cl2 is going to be completely used up. But how much H2 will be left at the end of the reaction? Well, it's a kind of a not official method, but you can easily do just 2.5 minus 0.5. So 2 moles of H2 will be left. Now the reason why I did this is because they react in a 1-to-1 ratio. For every H2, for every Cl2 mole gone, there will be an H2 mole gone. So 2 moles of H2 will remain. So now if we use some easy stoichiometry, if we know that 1 mole of Cl2 produces 2 moles of HCl, how many moles will 0.5 moles produce? 1 mole. So we have 1 mole of HCl produced. And since argon is inreactive, then we have 0.5 moles of argon. Continuing on the next page, now we can easily find X of H2, X of HCl, and X of argon. Very easily. 2 over 3.5, as is the total. This is 1 over 3.5, and this is 0.5 over 3.5. The number of moles of the gas over the total number of moles. And you should get for this 0.571. For HCl you should get 0.286, and for argon you should get 0.143. And what's the last gas that is remaining? 0. X of Cl2 is very obviously 0 because there's no moles of gas left of Cl2. And that's number 6 solved. Move on to question 7. 5 identical balloons contain each of the following gases: C2H6, SO2, O2, CO, Ne. Each filled to the same volume at 25 degrees Celsius and 1 atmosphere pressure. Part A says which balloon contains the greatest mass of gas? Explain. B says compare the average kinetic energies of the gas molecule. Explain again. C says which gas is expected to deviate most from ideal behavior. And D says 6 hours after being filled, all the balloons have decreased in size. Predict which balloon will be the smallest. I'll give you guys a few seconds to solve the question and we'll check together. Let's start with part A. Which balloon contains the greatest mass of gas? Now we should pay attention that they have said 5 identical balloons, so the balloons don't affect anything, and they have the same volume at the same temperature and the same pressure. So all of these things do not change anything of the mass. Well, we should know that Avogadro's hypothesis says that when you have equal volumes of gas, same volume, at the same conditions, so same temperature, same pressure, then they have the equal number of moles, right? Now, if you all remember, mass is equal to the number of moles times molar mass. So now what does our mass depend on? If the number of moles are same between all 5 of these gases, it depends on the molar mass. And now if the one with the greatest mass of gas would be the balloon which has the gas with the highest molar mass. And the one which has the highest molar mass is SO2. SO2 has the highest molar mass. You can check that. So part A, the answer is SO2. Part B. Compare the average kinetic energies for all the gas molecules in the balloons. Explain. Now we should know that the kinetic energy depends on the temperature. If the temperature increases, the average kinetic energy of each gas increases. Since the temperatures are the same, the kinetic energies are the same. So same Ke. Part C. Which gas is expected to deviate the most from ideal behavior? Now we should know that as gases get bigger in size and complexity of molecules, they deviate more from ideal gas behavior. What does deviate mean is they act less and less like ideal gases, right? So the assumptions that we have made for ideal gases does not apply to them. So what do we mean by bigger in size? I mean bigger in molar mass. That's how you get bigger in size, right? And we just said in part A, which has the highest molar mass? SO2. So SO2 is expected to deviate the most from ideal behavior. Part D now. 6 hours after being filled, all the balloons have decreased in the size. Predict which balloon will be the smallest and explain. Okay. For this one, the answer is neon. So now we have to explain why. Why is it neon? Basically, there's something called Graham's law of effusion, and it is represented something like this. V1 over V2 is equal to the square root of M1 over M2. Well, what we should know is basically the lighter the mass, the quicker it will go. So if mass decreases, the velocity increases. And if you think about it, it makes sense as well. Let's say I have two gases and they are the same temperature, right? Then that means that their kinetic energy is the same. What is the formula for kinetic energy? Half mv squared, right? Now let's say I have two gases. I'll call the first one m1 v1 squared is equal to half m2 v2 squared, right? Now if you think about it, if the mass of the first one is big, then how will the second kinetic energy be the same? Well, the mass cannot compare to the first mass, so the velocity has to be much bigger than the velocity of the first one. So the lighter the gas, the higher the velocity. That's why neon will be the smallest, because most of the gas will be out by that time. Let's move on to question 8. The molecules of a certain gas X of formula NXH2X move 4 times as slow as the molecules of hydrogen gas at the same conditions. Find the molecular formula of X. I'll give you guys a few seconds and you can solve. Let's solve it together. Let's say the given first. So let's say V of H2 is equal to 4 times the velocity of NX H2X. I'm just going to represent them by their formulas. Since the velocities are the same, shouldn't the kinetic energies be the same? Right? Since they are the same temperature, same conditions, right? So since the average kinetic energy depends on the same condition, like depends on the temperature, if the temperature is the same, the kinetic energy is the same. So half m of H2 VH2 squared equals half m and nx, sorry about that, nx H2x. And now I'm just gonna substitute by the equation. Isn't this equal to, or no, let's just keep it for now, v n x H2x squared, right? Now if we substitute vh squared, we get half mh2 into 4vx nx H2x squared equals half nx H2x, and then v of all of this squared, right? Now 4 squared is 16, 16 divided by 2 is 8, so 8 times, well, what's the mass of H2? Isn't that 2? V n x H2x, all of this squared is equal to, well, half m n x H2x v n x H2x squared. These two are equal, they cancel. Let's continue on the next page. We had 8 times 2 is equal to half the mass of the unknown gas. Let's call this x. Well, that's 1632. So 32 equals mx, right? Now, since you know that the molar mass is 32 grams per mole, so basically we have an x, H2x equals 32. The molar mass of nitrogen is 14, so 14 into x plus 2x, because H is 1. 1 times 2 is 2 equals 32. 18x equals 32. Oh wait, no, sorry, 16x. 16x equals 32. X is equal to 2. And that's the final answer. Let's move on to question 9. Below are two diagrams showing the energy profiles of two reactions. Fill in the blanks under each diagram. Now I want you guys to fill in the blanks. I'll give you guys 2 minutes and then we'll check together. Okay, let's check it together. I'll call this reaction 1, reaction 2. Let's do reaction 1 first. Part A asks us what is the reaction type. So we know there are two reaction types, either exothermic or endothermic. This reaction is, now looking at the graph, we can see that the energy is decreasing. Where is this energy going? Now the energy is being released, right? Because as you all know, energy is always conserved. You cannot destroy energy, nor can you create energy. So this energy hasn't disappeared anywhere. It's gone to the surroundings. And when a reaction releases energy to a surrounding, or when the energy of the products is less than the energy of the reactants, this reaction is known as exothermic. So I'm just going to put exo. Now this reaction obviously releases how many kilojoules? You look at the difference. So this is 150 kilojoules. Blank kilojoules is transferred, blank the surroundings. Again, 150 is released, so 150. Now to or from, to the surroundings. The activation energy of the uncatalyzed reaction is blank, while that of the catalyzed is blank. Now, why do we use a catalyzer? Why do we use it? We use it to lower the activation energy. It gives us an alternate path where the activation energy with catalyst, it has to be less than the activation energy without a catalyst, WC. That's the only reason why it would make sense to get a catalyst, right? So now we have two different reaction paths. We have one reaction path, let me do it in red, that goes like this. And the other one, let me do it in blue, goes like this. Now obviously, just by plain reading, we can see that the red one has a lower activation energy. It goes up a lower amount than going to the final state. So for the uncatalyzed, it's obviously 200 kilojoules. And for the uncatalyzed is 150. Look at the heights here. Now let's move to reaction 2. Now for reaction 2, we can see that the reactants are here, the products are here. Wait, the products have a higher energy than the reactants. So that means it's endothermic. The reaction does not release, it absorbs from the surroundings. Absorbs. How many kilojoules? 75 kilojoules. Why? If you look at the difference, if you draw a line here and here, you see that the height difference is 75. So blank kilojoules is transferred, obviously 75. Is it to or from? From the surroundings. And now again I'm going to use red and blue. This is the red. And let me use green this time. This is the green, which has a lower height. Obviously the red one. So the catalyzed reaction would have a lower activation energy. So this would be 200. Again, looking at the heights. And the uncatalyzed reaction would be 300. So you just look at the heights.
Hello everyone, this is Ali Bihadali and I'm doing questions 10 till 18 of the chemistry periodic revision sheet. So yeah, let's start. A student was assigned the task of determining the molar mass of an unknown gas. The student measured the mass of a sealed 1686 milliliters rigid flask that contained dry air. Now without continuing, to be honest with you, you really don't need to read this. I do not recommend reading it. However, for the sake of revising, I recommend reading it this time, but not in the exam, not to waste time. So read it now so that you don't read it later. Okay? So the only values you need to know so far is this, these two, and these three. Now I'm going to give you some time to solve A, B, and D. I'm showing them on the screen. I'm showing you the question also fully. So I'll give you a few seconds to pause. Solve them on your own. Take as much time as you need. Go as fast as you want, but solve at your pace also. So make sure you solve and do your best, so that when you do a mistake, you would always be able to recall it and possibly fix it next time. So yeah, I'm gonna give you a few seconds to pause if you didn't already. Okay, so let's start. A, what does A say? Calculate the mass in grams of the dry air that was in sealed flask. So we're looking for the mass of the dry air. Now let's just, for now, as a tactic, let's write the symbols of what we're both required to find and given. Let's just write the symbols. We can probably, the formula will probably pop up to us when we do so. So let's do mass. What are we given? Density. I mean, we're not given mass, but as I said earlier, also required to find is considered like, you know, write the symbols, just write the symbols. So density. Now density it immediately gives you the formula. It immediately gives you V, which immediately gives you D over, D equals mass over volume. So mass is density over density times volume. Why did I use mass? Because I said calculate the mass. Now all I did was just blindly use the formula, arrange the formula, and just substitute. So now let's look carefully. Also, I didn't say this at the beginning, but please spare some time looking at the symbols. The units. This might save you future mistakes if you ever do that. So degrees Celsius, torr, you know, this is a special one. Milliliters, possibly something you're gonna change. Grams per liter. Well, yes, you're definitely gonna change that. And we're actually using the volume here and the density there, so we're definitely gonna change. So 1.18 times, we said we're going to change this to what? To liters, because we're using liters there. And also liters is SI, so that's why you're not changing the other one. Okay, so what happens if you multiply the two of them? If you multiply the two of them, you get... Also, always check your answer in the calculator. Like, always do calculations at least twice. Or if it's simple calculation, just look at what you have written, just to make sure that you're not doing any mistakes. You should get 1.99 grams. Significant figures 3, 4, 3. So 3, 4, so 3. Okay, so B, calculate the mass in grams of the sealed flask itself. So we have what? The dry air. We have dry air and sealed. We're looking for sealed. How do we do it? Subtract. So 158.70 minus 1.99, you get 156.71, I believe. Yeah, 1. Anyways, so one remark: when you're subtracting or adding, always compare decimal places. When do you do that? Before the operation. So take it as a rule. Well, it is a rule, I guess. Minus and plus are done before the operation, like before doing the operation. What do you do exactly though? Compare the decimal places. And multiplication, division, do the process after the calculation or after the process. Do the comparison, and it's the significant figures that you compare for the final result to be influenced. So the final result here is not influenced by anything after the calculation. After the calculation, you just write it and that's it. So you always compare the minus, for the minus and plus, you always compare the decimal places first. Once you get the answer, you don't do anything to it. Okay, so say that the 0 is not there, just for the sake of this example. If you don't know what to do, like if you have varying decimal places, before we had the same one, right? But what if we remove the 0? What do we do? In this case, you round this one. It becomes 2.0. You round the one with the more decimal places to be like the one with the least. So like to get the least number of decimal places. So 2, and you subtract. But again, in this case I'm changing given just to show you. So I'm getting it back. Well, we've already done the calculation, so it's right here. Let's remove this so that we have more space. Boom. Let's go. So C. What does C say? Calculate the mass in grams of unknown gas that was added to the sealed flask. So we need unknown. We have unknown and sealed. We have sealed, so of course we can get unknown, right? So 159.45. The hell am I doing? 45 minus 156.71. Subtract, you should get 2.74 grams. Again, subtraction, same different places. I don't care what this is or what value I get here. As long as I care here, I wouldn't care there if it's subtraction or addition. So part D, using the information above, calculate the value of the molar mass of the unknown gas. Molar mass, that's a symbol, right? Now we just had what? Mass. What other things pop up in your mind? We have the density. I'm probably not gonna use it. We have the volume, we have the pressure, we have the temperature. Things are starting to show. Of course, we'd use in this case PV equals N is replaced by M over mass over molar mass. R stays R and T. So we're looking for molar mass, right? So rearrange the equation. Okay, yeah. So you get MRT over PV. Now time for substitution. We got earlier to be 2.74, so 2.74. R is 0.0. Now, just to avoid confusion, or I mean, I also could be confused, but let me tell you what I know. Do you use 82 or 80? 0.8, I mean 0.082 or 0.080, or a possible other number, maybe the full or 4 decimal place or something. Which one do you use in the exam? Well, let me tell you what I would think. I would honestly believe that they would give you the R in the exam. Why? Because they've done so with the electrons and the mass of the electrons and blah 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 in the physics. In the physics, they give mass of the electrons and the charge of the electron, I believe. At least the mass, or one of them at least. But they give the value that they didn't in the sheet. They only, put it in the answers, but that's it. So I honestly would believe that they would give you the answer, but say that they don't. The answer key uses 80. So for the sake of the example, I'm going to use 80. But one last thing, like for example in the exam they didn't mention, for example, they didn't say which one, and you really want to know if it's 80 or 82, check the other questions in this sheet. If they use 82, probably this is an exception. Like, as in, I don't mean that you use 80 only here. It probably just means don't use 80. Maybe it was a mistake, some kind of thing. Mood, the guy who put the answer, just anyways. So yeah, let's just continue. By the way, if I confuse you guys, you can always go back to a few seconds or minutes ago and check what I just said, if you want to hear what I said again, to confirm if you heard it properly, if I missaid something. Also, sorry guys if I make mistakes, I just can't see them immediately. If I see them, I'll correct them, so just don't mind me if I do mistakes. I'll try my best not to do them, not to confuse you. So 750, that's what the pressure, right? Now this is torr. To change from torr to atmosphere, according to the solution, it uses 760, which I honestly did not recall. But now, from now on, to recall them, this looks to me like the millimeter mercury. So that's how we can remember it. It's like the millimeter mercury. So you change by dividing by 760. But then again, this is torr to atmosphere, not millimeter mercury, but just saying that how you could remember it. So what we're left with, volume 1.686. Do the calculation. What do you get? You get 39.0. Now units. First of all, let me tell you significant figures. No, this is you don't care. You take the value, so you don't care. Again, you don't care about this one. And 3 you don't care. 4, so 3. Anyways, so the units. How do you get the unit? Well, what are we doing? We're doing. We're getting molar mass. Well, I know that number of moles is mass over molar mass, correct? So molar mass is mass over number of moles. Unit of mass, grams. Unit of moles, moles. So we are done. Grams per moles. That's part D. So let's use some space here. Okay. Now parts F and E. I'll give you some time to do these because they weren't shown on the screen. So have a few seconds to do them. Okay, so let's start. E. After the experiment was completed, the instructor informed the student that there was the carbon dioxide. So after all this, all what the student does and the calculation, everything, the teacher decided to tell them that it's carbon dioxide. and it's of course 44 degrees, 44 grams per mole, the mole mass of the carbon dioxide. So you do get a different value than the value you've calculated. And which one's wrong? Of course this one's wrong, but of course due to some error, which we later on will try to figure out which is what could be possibly the error. But for now we need to calculate the percentage error. So to do that, it's always calculated minus real or given or whatever it's called, minus over the real given, whatever it's called. So the calculated one minus given over given, or real over real. So anyways, calculate is what? It's 39 minus 44 over 44, and do this quickly, minus 11.4%. Let me just double check. Also you multiply by 100 and percent. There you go. 39 minus 44, just to double check the calculation. 11 point, okay, correct. So from what does this tell you? This tells you that the value we just calculated is less than the value we're supposed to get by an 11.4%. Minus tells you it's less, and this number gives you how much, by how much. So F we're taking cases. F is saying for each of the following two possible occurrences indicated whether it could have been responsible for the error, or blah blah blah. You need not include any calculations in your answer. So the only thing you need to say is this possible, is it not, and why. So let's look at occurrence 1. The flask was completely flushed with CO2 gas containing some sulfur dioxide impurity. Well, that's basically saying that you had some CO2, but rather than saying only CO2, you had possibly some sulfur dioxide impurity in it. Now, we said some and some impurity, so it's not as much, but you still had it. Now, sulfur dioxide, is it denser or less dense than carbon dioxide? It's denser, right? So, unless, you know, it's a small, incredibly small amount, but it's still denser than CO2. So, it slightly would deviate the molar mass. It would slightly become bigger, a slightly bigger molar mass. So what did we say? A slightly bigger molar mass. What do we have? A slightly, well, not exactly slightly, but it's less than the one we're supposed to get. So we have a contradiction. So occurrence 1 is not possible at all. It's the opposite. It's supposed to decrease. So if you told me somehow you had nitrogen, which is 28, and carbon dioxide is 44, that's possible. Yes, it is possible, a possible occurrence. Not sure if it chemically wouldn't work, but realistically, with calculations and all that, it would work. So yeah, so occurrence 1 in this case, because they're using SO2, it is impossible. Occurrence 2, the temperature of the air was 23 degrees, but the temperature of CO2 was higher than the reported 23 degrees. So it's basically saying that the temperature that we have, we supposedly are supposed to be given a higher CO2 temperature. So they're telling us that we got a temperature that's less than the real temperature. Wait, let me rewrite it. We got a temperature, that's what we got, right? 23 degrees Celsius, less than what we're supposed to get. So because we got a lesser value, if we go back to the equation down there, if we got a lesser value, what are we supposed to expect to get for the molar mass? A lesser value, right? And what did we actually get? We indeed got a lesser value. So this is in fact consistent with the equation, or at least the reactions in the equation. Yeah. So occurrence 2 is plausible. It could happen. And so we don't have anything to say no to it. So occurrence 2 happens, or possibly could be, occurrence 2 could possibly happen. Why? I just said because you can immediately reference the formula. You can say in the formula blah 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 that if the temperature increased, in this case decreased. So if the temperature decreased, the molar mass would decrease, which is consistent with the calculated molar mass. You can say this however you want. You can go back to the marking scheme or the given answer, sample answer. Probably said it better than me, but yeah, anyway. So next question, 11. 6 grams of a gas exerts a pressure of 0.20 atmosphere. What extra mass should be added in order to increase the pressure to 0.80 atmosphere, keeping other variables constant? So what's changing in here? we have the mass is going to change. We're going to add a certain amount to mass, and we have the pressure. The pressure is going to increase in this case. So obviously, if the pressure increases, the mass should increase to increase the pressure. So what relation will we use? We will use this relation m1 over p1 equals m2 over p2. Now the orientation doesn't matter, which one's up, which one's down, doesn't matter, as long as it's directly proportional, so one over the other, giving a constant. That's how you're equating them. So yeah, so let's continue. So we are looking for the added mass or the extra mass, but before that, let's find the final mass first of all. So m2 is p2 over p1 times m1. Okay, so how much is p2? p2 is 0.8 0.20 times m1, which is 6.0. You get 24. Yeah, 24 grams. Two significant figures. So 24 grams. We're looking not for the final mass, we're looking for the added mass. Like realistically, when a person has a certain amount of mass and they want to know how much to add to get this amount of pressure, so they're going to subtract. So 24 minus 6.0 equals 16. Yeah, 18, sorry. 18. Yeah, okay. 18 grams. Just a side note, 0.0, there's no decimal here, so you round this to 6. 24 minus 6 is 18. So if you have any doubts, I hope I cleared it for that part. So B, a fixed mass of gas at 0 degrees Celsius exerted a pressure of 0.2 atmosphere. What will the pressure become if the gas is heated to 27 degrees Celsius at a fixed volume? So the volume is fixed, so we don't really care about it. We have the pressure, we have the temperature, and these two are changing. So pressure and temperature, P1 over T1 equals P2 over T2. Okay, so in that case, by the way, also same thing as that one, the orientation doesn't matter. Okay, so let's continue. We're looking for P2, correct? So P2 equals T2 over T1 times P1. So T2 is what? T2 is, yeah, okay. So T2 is 27, let me just close this, 27 plus 273 over 273 plus 0, so I'm not going to write it, and the pressure, initial pressure is 0.20. Now just add them, 273 plus 27, yeah, 27 over 273 times 0.2. You get 0.2197, so on. Now you're adding here, I guess you shouldn't really care as much, no, but this one is again two significant figures, so 2 here, same thing, so 2 what? Atmosphere, because you're looking for pressure, and it's pretty much easy. So yeah, okay, so we're doing question 12, but before anything, download the new or the updated revision sheet for the chemistry. I uploaded it on the main group, but you can also download it from your friends or web school. So I'll be giving you a few seconds to pause this video and try solving this question on your own, and once you're done, unpause and we'll do it together. Okay, so let's start. So first of all, before anything, we here are using we're using an iron 2 compound, and we're titrating it with what? With the permanganate ion, with a permanganate solution, but it's not given to us, so I'm just going to mention the ion for now. So let me remind you a bit about titration. So in titration, let me just do this. Okay, so in titration, here they're just adding the solution that's going to be your main reactant, which is here. In this case, it's the iron 2 solution, or the iron 2 compound. So your solution now needs a titrant. This is called the titrant. You're titrating with this. So this titrant, which in this case includes the permanganate ions, you're dropping it drop by drop, as you can see, drop by drop. So what you're doing is you have a certain concentration here, and you have an incredibly small concentration here, which is its value is a drop. These two will definitely, as you can see, it will definitely react to they will definitely react to give, as you can see, Fe3 plus plus Mn2 plus some water. So basically the idea is whenever there's a permanganate ion, both the Fe2 plus and the permanganate ion are going to give, and I mean some acid, they're going to give these. So that means any drop that you give is immediately consumed. So with that idea, we're asked, by the way, what I just mentioned is important here, but I'm going to reference it later. So let's first of all do the oxidizing and reducing agent, which is really easy. So the oxygen has, I'm going to go through this quickly, it has a charge of -2. -2 times 4 is -8. So you have x minus 8 equals -1. So x is +7. Now you're going from +7 till from +7 till +2. So that's a 5 decrease. Well, a decrease means it's getting reduced, which means it's the oxidizing agent. Now automatically this is the reducing agent, but if you want to try Fe2 plus into Fe3 plus. 2 to 3 oxidized, therefore it's a reducing agent. We're done with part A. Reasons, well, it says explain using oxidation numbers. Well, I definitely did. I mean, even though I just wrote this, but in the exam, you explain it the way I just explained it, you know, like you get the Mn and how much it changed and blah blah. So now part B. The mass of the mass of a sample of iron 2 compounds carefully measured before the sample is dissolved in distilled water. The resulting solution is acidified with sulfuric acid. The solution is then this is where the H plus came from. Titrated with a permanganate ion. So describe the color change that occurs in the flask when the endpoint of the titration has been reached. First of all, let's go back. So as I was saying, you're dropping this drop by drop. So its concentration is really low, and whenever you have a drop, it immediately reacts with the iron 2 ion to give an iron 3 ion and the manganese 2 ion. So with that, what's the color of this? It's greenish. This, it's pinkish. But there's one issue. It's one drop and it immediately reacts, so you'll never be able to see this pinkish color. Well, not exactly, but you won't really see any pinkish color as much. It's going to be mostly greenish. So it's greenish to something. Now let's figure it out together. In titration, you're going to technically neutralize or fully consume one of the reactants. So one of them you have in excess, and one of them is limited. So the one that's in excess is you're going to drop until you see a color change. This is called the what was it called again? The endpoint. It's also called the equivalency point. It's also called, by the way, I really like this one term. It's called the titration error. Now, why is it titration error? Because you're adding one extra drop to see the color, but in between it should be, you can kind of say colorless, because there's no iron and there's no manganese, permanganate ion. Those two kind of like neutralized each other or fully consumed each other. So when you add that extra drop, now you're finally able to see the color change, which is pinkish. That's when you know you have an excess permanganate ion by just one drop. That's how we can calculate the error and all that. So the color change is definitely in this case greenish to pinkish. Greenish due to the Fe2 plus ion, pinkish due to the excess MnO4 or the permanganate ion. So now with that we're done with B. We explained why the color change happens. We explained how, you know, as I said earlier, that this is now in excess before this gets consumed, blah blah blah. Okay, so part C. What effect will adding, let me just do this, oh whoops. So what effect will adding more of the what? It says aliquot. Aliquot also refers to here the titrant, which in this case is the permanganate ion. So they're saying, oh, sorry, adding less, yeah. I'm not sure if I said more or less, but here it's saying less. So if you're adding less of the permanganate ion, what will happen to the determined value of the mass percent of the iron in the compound? So you have the iron compound and you want to get the percent mass of iron in its compound. Okay, so with that, it's the mass of the iron over the mass of the compound itself, the Fe2 compound, blah blah. So yeah, so how do you get that? Let's start with step by step to reach this. So first of all, we know that we're doing some kind of neutralization reaction. So with that, you have the number of moles equal. But here, keep in mind the coefficients. You have 5 Fe2 plus and you have 1 permanganate ion. So for the number of moles to be equal, you multiply this by 5. So as if you're saying 5, 5, you know, for them to be equal. So yeah, so 5 times, or if you want to take it as a rule, it's coefficient times the number of moles. If you have two separate coefficients, you have to take ratios, but let me not go through that. So yeah, the coefficient times the, what are we given? We're given the molarity, and we're given the volume, so we get the number of moles. And number of moles times the coefficient gives us number of moles of what? This is the number of moles of the iron. This is the number of moles of the let me just write it. Okay, number of moles of what? Of the permanganate iron, MnO4. Anyways, MnO4 nice. So yeah, now you have the number of moles. You want the mass of Fe to reach this. So mass is what? Mass of Fe is, well, we know number of moles is mass over molar mass. We can get the molar mass from the periodic table, but for now let's just keep it M. So mass is number of moles times molar mass. So mass of Fe is what? It's the number of moles times the molar mass. So number of moles we got here, so 5 times molar mass of what? Of the permanganate iron times the volume. Well, I mean, they gave us M and V, so I don't need to point this out. You see, they gave us M and V. So times the molar mass of the Fe, which I believe is somewhere around 55.85 or something. So I'm just going to write it as a number so that you don't get confused if I write, let's say, another M. Yeah. So now you want the percent mass. So how do you do this? Percent mass is simply, as we said, the mass of Fe over the mass of the Fe compound. So mass of Fe, 5, molar mass of the permanganate iron, volume of the permanganate iron, times the molar mass of the Fe itself. Gives us the mass over the mass of the Fe2 plus, I mean Fe compound, Fe2 compound, which is said here to be G. They give us G. So now you truly understand why they gave us M, V, and G. So now we have this equation. So what do? We are looking for less aliquot, so less titrant, so less permanganate ion. Now what does it mean, less permanganate ion? Which means less volume, right? So less volume means less number of moles of permanganate ion, which means less number of moles for the iron, which means less mass for the iron, which in fact means less mass percent of the iron. That's how the solution does it at the back. But I personally believe if you have this equation down, you can immediately point out that less volume means less percent mass. But anyways, they're free to do whatever they have, so that's how you do it. Okay, so question 13. Now this one's really easy. I'll give you a few seconds to pause and solve it, and then afterwards we'll do it together. Okay, so let's start. It says 3 grams of ethane were burnt in a calorimeter. So ethane, that's C2H6, and each carbon is 12. So it's 2 times 12 plus 6 equals 30. Now what's that? That's the molar mass, right? So it's grams per mole. Again, if you forgot the units, it's N equals mass over molar mass, and then you know what to do next. So with that, we have the molar mass, we have the mass, so we can get the number of moles. Number of moles is molar mass times, it's the mass over the molar mass. So with that, it's 3 over 30, which is 0.1. Well, if we care about the significant figures in this case, this one's calculated, so it's 3 significant figures, and we looked for the molar mass, so moles. Now why do we need the number of moles? Why did I do this? Well, we need delta H, the heat of combustion per mole of ethane. Now for that, you need minus Q over N. We just got the N. So now you need the Q. For me, I'm going to immediately substitute. The N, we said 0.1. Now what for the Q? The Q is, what is Q? Q is MC delta T. However, depends on what C you have, you can do C delta T. The difference is one specific heat capacity and the other is just heat capacity. Here they didn't say specific. Now say that they forgot the word. Look at the units. Kilojoules per coulomb. Now you might say, so this has 2 units, the other one has 3 units. What are you achieving? You're achieving joules, you're achieving energy. So here, to achieve energy, you have to multiply by the temperature, and that's it. So that's why you need only T here. However, here in the other one, its units must be something like joules grams per degree Celsius. So no, sorry, it's down. I knew something was wrong. Yeah, so it's per grams degrees Celsius. So that's why in that one you have to multiply by the mass and by the temperature to get the joules. So anyways, we'll use C delta T. We're given C, so 25, and this is 5 degrees rise. By the way, this is delta T, and we have an increase in 5 degrees Celsius. I mean, so if you calculate it, you get minus 1250 kilojoules per mole, which is, in significant figures, 1.3 times 10 to the power of 3 kilojoules per mole. Kilojoules, because we have here from the C, it's in kilojoules, so we continued with that, and then times 3 to the power of 3, so that we get 3 significant figures. Two significant figures, because the change in temperature is 2, so we should end up with 2, and that's your answer. Okay, so question 14. I'm showing you part A and B, so pause the video and try your best, and then once you're done, we'll do it together. Okay, so question 14A. We're mixing hydrochloric acid with sodium hydroxide in a coffee cup calorimeter, and we're getting the temperature to be 26 degrees, so that's a 6 degrees change. If you want, let's write that. 6 degrees change. And we're looking for the delta H, so that's immediately delta H equals, well, it's minus Q over N, and then we're going to substitute later. So we have the hydrogen ion, or the H plus OH minus, to give the H2O, water. So assume that the density of the solution is 1 gram. Now this is an interesting unit to use here, because we usually are used to, having volume here, and usually the trick is that, people keep it in centimeters cubic when you're supposed to change it to decimeter, especially when you're doing number of moles and all those standard unit ones. But in this case, when you do Q, now let's do Q. Q is MC delta T. Now this is energy absorbed by the solution. So the energy absorbed by the solution. So in that case, we're talking about a solution. Now, solution of what? Of sodium hydroxide, of hydrogen chloride, or is it both? So it's both. So because it's both, you have to add the volumes. Now, how do you add the volumes? You add them like this, or do you add them like this? The difference being is that you're adding centimeter cubic here, you're getting the answer to be in the same unit. Here you're adding decimeter cubic and you're getting the answer to be in the same unit, which is again decimeter cubic. So the decision has to be made based on C in this case. C is in what unit? Not C. We're looking for the mass, right? This is all just volume. And to get the mass is density times volume. You can do it by checking density equals mass over volume. You get, mass is density times volume. So you get this. So density, in this case, we have the volume, but we're looking for the units, so we look at the density. Density here has the units grams per centimeters cubic. So you're forced not to change this to be able to get the grams. Otherwise, you're getting something else. So to get the grams, you have to keep the same units. So again, you're going to add them this way. This is the correct way, and this is the wrong way. So add them like this, you get 200. So now we continue. 200, 200, that's the volume, times the density is 1, times, we said the C is what? 4.2, times the delta T, which is 6. So now let's do this first. 200 times 1 times 4.2 times 6. You get 5040 joules. Now n, how do we get n? N, there are multiple ways, but let's see. Okay, so we have volume, we have molarity, we have volume, molarity. Well, we know one famous formula, which is n equals cv. So that gives us now first of all, what do we do? Do we use the hydrochloric, or do we find the H plus moles, which is given from the hydrochloric acids information, which is the volume and the molarity, or the other one, the hydrochloric acid, which gives us the OH, or what do we do? So in this case, we'll look, if you either lock your eye on the water, or let's say the H plus, one of the reactants, you're going to use that and you say per mole of that. In this case, it's 1, 1, 1, 1, so really it doesn't matter which one you pick. Just pick one of them, don't pick both, as in mix or add or anything. So concentration of one of them, I'm going to pick the HCl. So that's 1 times. Now here is the trick, it's number of moles, so you have to change from centimeters cubic to decimeter cubic, because number of moles does not accept anything other than decimeter cubic or liters, somewhere in that scale. So 0.0, blah, 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 you get this, and then you divide them, you know, in this formula. I'm not going to write it, I'm just going to put it in the calculator immediately. 5040 over 0.1. Now we get this big number. So delta H is minus 50400, which is 50.4 times 123 10 to the power of 3 what. Well, we're working with joules, so joules, so you can replace this with kilojoules if you want. Kilojoules per mole, and we're done. Now part B, you can do the same thing, so let's just do this faster this time. So we're looking at what? Delta H. So delta H equals, by the way, as I said, I got the coefficients from here, that's why I wrote this here. Now same thing there, this is the reaction, again 1, 1, 1, 1, so I'm going to go really fast, over n, and then we said this is minus mc delta T over number of moles, we said is CV, and the C's are different, keep that in mind, don't cancel. So minus m, mass, we use this from density, so density times volume, times the C, times the delta T, over, we said CV, and then you just replace immediately. I'm just going to show you how you replace, so that you know what numbers I'm using. Again, we're looking at this one, so its density is 1, volume is what? By the way, it's per milliliter, and this is given in liters, so you do the change here also, by the way. So that's 200. C is what? C is this, 4.18. I don't have them. Oh yeah, I do have space, never mind. Okay, so 4.18 times yeah, it's 1.5 change in temperature, and then CV, as I said, pick any of them, it doesn't really matter, they even have the same concentration, same volume, so just pick any of them. And again, number of moles, so you have to keep the units appropriate, so you get this. Let's put this all together in the calculator and see what we get. 200, whoops, did a mistake. Anyways, I'm just going to do this immediately. 200, 4.18, 1.5 divided by 0.2. We get somewhere. I'm not going to double check my answer. It could be wrong, but I'm not going to double check it. I know that the process is correct. So you should get something like this. But just to, in case, let me just double check quickly. So just to check for the calculation, everything else should be correct. And there you go, it's correct. So we're done from this question. Okay, so question 15. I'll give you some time, pause the video, and afterwards we'll do it together. Okay, so let's do this. First of all, the entire concept is that you have something hot and you have something cold, be it a solution, a solid, whatever it is. The temperature will go from the heat energy is going to flow from the hotter one to the colder one if you have some form of connection between them. In that case, it's direct contact. It's a metal dropped into that calorimeter, which contains water, with cold water to be specific, like from hot to cold. So you're going to have a temperature change. Obviously, the higher temperature one, which is, let's say, the hot one in this case, is going to drop, and the one with the lower temperature is going to increase because it's being given heat energy. Now this will keep happening till they reach a certain level where both temperatures are the same, and you have no net heat change, no net temperature change. So that's, of course, assuming there's no heat loss, there's no energy lost anywhere. In that case, because there's no energy loss, energy lost here is going to be directly gained here, so that you can equate them. And we know that we're talking about Q's, and Q's are MC, each Q is MC delta T, MC delta T, and M here is the mass of what? The mass of the piece of the metal, for example. Let's have this to be metal, and this to be the water solution, whatever you want to call it. So now the mass of the thing, of the metal. So we have the mass, 20 grams. We have the heat capacity, we want to find that, so let's not put parentheses. Delta T, well, we know for sure it's going to equilibrium condition, equilibrium temperature. So it's going from high 62 to a lower 27.5. Even though the water is 27.5, I just said that the heat change or the temperature change will keep on going until they have the same temperature, which everything is going to stop. No change in temperature is observed, no change in heat energy is observed after that, after they reach the same temperature. It's like two people fighting, and then when they reach an agreement, everything stops. Same thing here. So you're going to do 62 minus 27.5 equals MC. We have the M to be what? To be 40, and then C is given to be 4.18, and delta T is given to be, well, 27.5 minus, let me extend this, minus 25. Okay, so with that you can just C equals, well, let's right now I'm subtracting the temperatures. 26 minus 27.5, you get 34.5. now I'm multiplying it by the 2, and now I'm multiplying the other side, and then I'll divide by the answer. Mixed two sentences. Anyways, 40 times 4.18 times 27.5 minus 25, and you get the final answer, which is correct, 0.61, if you round. 61 what? Well, this is, well, we're working with this. They even said in, so we really don't care, just immediately joules, grams, degrees Celsius. So that's how we get the answer. Okay, so question 16A and 16B. So pause the video, especially for 16A. 16B you can do it easy, but 16A, you need to know the definition. So try your best, try recalling it. Don't worry, I have a way for you to memorize this easily. I personally use this way. But for now, pause it, try your best, and once you're done, we'll do it together. Okay, so let's do this together. So first of all, we're asked to define the standard enthalpy of formation of a compound. Now, if you want to answer this, you will be kind of like lost. Where do you start? That's the main point. Where do you start? It's like memorizing lyrics of a song. You have to know the beginning and recite it till the end. It's like you remember it sequentially. You know each word, you know the full phrase, you know the full sentence, the full paragraph, from beginnings and endings and stuff. So let me show you this way. I personally use it to memorize this. So for me, I break this into parts. Standard enthalpy formation of a compound. So I break it to standard enthalpy formation of a compound. So here they are. For me, enthalpy means energy change or enthalpy change. Standard means standard states and standard conditions. Formation of a compound, formation of 1 mole of a compound. From where? That's the question. From where? From its elements. So now link all of this together. I know this kind of like looks funny, but let's do this. So it's the formation, it's the enthalpy change. Let's go one by one. It's the enthalpy change of, well, we can't mention standard yet, so let's skip it. It's the enthalpy change of the formation of 1 mole of compound from where? From its elements. In what state? In the standard state, standard conditions. There you go, that's your definition. Let me repeat it one more time if you're not convinced. So, enthalpy change of formation of 1 mole of compound from its elements in standard state, standard conditions. There you have it, you're done. This is personally how I memorize it. So now part B. Let's get this empty space here. So part B, gaseous hydrogen and fluorine combine to form hydrogen fluoride. So let me write the formula, H2 plus F2 to give 2HF. So this is the way it is, but we said 1 mole. So if we're working with, we want the formation, the heat of formation of hydrogen fluoride when talking about the standard enthalpy of formation, which is what we just referenced. We said 1 mole, right? So let's do this 1 mole. So how do we do it? Just write like that, and then you have half. Okay. And then this was, you probably know what to do from now on, honestly, but I'm going to do it anyways. So 540 kilojoules per mole. Oh no, sorry, just 540 kilojoules. And then here you have 1, so you divide by 2. Okay, so minus 2, believe it's just write 4. Okay, so 270 kilojoules, and you're done. That's it, pretty much. Okay, this one's pretty easy. It's also fun. So I'll give you some time. Pause the video and try solving it. And once you're done, we'll do this together. Okay, so let's do this together. We're looking for the delta H of this reaction. We're given 2 reactions. We're asked to use Hess's law. Now this can be really fun. It's just like puzzle solving. So you have Fe2O3. This caught my eye. And here I saw it again, so I'm going to flip this reaction. So let me write, okay, it's already blushed. So let me flip this reaction. We get Fe2O3 giving 2Fe plus 3 over 2 O2. And here delta H became what? Became plus. So 820 kilojoules. However, we don't just need to do that, we also need to multiply by 2. So let's do that. Here becomes 4, here becomes 6. And this times 2, let me just write it here. It's 1640. 1640. Okay, that's one equation done. Now here, you don't need to reverse, you just need to multiply by 3. That's all you need. So 3 times, 3C plus 3O2 giving 3CO2. Delta H, we need to multiply by 3. So minus 390 times 3, that's minus 1070 kilojoules. And then by Hess's law, in this case, just add. This is 6 over 2, which is 3. 3 and 3 cancel. And you are basically left with 2FeO3 plus 3C. Okay, for a second I thought that was a lone oxygen. Plus 3C to give 4Fe and 3CO2. Delta H, you just add them. Delta H equals, so we have the negative 1170 plus the positive 1640, we get a positive 470. It was an easy one. Okay. Question 18, this is another nice one. Pause the video, try doing your best, and once you're done, we'll do this together. Okay, so let's start. Question 18. So we're given a formula and we are asked to find the heat of formation, and we're given heat of formation of each one from their elements in standard state, standard conditions. Now we're not given oxygen because it's already in its standard state. You cannot get an element from its standard state if it's already in its standard state. Like it's basically saying nothing is happening. So 0. The energy change for this one is 0, the heat of formation. So yeah, so with that, the formula is products. So H delta HF for the reaction is you have the delta HF of the products minus the reactants. So what do we have as products? So it's delta HF of what? Of the products, which we'll start with the CO2, adding the products together. So, and what's the other one? H2O minus the reactants. We said the O2 is 0, so no need to include it. So I'm gonna skip immediately to the C3H8, and let's just write that. But however, I missed something. There are coefficients right here, because you're forming 1 mole. But do you have 1 mole? Well, for this one, yes, you do, but for the other ones, no. So in this case, it's 3 times the CO2, the delta HF of the CO2, and you have 4 times the delta HF of water minus delta HF of C3H8. There, it's 1 already, so yeah. So 3 times minus 390 plus 4 times minus 286 plus, well, because minus makes a plus, so plus 100. This is definitely giving you a negative answer. Let's just get what this answer is. So minus 4 times, or you know, minus 26. By the way, I'm starting from here. I'm doing this because I did 100 plus. Minus 4 times 286 minus 390 times 3. You get minus 2,214. What are we talking about? Kilojoules per mole. After all, it's still a delta H. So in kilojoules, we are working. Oh no, they just said delta H. Yeah, delta H, sorry. Delta H. We are given delta HF of these, but we're looking for delta H. So yeah, this is the answer. But if we stick to significant figures, I mean, it's kind of messed up, to be honest. So they either have this answer, or they probably have something like, I'm guessing they have something like this, times 10 to the power of 3 kilojoules. It's one of those. Anyways, it's not really important. Both of those are correct. So yeah.
Hey guys, so we'll do number 19 to 27. So let's start off with 19. So for ionization energy, you look for the biggest jump in between them. So the base jump is, this is around 2 times, and this is also around 2 times. Here it's around 2 times as well, and then another 2 times, a little more than that. And here you have more than 4 times. So this, in between this and this, is the biggest ionization energy jump. So it's group 5. Now group 5, it has 5 valence electrons, and it forms 3 minus ions. So what was the expected chloride is, you either donate all these 5 valence electrons to form a covalent bond, or you donate, it shares 3 electrons. So that's why it's either YCl3 or YCl5. The first ionization energy of aluminum is less than that of B, because valence electrons of aluminum experience more shielding. That's right, because aluminum, as you can see, is like here, the aluminum nucleus, and then you have the core, and then you have another core, and then you have these 3. But boron, it just has the core, and then it has the outer shell. So there's more shielding in aluminum. As for the ionization energy of F, it's greater than O, because F has a higher nuclear charge. What this means is that this is more positive of F compared to oxygen. which is why it attracts the electrons more. The atomic radius of calcium is larger than of Mg because it has more core electrons and more shells, which is why it's bigger, and then Mg is just this much with 2. And more shielding, obviously, because more core. The second ionization energy is greater because you have the same nuclear charge that attracts more electrons now that this is gone. So it's more focused on this electron. The atomic radius of Cl is smaller than that of S because Cl has a large nuclear charge. What this means is Cl is very small compared to S because having a larger nuclear charge means it attracts the electrons more. Okay, so for number 21, you have these 3 photons and you are asked what they do to molecules. So microwave, it has the least amount of energy, so all it does is just rotate the molecule. So if you have a molecule here and it just hits it, it will just maybe like rotate it, that's all. And then infrared, it has more energy than that. If it hits it, it will make it vibrate a lot because it has more energy. That's why it can do more damage or more effect. And then ultraviolet, it will cause electrons because since it's very energetic. You have this atom here, this is the nucleus. It will maybe cause an electron over here to move up energy levels over here because it has energy, a lot of energy, which it can use to move the electrons upwards. So that's what ultraviolet does.
Let's do number 22. The plot below shows the first ionization energies of period 3 elements. Using the plot, do you expect the following reactions? Let me just put the S. Reactions to be exothermic or endothermic. You have 2 reactions. I'll give you guys a few seconds and then we'll solve it together. Okay, let's solve it together. For the first one, I'll just be writing the half reactions of what's going on so we can visualize it better. So for the first one, we'll do Al gas plus 1 ionization energy, or ionization energy 1, to give Al plus gas plus 1 electron. Because if we refer to what I've written here, if you are removing an electron, that's endothermic, and if it's endothermic, you're absorbing energy, so it has to be on the left side, and adding electrons is exothermic. Okay, so here we can see that it is endothermic. And for the second one, Mg plus gas plus 1 electron to give Mg gas plus ionization energy 1, and this would be exothermic, right? Now if we can just compare the energies, we see that Al, if we draw the line, is approximately, let's give it a value of around 600 kilojoules, and if for the Mg it's closer to 750. Since the value of the ionization energy of Mg is larger and it's exothermic, it makes more sense that the whole reaction would be exothermic. Think about it this way. We know that delta H for endothermic is positive, endo, and for exothermic is negative. So think of the Al height as positive and think of the whole height as negative. Which is higher? Well, obviously the negative. So the whole reaction delta H is negative for the first one. Right? Now let's go on to the second one. Okay, the second one says S gas plus Cl plus gas to give S plus gas plus Cl gas. Now we can see the quick reaction is S plus ionization energy 1 to give S plus 1 electron, and Cl plus gas plus 1 electron to give Cl gas plus 1 ionization energy, or ionization energy 1. This is endothermic or plus, and this is exothermic or minus. Now if we just quickly go back to the graph, we can see that, if I'll just erase this so it's clearer, we can see that the S here, the positive, because it was absorbing energy, and the Cl, which is higher, is negative, the whole thing. So well, this clearly shows us again that the whole reaction is negative, because the Cl energy, ionization energy of Cl, is greater than ionization energy of S, which shows us that the whole reaction, delta H, is negative, exothermic. And that's the answer.
Okay, so for number 23, you are asked to about the spectrometric or calorimetric method, which is basically how you determine the absorption or concentration of a solution, or the absorption of light. So you have light that goes through a hole, and then it passes through a test tube, and it has to be a colored solution. That way the light will bend in specific ways. So this is like blue, and this is red, and then you have the spectrum that measures it, the light intensity over here, and then depending on the intensity, that's how you find out the absorption or the concentration, if you know already the absorption. So let's start with the letters, the number A, B, C. So number A, it asks how do you get a concentration of such and such. This is basically just a dilution question. So for diluting the 0.1 to 0.02 using distal 10. So you have 0.1 whatever, and then you have to dilute it to 0.02 whatever, it doesn't really matter, but the volume. But since it's 100 milliliter, it's best to just get this 100 milliliter. So CV equals CV. So 0.1, 0.02 times 100. Perfect. So this is 2, this is 0.1, so this you multiply it by 20. So this is 20 milliliters. And that's A. For B, identify the optimum wavelength. It's simple, you just find the one where it's minimum or maximum here. So this is 510, 510, so this is good. And then for C, they ask what the absorption of the unknown solution is 0.275. So you just go to this graph, go to 0.275 here, down, so 0.05, which is in the range, 0.5, sorry. After this should be 0.05, there's a typing mistake. And then Beer's law, this is basically just relating the absorption, molar absorptivity, path length, and concentration. So this is the jar, this is the light where it comes in, and this is it. So path length of curvette is this much, this from here to here. Molar absorptivity is the molar concentration, it's how much per mole does it absorb, and then C is concentration of the solution here, and then A stands for absorbance, which is this variable, and then E, where the unknown solution leaves fingerprints. If you leave fingerprints, that means less light will go through. If less light goes through, it means that the solution absorbed it more, in a sense. If it was perfect, if it was ideal, it means that it would have absorbed more, so the recorded absorption would be higher, which would make the concentration seem higher. So higher apparent absorption and higher reported concentration. So why is the method of determining COCl2 different than NaCl? Simple. NaCl is colorless, COCl2 is blue. So that way, since it's blue, it will reflect the light. It will reflect the light, and it doesn't go blue-red. Sorry, it actually just blocks this side and just gives out blue light. That's how light works. Okay, so for 24, they ask explain the photoelectron spectra. So at this energy level, there's the electron that is released, and this energy level there's an electron that's released. So 400, why is the nitrogen less than the oxygen? Because oxygen has a greater nuclear charge of 6, while nitrogen has 5. And that's why it attracts the electrons more, because this is more positive. So oxygen has more. And as for Ne, they have to explain what is happening here. So if you write the electron configuration, it's 1s2, 2s2, 2p6. Now the height of each peak represents how many electrons. So over here you have the p orbitals, which is 6. Here you have the s orbital, which is 2. Now they're grouped together because this is the second level. And then here you have the 1s, which is really far away because it requires a lot of energy, and it's a core electron, and you have to really take it away from the nuclear charge, which is really high right now. Okay, so for number 25, this is about ionization energies. Ionization energy is just the energy to remove an electron from an atom. So the first will be to remove from the atom, the second will be to remove from the 1+ ion. So that's what they showed over here. The first, as you can see over here, this is the second. Now the second ionization energy is always larger than the first, because you have the same nuclear charge, the same positive charge. So obviously if you have less electrons, and now you have more positive energy devoted to attracting the electrons, that's why it's greater. Now for sodium, you have this, and then you have the shell, this is the positive nucleus, and then you have just one electron. So once you remove this, you have to remove the electron from an already stable shell. That's why it takes a lot, 9 times more. While at 1.5 only, because since this is already higher, it's only 1.5 times to remove the second one, which is in the same level. So 1.5 is relative to the one you removed last, the second one. It's really big, but it's just relative. Now, why ionization energy of sodium is less than lithium is because sodium, it has a shell protecting it, and then lithium. So this one is sodium, and then lithium is only this much. So obviously, it's more protected from this positive nucleus. Now, why ionization energy of sodium is less than magnesium? It's because Na, and then you have the shell, and then you have this and this one here. So to remove the sodium electron, you have a specific charge. But if you had the same greater charge for the same shielding and you had another electron, it would be way less because it's the same shielding. So higher nuclear charge means it's easier to remove it. It's harder to remove it, sorry. So the sodium is less. Over here, aluminum less than magnesium. Aluminum has a p electron, 11 electron on the p orbital. So to remove this, it's easier. Easier as in takes less energy. Now, why is the ionization energy of oxygen less than that of nitrogen? It's because oxygen contains 2p4. So you have this. This is for nitrogen. But for oxygen, you have the spin electron, the other spin. So since it's the same p orbital, it's actually very stable if it's half filled. so it takes less energy to remove this P. Okay, number 26, it asks about size. So Na and Na plus just has an electron removed. So it's obviously smaller because it's less size. Cl and Cl minus, Cl has an electron added. So Cl minus is bigger. And for this, if you look at the periodic table, they all have 10 electrons, because if you account for the ions. So it just depends on the nucleus, how big of a charge it has. So the greatest charge, which is Al, it's going to be the smallest, because it will attract the electrons more closely together. And then Mg is the next, Na, then Ne, then F minus, then O2 minus, and then N3 minus, because less nuclear charge, N3 minus has less nuclear charge, so it will not attract it as much. And then for 27, you have Se and Se2 minus, and then you just write the electron configuration, its memorization, S2, S2, P, and then you have all these. So for the ion, which is 2 minus, you have to add 2 more. And then explain why the radius of Se2 minus is larger. Simply because you're adding electrons to this Se atom, so obviously this one will be larger because you're adding more. But if you want to get into technical terms, adding more will increase repulsion between the existing electrons and the valence. So that's why it will just push each other more, and it will increase the average distance between the valence electrons. So the electron cloud has greater radius. For part B, the Se2 minus is isoelectronic with the Kr atom, so it has the same number of electrons. But since Se2 minus is sort of artificial in a sense, because you're adding electrons not to a natural state, it will take less energy to remove the electron from this one rather than this one. So it takes less energy for the Se2 minus, and then requires less energy because the p orbital, and compared to this p orbital, if you compare it here, then it's artificial, as I said, and it's less attracted because the nuclear charge is smaller. And that's it. Thank you for watching. Okay, hey everyone, so today we'll do the chemistry revision sheet. That's what you came here for. So let's start off. The first question is 3 grams of ethane were burnt and heat capacity 25 kilojoules, and they say calculate heat combustion per mole of ethane. So obviously heat combustion per mole of ethane, so it gives you a general idea of energy per mole, so you can just work off that. So here you have joules, so that's energy, and then you have to multiply it with Celsius to get rid of this, so it becomes 25 kilojoules times 5 over number of moles. Now 3 grams of ethane, so mass over molar mass, so 3 divided by ethane is C2H6, so that's 30. So it ends up being 1250 kilojoules. Now it's exothermic, so there's a negative, and then you account for significant figures, and then you end up with this answer. Now, second question. 100 centimeter cubed of 1 molar HCl mixed with 100 centimeter cubes of 1 molar NaOH. So acid and base of equal concentration and equal H plus and OH minus. And the maximum temperature recorded was 26, so that's a 6-degree rise Celsius. And assume density 1 gram centimeter cubed for the solution and 4.2. So 6 degrees Celsius, you just do Q equals MC delta T, so MC delta T. So you multiply 1 gram per centimeter cubed times 200 times 4.2 times 6, and then you do end up with minus 50,400 joules per mole. no, what you get is the energy, and then you have to divide by whatever amount of water is formed. So it's 100 centimeter cubed of 1 molar for both of them. So 0.1 times 1, which ends up being this answer. Now for part B, NaCl is mixed with AgNO3, so they asked to find the temperature, not the temperature, the specific heat capacity. So you can just use Q equals mc delta T, because you have this value, and you have to combine it with AgCl. So the specific heat capacity of the solution is minus 418. So 418 times 1 gram per milliliter. How many milliliters? It's 400 milliliters, because 0.4 liters. And then that's M times C, 4.18, and then times T, the temperature change, so 1.5, all over the number of moles, which is, as you can see, AgCl, Cl, and they have, it's 1-to-1 ratio, and it's present in 1-to-1, so you can just use that. So 0.2 CV times 1, and then you end up with 12540. And keep in mind that since temperature increases, energy is released, so it's always negative if temperature increases. For question 2, part C, you have the exact same scenario, but this time you'll notice that the values have changed. So since the Cl and Ag react in a 1-to-1 ratio, you just pick the one that's smaller. So it's this. So you use this for your calculations. So now it's the exact same thing to find delta H. You do Q minus Q over M, which is equal to minus mc delta T, but since you have density, it's density times volume times C times delta T, over, this time you take the limiting reagent, so the number of moles, AgCl, so Ag and Cl, it's 1-to-1 ratio again, so 0.1 times 1, and then you answer the question and you end up with 18.8. So for number 3, a 20-gram piece of metal was dropped into a calorimeter. So obviously the metal will lose temperature to the water, and the water will gain temperature. So you have to sort of get the energies equal. So the water was stirred, and its highest temperature was recorded to be 27.5 and 25 degrees Celsius. So once it was stirred, then we know that their values are equal. Not their values are equal, sorry. That the value of the heat lost of the metal was equal to the heat gained by the water. So you just equate Q. So Q for the metal is mc delta T. So M is 20 grams times C, which you need to find out, and delta T is, it was at 62 degrees Celsius. The water was stirred and recorded to be 27.5. So the net change is 62 minus 27.5. So mc delta T of metal is equal to the Q gained by water. So again, mc delta T 40, mc 4.18, and delta T, which is 27.5, so 27.5 minus 25, which is 2.5, and you just solve this for C. So this is 20 into 62 minus 27.5. and then you just put in the calculator and solve it. You end up with 0.606. 4a, determine the standard enthalpy of formation. So standard enthalpy, it's a few conditions to know if it's that equation. All of the elements must be in its elementary state by itself. So like H over here, it's H2, F2 here. If it was Na, it would be Na alone. If it was carbon, it would be carbon alone, and maybe like salt, you put the state symbol, so like that. The second condition is that it has to be 1 mole of product, 1 mole of the substance produced or formed. So the standard is defined as the change in enthalpy for 1 mole of a compound from its elements in their standard state. So H2, F2, not just H atoms, which are very reactive. Gaseous hydrogen and fluorine. So we have here, that's the formula, because H2 and F2 are the elementary states, and then 1 mole, and then you just balance it. And with an enthalpy change of minus 540 kilojoules. So you need 1 mole, this is 2 moles, so you just divide by 2, and you get minus 270. Divide by 2 equals to minus 270. Now Hess's law, it's basically just sort of math, I guess. So you need this equation. So let's just work with the reactants first. So Fe2O3, we need 2 of that, but in the other side. So it's 2 times 820. So the negative becomes positive because you flipped it to the other side. Then you need 3C. So this one stays the same, but 3 times. So plus 3 times minus 390. Then you just make sure that every product is sort of cancelled out. So here it's flipped, and you need 2 of this, so 3O2 on the N side. This is very messy right now, but 3O2 on the products because it's flipped, and 3O2 times 3 on the reactants, so they cancel out. And then CO2 is the same for 3O2, and then it's 2Fe times 2, so 4Fe. It's flipped, remember. So it ends up in being in the products. So when you do the math on the calculator, you get this. Same for here. Decomposition of B2H6 into its elements. So decomposition is B2H6, this is balanced, into 2B plus 3H2. This is basically just making it elements. So B, boron, is a metal, so it will be alone. Hydrogen is a gas, diatomic gas, so it will have 2 atoms which will be split from the 6. Will be paired together. So again, B2H6 split into 2B plus 3H2. So you start off with B2H6, so it's just one of that, so it's minus 2100, and then you have next H2 but on the other side, so you need 1 of that and 3 of that, but on the other side, so it's minus 3, so plus minus 3 times minus 250. And then you need boron. I'm going in order from up to down. You don't have to. You can just go along the list. So boron, you need it on the product side, and it seems to be already matched with 2. So you just multiply by minus 1. So minus 1 into minus 1250. And then you solve it in the calculator, you'll get the answer. But just to make sure, you should always try to make sure that the products align with the reactants. So minus 3 is 3 over 2 on the product side, 302, and this is 1, so 302 is here, and then minus 1 here is 3O2, so this adds with the 3O2 and becomes 3. No, these cancel. And then 3H2O with 3H2O, they cancel, and B2O3, B2O3, it's just 1. So
Guys, let's do part number 5, part C. We have 3 reactions. I'm not going to read them out, you can read them. And we have 3 delta H's for each reaction. We need to use the above equations to calculate delta H for the following equation. FeO solid plus CO gas to give Fe solid plus CO2 gas. Now this is Hess's law. I'll give you guys a few seconds. You can solve and then we'll check together. Okay, let's check it together. First, to make our lives easier, let's call this reaction 1, reaction 2, reaction 3. So, whenever I'm just going to be jumping around between reactions, you guys can keep a track. Okay. Now, this question is a very tricky question, and the way they explain the sheet is correct, but it's a bit misleading. So, let's just see how it works. What we should see here are the ratios. The ratio between FeO and Fe are 1 to 1. So we need a number that the ratio is 1 to 1. But here we have 3 FeO and 2 Fe. What should be done? Well, you should multiply each number by the other number to get a common factor or a common multiple, sorry. So what we should do is, since Fe is required on the right side, all you have to do is multiply this by 3. And since FeO is required on the left side, we flip. So let me just write flip. Then multiply by 2. So now I'm working on reaction 3. Okay, reaction 3. Flip, multiply by 2. I have flipped, so 6 FeO. I'm not going to write the states because it's going to take a long time. Plus 2 CO2 to give 2 Fe3O4 plus 2 CO. And when I multiply the second reaction by 3, I should get 3 Fe2O3 plus 9 CO to give, let's see, 6 Fe plus 9 CO2, right? So now we've got 2 reactions out of 3 sorted. All you have to do is work on number 1. Now what should we do on number 1? Let's think about the other reactants, sorry. Now we have, let's see, Fe2O3 and Fe3O4. These 2 are not needed in a reaction. We have to find a way to cancel. Well, we have 3 Fe2O3 on the left side of the first reaction, and we have 2 Fe3O4 on the right side, both of which are corresponding. So what we need to do is just flip reaction 1. So we are able to cancel everything. So when we flip, we should get, let's see, 2 Fe3O4 plus CO2 to give CO plus 3 Fe2O3. Once we have, let's check now quickly. Okay, 2 Fe3O4, 2 Fe3O4 are cancelable. 3 Fe2O3, 3 Fe2O3 are cancelable. 6 FeO, 6 Fe right side. 2 CO2, okay, we have CO2 here, okay, it works. Now let's find out the delta H's for each of them. Let's start with this, delta H number 3. What did we do? We flipped and then multiplied by 2. So minus 2 times this, right? Now let's work on delta H2. All we did was multiply by 3, so it's 3 times negative 22.78. And delta H1, let's work on that. All we did was flip, so it's 50.20. Now we have to add this huge number of equations. We immediately cancel. This is cancelable with this. We have 6 FeO plus. We have 2 CO2 plus 1 CO2 is 3. 3 and 9 on the other side, so 6 will be gone. So these 2 are cancelled. 9 CO, 2 CO and CO. 9 minus 3 is 6, so 6 CO, we got rid of these to give 6 Fe comes down plus, if we remember, oh wait, Fe is also gone. We had 2 plus 1, 3 minus 9, so that's 6 CO2. Now we finally move on. Let's just quickly write a quick summary of what we had. 6 FeO solid plus 6 CO gas, let's go back to the states, plus 6 Fe solid, to give 6 Fe solid plus 6 CO2 gas. Now if we quickly go back to the given question, this is exactly what they required, but they want ratio 1 to 1. And let's just quickly write the delta H. Let's call this reaction 4, which is equal to, if we add them all up, minus 65.04 kilojoules. Now when they want ratio 1 to 1 and every single number is the same, we just divide by 6. So dividing by 6, we should get FeO solid plus CO gas to give Fe solid and CO2 gas, and our delta H4 was this, so all I have to do is divide by 4, so it's minus 6 by 6, giving us minus 10.84 kilojoules. And that's how you solve number 5, part C.
Okay, so for number 6, you have to find delta H, and you're given sort of delta H of formation. So formation means if they're formed, you use that energy, but if they're broken down, then you just reverse the sign. So O2 is an element, it's in the elemental state, elementary state, so you don't need to worry about it because it's 0, the formation is 0. But C3H8, you have to break it down, so that's why for this it's the opposite, it's not minus, it's positive. And then CO2 is produced, so, and the coefficient is 3, so multiplied by 3, so 3 minus 390 plus H2 is 4, and it's produced, so it's formed, so just plus 4 times this, and then plus 1 times minus 1 into minus, well, let me make that clear, minus 1 into minus 100, and you simplify it, and you get this. Number 7. Consider a calorimeter of heat capacity with when... Okay, part 7. You're asked to find delta H in kilojoules per mole. So the obvious answer is, since it's kilojoules per mole, so energy per mole, so minus Q over M, and then equal, so Q is heat capacity times increase, 5.7, 11.3, you end up with kilojoules, so you don't have to worry about that, times 5.7 over N, so it's 3 milliliters density like that, and then with C2H4. So N is mass over molar mass, and then mass is density times volume, so 3 times 0.789 over the molar mass, which is 28, because C2H, it's not 28, the 28 is for C2H4, but C2H5OH is what we have to calculate. I think that's a mistake over there. Yeah, that's a mistake. So C2H5OH, it's 46. So C2H5OH, and you just simplify that, and you'll get the answer. Okay, so for number 8, we're asked about ionization energy as we move across a period. So you have the nucleus with increasing positive charge as you go from left to right, and you have the same number of electrons, core electrons. So let's say for the first group, you have one electron there, one electron. This positive energy is going to reach it from this side, and then this positive energy doesn't reach it. But let's say you have the second nucleus of this is group 1 and this is group 2. So here you have the nucleus, and you have the core electrons, and you have these valence electrons. So as you can notice, you have a higher positive charge but the same level of shielding, so it will attract the electrons more closer, and it will attract it more strongly. Therefore, it's harder to remove them, and ionization energy increases as you move across the group, period. And as we move down across the group, the shielding increases. So here, the first group, first period, and you have, let's say, one shielding, and then second period, you have two shielding, and then the valence, and then third period. So as you can see, the electrons get further and further away from the nucleus, and therefore it's less strongly bonded, so it takes less energy, so less ionization energy is required. And arrange the following in terms of ionization energy for size. Nitrogen has the highest because, and phosphorus has, I'll explain later, and then Si and Al. So as we said, ionization energy increases as you go across the period, and this is group 3 of the same period, this is group 4, this is group 5, and this is also group 5. So these are the same period, so obviously it makes sense why the increase in ionization energy. And then as we said, across group, as we go down, then ionization energy decreases. But nitrogen is a step up, it's the second period, while this is the third period. So this one, it's closer to the electrons for the same number of valence shell. Yeah, for the same number of valence electrons. So this has a higher ionization energy, and that's why it goes like this. So here, same period. Here, same group, but different period. So this takes a higher energy state. Energies. Okay, so number 9. Write an equation to illustrate the first and second ionization energy of sodium. So first ionization energy, you're removing one electron from the gaseous state. So that's exactly what happens here. Second ionization energy, you're removing another electron from the first ion that was formed from the first ionization energy. So here you have it. So Na plus in the gaseous state, we will lose an electron to give 2 plus Na2 plus electron, I will lose one. And why is the second greater? Easy, because the nucleus, it has the same level of positive charge, and there's less electrons this time, so it will be strongly attracted. So that's why, since it's more stronger, because there's less, let's say, recipients of the charge, then the ionization energy will be greater. The second ionization energy is around 9 times. Why? Because as you can see, this is a Na nucleus, and then you have 2 core here, and then there's 8 valence electrons, not valence, sorry, other core in the next shell, and then you have 1. So once you remove this, since it's just like a lone pair, not lone pair, lone standing, like alone, and it's further away in the last shell, which is less energy level, which has a lower energy level, the first ionization energy is smaller. Next, you'll have to remove one of these, which is in a greater energy level, which is closer to the nucleus, so it's around 9 times greater, so that's why. Why is the energy of sodium ionization less than lithium? Because sodium has a whole other shell of electrons. So sodium has this, and then 1. But lithium only has this and then 1. The size, they're not scaled, the sizes, but as you can see, there's 1, 2, and 1 only. This is the actual nucleus. The last one is the nucleus. So 1 here, of 1 shell between the valence and the nucleus. Here you have 2 shells. So that's why lithium is strongly bonding this electron. It has a higher bond. So it takes more energy to remove this. Why is ionization energy of sodium less than that magnesium? Same shielding, Mg has higher nuclear charge, so it's pretty obvious. And why is the ionization energy of aluminum? It has to do with p orbitals, because as aluminum, like when the extra electron from the magnesium, where it would have gone, is in the p orbital. So this extra p orbital is actually easier than removing from a complete s orbital. So that's why Al is less than magnesium, because Al has the p orbital. Al's electrons, the first ionization energy, is coming from the p orbital. Why is the ionization energy of oxygen less than that of nitrogen? Because again, like in this case, N has a complete, as a half p orbital, but O has a half p orbital plus one more. So since this sort of stops it from being either perfectly half or perfectly full, O has less, because it deals with completing the p orbital from when it was sort of stable in this, not stable but like relatively stable compared to oxygen. So it tends to have a lower ionization energy because of this extra. So visually you could have seen it here, not in the atom but in a table. So this is the N for p orbital, but O has this extra one. So instead of like a uniform distribution, here you have extra electrons, so it is easier to remove it than nitrogen. And number 10, arrange the following in increasing size: Na, Na plus lost an electron, so Na is bigger. Cl minus gained an electron, so Cl minus is bigger. And here, all of them have the same number of electrons, which is 10. So it depends on the positive charge, or how much the nucleus is willing to attract the 10 electrons. So obviously, greatest positive charge will attract it a lot, which means the radius will be smaller, and the size itself will be smaller. So Al is most positive, then Mg, then Na, then neon, then F minus, then O2 minus, then N minus. As you can see, it's decreasing in charge number. So 3, then 2, then 1, then 0, then minus 1, then minus 2, then minus 3. And F minus, Cl minus, O2 minus, Sr2 plus. So first thing you look at is the actual core electrons. So Br and K krypton and rubidium, strontium, same period, and F minus, O2 minus, same period. So second period, third period, and these are larger periods. So F minus will go first because it attracts it larger from F minus and O2. Same period, of course. So F minus, so greater nuclear charge, less size. O2, then O2 minus, they forgot the O2 over there. So O2 minus, then the same period but less nuclear charge, so it will attract the electrons less, and it will be more free to go outside and make the size of the atom bigger. Then Cl minus, because it's the third period, and the rest are 4 or 5. No, the rest are all of them are 4. So Cl minus, and then here it's just decreasing charge. So 2 plus, and then 1 plus, and then 0, and then 1 minus. So less nuclear charge is what gives it these charges. So as it goes here, it's less. So size will be bigger due to less attraction. Okay, so for number 11, you're asked about electron species. electron configuration. And here what we have in front of us is the electron configuration, and to find out how much or what order it is in, you just draw arrows. So here you draw the list, and it goes like that. Okay, so you just keep on going in this direction from left to right of arrows until you've met your electron number. So that would be like 2, 4, and then 10, sorry, and then 12, and then 18, and then 20, and then 30, and then 36, 38, and so on. So that's what you do. And then for A, SE and SE2 minus, you just do that thing, and you look in the periodic table for the amount of protons, atomic number, and then since SE is neutral atom, you just copy that. And then SE2 minus, you just add 2 more electrons. The radius of SE2 minus ion is larger than SE atom because you're adding 2 more electrons, so it additionally becomes bigger, and the positive charge is more, spread out throughout all the electrons, so it's more loose in a sense. So the extra repulsion between the, electrons pushes them away and increases size. Se2 minus ion is isoelectronic, easier to remove electron. Well, that depends on the charge and the electrons and how they interact. So both electrons are from the p orbitals, and because they're all in the same orbitals, because they're isoelectronic, and they're none of the exceptions, and it requires less energy to remove 4p orbital from a selenide ion, simply because it's not its natural state. Se2 minus is an ion where you had to give energy to make it to make the electron free, or to make the electron go to a higher energy level. So this energy spent obviously increases for every electron you remove. So it is no doubt that Kr Se2 minus is easier to remove an electron, and Kr is a neutral atom, and it's noble gas, and therefore it's very stable. So Se2 minus is easier to remove, and it's less attracted to the nucleus because there's more electrons than protons. Number 12, successive ionization energy. This one's very easy. You just check for the biggest jump, and this is around maybe 2 times, and 2 times, and 2 times, and then 2 times, and then here it's around 5 times jump. So you can tell that it's it's group 5 because 5 valence electrons. And since it's 5 valence electrons, it can form covalent bonds, or it can form ionic bonds with 3. So like group 5, 6, 7, 8. This one's 0, and this one's -1, -2, and -3. So it would form chloride, so YCl3. But there's also a special case where the electrons, you know how it's 5 electrons? Yeah, each of them bonds to a Cl, as we saw in the shapes of chemistry, in which Ali will explain later. So it's YCl3 and YCl5. Yeah, that's the answer. And then number 13, first ionization energy, Al, is less than that of B, because more shielding, because Al is here with core electrons, and then another core electron, then 3 valence. B has 1 and then 3. So less shielding, more closer to the nucleus, and therefore more ionization energy. Ionization energy of F is greater than that of O, because here you have F, O. F has a greater positive charge, and the same shielding is experienced So even if this has 7 and this has 6, right? It's same shielding, so whichever one has the greater positive charge will attract the electrons more. So therefore F is having a greater first ionization energy. Atomic radius of Ca is larger than that because there are more valence electrons in the higher shell. So like 1, 2, 3, or NMG has only 1 and 2 and 2 valence, and this one has 2 valence as well. So more shielding. So atomic radius is greater, but the ionization energy is less because it's further away. Second ionization energy is greater than first because obviously the nucleus has a positive charge, so once you remove an electron, it will have a net positive charge, so to remove another electron again from the already positive charge, it's very difficult, and difficult as in it takes a lot of energy. And the atomic radius of Cl is smaller than that of S because Cl has a larger nuclear charge. So it's the same group, Cl, S, same shielding, and this one has 6 and this one has 7. So as you can see, the shielding is the same, but therefore it depends on the nuclear charge. So Cl has a greater nuclear charge and it attracts it closer. So this is closer, and as it attracts it closer, the size is smaller, so therefore Cl has a smaller size due to its larger nuclear charge. And then number 14, predict the formulae, Mg and N. Mg forms 2+, and N forms 3-, you just switch them, so Mg 3, N2. Al, it forms 3+, you look at their groups, and then -2, and then you just switch and switch, so Al2, O3. Li has 1+ ion, and O is 2-, you just put the numbers like that, so Li2O. And then Ca forms 2+ ions, and F forms 1-. So therefore you put 1 down, 2 down, so CaF2. Ca1F2. So you don't put the 1. That's basically what's happening here.
So number 15a, how do the size and charge on ions generally affect the value of the lattice energy? Lattice energy by definition is the formation of one ionic solid from its gaseous ions. Because you're forming bonds, you're releasing energy. When you break bonds, you need energy, so you supply this energy. But here you're forming bonds, so then again you are releasing energy. Releasing energy means exothermic, so that's why you can compare the exothermic levels, one being higher than the other. So that's why when you say most exothermic lattice energy, you're referring to the one with the highest lattice energy. So let's take examples of what makes what are the factors. The factors are size and charge. You can use Coulomb's law to make the bridge between the lattice energy and the charge and the sizes. So Coulomb's law says that the electric force is directly proportional to the product of the charges and inversely proportional to the distance between them. So in this case, the greater the charge, the stronger the force. So therefore, the stronger the bonds, so the more energy released when you form them, because you need more energy to break them. So that same energy in reverse, you'll be getting more energy to form them, because it's like give and take. So even if you need more energy to break, it just means that you need more energy, that you're gonna get more energy when you form. So yeah, so if the distance, let's say, decreases, again the force increases. So your highest force is the ones with the greatest charge and the smallest distance between them. And because the distance relies on the size of the ion itself, so the smaller the ion, the stronger the bond, the stronger the force, so therefore the more exothermic the lattice energy is. So let's immediately hop into the questions here. So LiF and Kf. In here you have the same anion, so you don't look at that. You look at the cation, Li and K. They're both plus, so now you look at the sizes. Usually start with the charge. The charge is usually your easiest answer, or the easiest way out. So because the charges now are equivalent, we just look at the size, which is the final factor. Li is much smaller than potassium ion, so therefore immediately LiF is more exothermic. Now NaCl and NaI, again in this case cations are the same, so anions are what you should be looking for. Cl is smaller than the I, so immediately NaCl is more exothermic. MgO and Na2O, again same anion, so you look at Mg and Na. Here it's Mg2 plus, here it's Na plus, so immediately your charge saved you some time by immediately saying this is, you know, greater charge, so greater lattice energy, more exothermic lattice energy, so that's your answer, more exothermic lattice energy than the Na2O. So CaO and CaOH2, same cation, you look at O and OH minus, this is O2 minus, this is OH minus. Even if you have two, you're still talking about, like, you're comparing them individually. So that's why, then again, the CaO is more exothermic than the other one. So in number 16, we are using the Born-Haber cycle to calculate the lattice energy of NaF, and we're given some reaction energies over here. So let's start. The easiest way to start is to start with the solid itself. We can, to be honest, you can start from anywhere, but I highly advise you start from this step. You have two reactions that produce this species over here, the solid. The first one having the energy called lattice energy, and the second one having its energy called standard enthalpy of formation, or the enthalpy of formation, so delta H F. The first one is forming the ionic solid from its gaseous ions, so that will be Na plus gas plus F minus gas. This one is forming the ionic solid from its, or like 1 mole of that solid from its elements in their standard state. I was recalling it from memory, that's why I paused. So here you have F, and this is by nature diatomic because from their elements, and this is gas, again by nature. These are all reactions, by the way, so they are reactions with their energies. So, and every reaction must be balanced, so this is why you put half. So let's keep on going. So we're supposed to reach this, but we're gonna do it in a series of steps. So let's continue, step at a time. Let's start with the Na. We cannot ionize immediately to reach this, so we have to change into gas. So what we want is Na gas plus F2, keep everything the same when you change something. When you change a single factor, you keep everything the same. Okay, so solid to gas, that's atomization, also called sublimation. So delta H atomization, or however you want to represent it, also sublimation, same thing. And then you go, now we can ionize immediately. Na plus gas plus half F2 gas. This is called the first ionization energy of sodium. And then we keep on going. This time we're done with the sodium. If you look carefully, we have Na plus gas, Na plus gas. We cannot do anything to the sodium because that's how we want it to be. So we want to reach from half F2 to F minus. So for the F2, which is F bonded to an F, we want to reach F and an F, which make a 2F. So to do that, we have to break the bond, and this is called the dissociation, or the bond dissociation energy. And that's defined by nature to be the breaking of 1 mole of bonds. However, do we have 1 mole? No, we have half. So this is not dE. This is dE over 2. But let's write. So it will be giving us by nature 2F, right? But we already have a half. But let me write it. It's fine. Let me write it. Let me write the entire thing. Na plus gas. This is what I meant. Look, you will be having half times 2F gaseous, and then of course half with 2. So that's what I meant earlier. So you can immediately just write F gas. And then from this step to this step, Na plus gas, same thing. Here you're changing from the fluorine gas into a fluoride ion in the gaseous state. In this case, you are giving an electron, so this is not ionization energy, this is electron affinity. So there you have it. We are done with the ionization. We're done with the Born-Haber cycle in this part. Now all you have to do is just add the energies. So you pick a direction. You pick for example, this clockwise, and start from somewhere. To be honest, start from this, safest and the best. But to be honest, you can start from anywhere. And then again, it's just conventions. The conventions are there to make your life easier. So let's continue. So we go from here all the way there. So delta HF is on the other direction. So you have to do minus. So minus delta HF. Atomization is with it. So plus delta H atomization. I'm just gonna say it atom. And also keep in mind the balancing. If you have something like Mg2 plus, you have to be aware that you have to do the ionization energy again, and there are some stuff that you might end up needing to balance, especially when you have, let's say, MgF2 for example. You have an F2 over here, things have changed slightly, and you might have to do certain stuff more than once. So yeah, so again, atomization and energy, ionization energy, same direction, i.e. first one, plus, from memory I think, yeah, plus, yeah, it's plus, and it's dE over 2. I'm writing quickly, not to waste time, and then EA, electron affinity, with the direction of the arrow we have over here, and then finally the lattice energy, again with our direction. All of this is equal to 0 because you're starting from a point and you're ending at it. So of course the sum of the energies should be 0. So we have finally this equation. So you basically just sort and you calculate. If you want me to do that, let me do that quickly. So we want the lattice energy. So everything will be taken on the other side. To do that, you just negate this, negate this, negate this. By the way, I'm doing LE equals minus. Actually, let me do it with you. It will be delta HF minus delta H atomization minus IE1 minus TE over 2 minus EA, and we are done because we just took LE to the other side. Pretty much. So let's just calculate. So we're given the values. So let's just put the numbers. HF, that's minus 570. Also, you have minuses sometimes from the energies, and you of course have the minus from the formulas. So just keep that in mind. So if you ever see a minus, you might end up with a minus minus. So just type that correctly in the calculator. So minus 570 minus the atomization, where is it? Yeah, 109 minus lattice energy. The ionization energy 495 minus D over 2, 154 over 2, and finally minus the electron affinity, which is already minus, so I'm gonna write plus 328. We get negative or minus 923 kilojoules per mole, because after all we're subtracting, so it will take the same unit, and we're done pretty much. If you have ever found some difficulties in either recalling or coming up with an answer to the question, are broken bonds exo or endo, are formed bonds endo or exo, and is delta H with respect to broken and formed bonds, is it broken minus formed or formed minus broken? If you ever find difficulty in remembering it, like for example on the spot, because every time you need to be reminded of it, then this should in some way help you. Even if it doesn't help you remember, it will help you to reform or recreate the formulas and the answers in your head, so you'll be able to answer yourself without the need of memorizing it, if you still recall the analogy at least in your head. So we have here broken bonds. Logically, when you have a bond over here and you want to break it, you're going to have to apply some force on it. Imagine, let's say you have a door. To break a door, you're going to use so much force just to break it, and this force of course comes with energy. The same thing, to break a bond you need heat in this case, and this is supplied energy. When you're supplying energy, it's endo, which is by definition positive, and we're doing this, we're breaking the CLs. And if you want to do the opposite, which is again by default should be negative, this is the formation of the bonds. You're forming bonds, and we just wrote, because it's the opposite of this, it should be the opposite in sign also. So if this is positive, then this is negative. So even if you don't see the connection between forming bonds and releasing energy, at least you can see it as the negation or the opposite of breaking a bond, which logically should connect with supplying energy, which means endothermic. So this way, if you forget one, you can get the other. Usually this will be your reference, because then again, if you're unable to see why forming bonds releases energy, you should be able to see why breaking bonds, like energy is needed to break bonds. So we're done with this, so we can prove this, delta H itself. So we said this is endo. Breaking a bond means supplying energy, so endo. Endo is by nature positive. Forming a bond, however, we said it's opposite, so negative. And this is actually where the minus comes from. It's actually originally the summation, and then the summation itself has a minus. A plus minus is what is minus, and this is why you have a minus. So this way, we just proved how you can get the delta H, and individually, if you were asked which one is endo, which one is exo, or like, individually, then you know what to say, you know what to do. So let's now get away from the formula. We have it in mind. Even if we forget, we can remake the formula again. So what was delta H? We said breaking a bond means you supply energy, so it should be kept the same. So I'm gonna say bonds broken minus bonds formed. Okay, so for this one, the broken ones are the reactants here, because you're gonna break this and that and that and that to form these. So it will be N triple bond N, the energy of that, plus the energy of, there are 3 HH bonds, so you have to break 3 HH bonds. Of course, make sure it's balanced, and here it's balanced. It will be easier if you can't see the balancing here, you can balance from here, and these would be the same technically, so you can just immediately do it, or like faster. And here you have 3, and here you have 3, so you have 6 of the NH bonds. So basically this is the bonds broken, these are the bonds formed, so you subtract the energies of these two, so this is minus that. So let's put the numbers immediately. This is 9, 4, 1 plus 3 and 2, 4, 3, 2, which is over here, and then minus 6 and 2 NH, which is 3, 9, 1, and you get 9, 4, 1. Let me just put that, 9, 4, 1 plus 3 into 4, 3, 2 minus 6 into 9, 3, 9, 1. You get minus 109. Minus 109 kilojoules, pretty much kilojoules. So we're done. So this one, the easiest way to do it is, like immediately using your memory. O, H, H, 2 electrons, and then done. This is bent V shape, angular, the name of the structure, and then you have ammonia, which is like this, and then you have a pair of electrons. If you want to double check, you can do this. Nitrogen has 5 electrons, it's sharing 1 with each hydrogen, it's left with a lone pair, pretty much. This is called triangular pyramidal, and if you want to show the wedges, you can go like this, like that. You can pick any, you can pick even the ones where you go like this, what anyways. Yeah. CCl4, carbon has 4 electrons, sharing 1 with each chlorine, but again from memory you can just go like this, boom, like that, and you're done. Of course you're left with the electrons here, just like this. if you count, you should have the correct number of electrons. And if you want to put the wedges, it has 4 atoms, and from the way it is, you have again horrible but anyways, it's square pyramidal. Let's keep going. And then you have N triple bonded to another N, you have a lone pair of electrons, you're done. Oxygen double bonded to another oxygen, and you have the electrons here. Now if you want to double check and you forgot how to, just basically count the number of electrons. If you have an N2, you basically have a 7, or 2 times 7, because each nitrogen has 7 electrons. Sorry, my bad, 5, I mean 5, my bad. So 2 times 5, you'll end up with 10 electrons. So that will be, if you're doing it step by step, if you put the full set, the octet rule, basically you're satisfying the octet rule, and you count, you have 6, so that's 12 plus 2, that's 14. You want to bring it down 4 electrons down. Adding a single bond takes away 2 electrons by calculation, because you're taking 2 from each side, so you have a net decrease of 2 electrons. So you can just immediately add another third bond if you know your math. So you can immediately go like this and take out those 2, take out those 2, take out those 2, and take out those 2. It's fine if you don't understand this, you can just immediately go like nitrogen, 14 electrons we said, right? 14. So again, I'm just drawing the arrow to show you, it's not some reaction arrow, it's just me writing. Let me do this. Okay, and then you have a double bond, and you're removing 2 electrons. Let's remove these, for example. And then you go again, triple bond. You'll have to do this pretty much. And yeah, that's pretty much how to do the nitrogen. Same thing with the other ones, same thing, calculate, and pretty much you can do everything. This is linear, and this is linear, and yeah, pretty much. For this one, usually it comes with practice. You know which ones are right, which ones are not. And there are, by the way, there are other ways to know. For example, when you have NO plus, you can do the calculation and you can do the thing, and it will not take you time, but you can do this. N2 is very, very, very close to this. The only thing you have is you have an oxygen which has 1 more electron than another nitrogen, because if you have 2 nitrogens, each one having 5, so that's 10. But if you have an oxygen which has 1 more electron, you'll end up with 11. But you also have a plus 1 over here, so it will be minus 1 electron because you're taking it away, so you have 10 again. So these should have the same structure as the nitrogen triple bond nitrogen. So they should look something like this. See? Of course you have to do this and then plus, and you're pretty much done. You can do the rest same way. The CN, one special way to do it is, I guess, not really sure about I mean, you can do it, yeah, NN again, NN, and C has 1 less electron. Yeah, 1 less electron, but you have a minus, so you're adding that electron, so you're back to square 1, like this. So yeah, pretty much. And then you can just keep doing the rest. But here, you can remember it like this. Boron species have, or like are electron deficient. So immediately this is not following the octet rule. Electron deficient means when you do this, they're gonna look like this. Like the boron will not need to have the octet rule satisfied for it. It will be the one that says it's fine, I don't need. It will be the ones that will kind of like give the compromise. It won't like complain about this not having the electrons. It's electron deficient, so it's fine. It's fine with just feeling 6 around it. For the other exceptions, you'll have ones like this and this. These two are because they can extend their valence shell, so they will have like this. The PCl5 will have something like this. Cl, 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 Cl. Let me draw it a bit bent, just because it looks nicer and probably more correct. Like this. And you just, it will take time, but like you just go like this. if you once you're done with this, and you can double check with the calculation, phosphorus having 5 electrons. By the way, I might say something wrong because okay, let me just do this. Okay, so 5 electrons, and each Cl, so that's 5 times 7 plus 5, so that gives you 35 plus 5, that gives you 40 electrons. You have 6 on each chlorine, so that's 6 times 5, you have 30, and you have 5 bonds, each one having 2 electrons, sorry. So you have 2 times 5, so you'll have 40. You're pretty much done. But here you have the anomaly, which is first of all, phosphorus is making 5 bonds, so that makes 10 electrons. So therefore you just have an exception, extending its valence shell. Phosphorus compounds can do these, sulfur compounds can do these, and the I3 minus, if you do the same thing, you notice that there's something off with it. If you do it normally, like this, for example, like this, and count, each I is I minus, so you have group 7, so 7 electrons times 3, that gives 21. You add one more because it's an ion over here, it's an anion, so you have 22, or negatively charged, 22. So 22 electrons. Let's calculate this manually. You have 6, so that's 12. Actually, an easier way to calculate would just be like 8 plus 4. So 8 times 2, which is 16, plus 4, that gives you 20. So 20 electrons. So basically you have 22, but you're using 20, so you just add another set of 2 electrons. Then again, look what you have. You have 3 lone pairs, and you have 2 bonds. So that makes 10 electrons around the I atom. Whoops. 10 electrons around the I atom. Then again, another exception, and you can keep going with the rest in the same way. So the ones that would be the exception would be not these, the boron compound, and you have the SF6, PCl5, I3 minus. The xenon will have a normal structure with the lone pairs normally. Let's check the ICl4. I'm expecting it, I'm positively expecting that it again doesn't follow the rule because we have I. So let's see how we're gonna do this. For me, by default, I'm gonna start with this immediately because I know that the structure is going to be correct in the end. So you have I, which is 7, plus again Cl, which is again 7, so 5 times 7 plus 1, you have 36, because this one has 7 electrons and each of those have 7, so you have 5 times 7, and you have minus, so plus 1, you get 36 electrons. If you fill the octet rule, which is going to take me time to draw everything, but if you do it on your own, you'll end up with 6 on each chlorine, which I'm done with right now. 6 on each chlorine, so that's 6 times what? 6 times 4, plus there are 4 bonds, so that's plus 8 electrons. You have 32. So how can you go 4 electrons? It's basically asking you to do this. Add a pair and another, and you're done. There you go. 2 lone pairs, 4 bonds, another exception. So that's it pretty much. So the rules in general are boron compounds being electron deficient, the the sulfur compounds and the phosphorus compounds that could form or that could extend their valence shell. Also, always draw the Lewis structure before, like if you're unsure of these, you can confirm, because sometimes you can have the compounds being normal, like with the actual proper amounts. Depends on what kind of combination you have. And then the I3 again could extend their valence shell, as we have seen in this example and this example. And yeah, pretty much. So for the resonance structures, you just do them normally, like like you do the Lewis structure normally, and then you do something special towards the end. So normally 5 plus 3 into 6 electrons plus 1, giving you 24 electrons. So you draw it like this, and O and O. If you put the electrons, you're gonna end up with 26. If if you want to double check, let's double check together. So you have 6 around each oxygen, so that's 6 times 3, because there are 3 of them, so 3 and times 6 because each one has 6, and this is having 8, so plus 8, that you will get 26. 26 is 2 electrons higher or greater than 24, meaning that I have to reduce by 2, meaning forming a double bond. So in this case you can form a double bond here and erase those 2 electrons and erase those 2 electrons, and you're done with NO3 minus 1 structure of it. Because you have a double bond, there's the possibility of forming a double bond here, and there's the possibility of forming the double bond also there. So you'll end up with another structure, again same thing, except that you have the double bond here and the O's like this. And minus, and again a third structure, same thing, but like this time with the double bond being here. And these of course would resonate to give us a more accurate structure, or like we represent it like this: O, O, and O. This is basically saying I have somewhat a single bond and a double bond, but to be accurate it's not a 1.5 because this bond is resonating 3 times, and resonating 3 times means it's 1/3 stronger than a single bond. So this is 1.3 stronger than a single bond, because you have it resonating here, resonating there and there, like the electrons are just like this basically. So yeah, pretty much. For the rest, same way, NO2 minus, you're gonna end up with N and then O and another O. You pick the double bond here, for example, you end up with this, and it's minus, right? NO2 minus. So you'll have it like this, and then of course the resonating structure would have the double bond on the other side like this, and like that, and we're done pretty much. The rest follow the same manner. CO3 2 minus, again you calculate, you put the electrons, you know, satisfy the octet rule, and then double check, recount, and then do the necessary formations or changes or amendments. You're probably gonna do just a double bond here, and you're gonna pretty much notice that you have 3 atoms, so 3 possible resonating structures. SO2, same thing as NO2 minus. You're gonna have a double bond on one of the O's, another structure is on the other O. Same concept, same way. If you know one of them, you know the rest. So for number 21, we're using this one theory called the VS-EPR theory, which stands for the valence shell electron pair repulsion. And this is basically having the repulsions between the lone pair, shared pair of electrons or electron domains being stronger than the shared pair and shared pair repulsions. So here I've drawn a small tiny diagram of the molecule of a water molecule. If you were to imagine this repulsive force between this lone pair and this shared pair, this is like, if you consider, let's say, both lone pairs, so these repulsive forces are going to be stronger than these repulsive forces between the shared pairs themselves. Because they're stronger, you're gonna end up pushing them until they're so close to each other, or they are not so close, actually at a distance from each other, that the forces basically balance out, and you have a smaller angle, a new one that's stable but a smaller one, which will end up being 104.5, the actual angle of water in this case. This is due to something that the VS-EPR is built on, which is the lone pair, shared pair electron repulsions being greater than shared pair. thus you're overriding the shared pair repulsion effect. You're overriding it because you're winning over it. So you're pushing the electrons until you reach, of course, a stronger force, and then they reach equilibrium. So the classification of this is AX2E2. We're expecting an AX. Well, the expected shape is the AX4, which is the tetrahedral with a bond angle of 109.5. But instead, we're getting, of course, an AX2E2 because of, or due to the VSEPR, or at least the VSEPR could, like, it can explain it, and it says that you, or like as a result, you'll have a smaller bond angle. So if you were to consider, let's say, here without the lone pairs, but of course to correct this I'm not going to have a specific one just to be accurate. Yeah, A, X, 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 X. You're going to have a tetrahedral of bond angle 109.5, but of course in water we have 109.5. If I said 4, sorry. And here you're going to have instead 104.5 because of the repulsions, from here. So if we consider the PCl5, which we have over here, one quick way to do it is basically phosphorus having 5 electrons, right? And chlorine having 7. They only need 1. Phosphorus has 5, and there are 5 Cls, and each Cl wants 1. So you give it, or you share basically 1, not give. You share 1, and that pretty much gives you the shape. No other modifications to it. No adding, no subtracting, no nothing. And we're done with this. So you could do this and apply this way to the other ones. For example, let's jump to xenon. Xenon, let's do xenon over here. Xenon, fluor. Okay, so we have an XC and 2 Fs, and if you can immediately start calculating, but if you use my way, you have 8 electrons over here, and the fluorines need 1 each, so you're gonna share 2. You're sharing from the xenon 1 here, and you're sharing 1 here. You're left with 6 electrons. So how are you gonna put these 6? You just put them like this. And of course you have these electrons by default, octet rule. Aslan, without the octet rule, to be honest, without the octet rule, they are already 7 electrons with fluorine. They're sharing 1 here, and they already have 6, other than the 1 shared here, which makes it 7. But anyways, and of course, wait, did I? Oh, so sorry, my bad. I don't know why I did this. I did it unintentionally. No need for the brackets, of course, because you don't have a charge over here. And then just add, if you want to double check, it's 8 plus 2 times 7, 22 electrons. Let's add 6 plus 6, which is 6 times 2, plus you have 10, 22 again. And this shape has a classification of AX2, the shared domains, shared electron domains, and you have the E, you have 3 of them, and this shape would be linear. This is a linear shape. And of course we can keep on going, the SF and so on and so forth, but to be honest, this is the fastest way, as you have seen. Like, let me try doing IF4 minus quickly. I has 7 electrons, and the Fs need 1 each. You have 4 Fs, so you're going to give, or share, sorry, why am I saying give again? You're going to share 1 for each. You have 4, so you subtract 4, you end up with 3 electrons. So it's sharing 1 with each fluorine. There are 4, so 7 minus 4, you get 3. You have minus 1, so it's, it's IF4 minus. And because of the minus, you're going to add 1 electron, so you're going to end up with 4. So you have 2 pairs of electrons, because each pair is 2 electrons. So as a result, you're going to end up with something like this. 2 pairs, and F, and of course you can do this and that. But anyways, this shape is called the seesaw because it looks like a seesaw, you know, that shape. So and yeah, you can double check the electrons if you want. Of course, sorry, these electrons, I'm usually not drawing them because in this example, when I'm explaining, it takes time, it's time consuming, and I'm thinking about the explanation as I speak, so that's why I usually forget them. I apologize. Here you have 10 plus 5, no, sorry, 6 times, how many fluorines? There are 4, so 6 times 4, you get 34 electrons. Yeah, 34 electrons. So this is 36 electrons, 36 over here, and we have 36 over here. They calculated 36. They match, so this is the correct diagram. And this is a seesaw, again. And the rest, of course, follow the same way. And yeah, pretty much. Whenever we mention electronegativity, to answer, for example, part A, to define it, we usually mention slightly positive, slightly negative, like whenever we would discuss these kind of concepts. We also talk about the shift in cloud, the electron cloud. Why is that though? It's because one attracts, like a certain atom attracts the electrons more than the other. So that's why you have a slight shift. Now this brings us back to electronegativity. So let's define electronegativity. It's the measure of the attraction or the ability of an atom to attract electrons in a covalent bond. This is the definition of electronegativity. Part B, what is the trend? Well, the trend is across a period, electronegativity increases, evident by, you know, like literally the entire period, but if you want to select a few, N, O, F. N less than O less than F, F being the most electronegative because, you know, across a period, electronegativity increases, and down a group it decreases. Example is Cl and F, for example. These are in the same group, however F is above Cl, and thus it's more electronegative than it. And of course we already mentioned F is the most electronegative actually in the entire periodic table, so there you have it, immediately your answer. So increases across a period, decreases down a group. C, bond, when is it considered polar? Well, when we're talking about electronegativity, which is one of the basics for a polar bond or polar compounds, then we're going to consider a certain number, which is the difference in electronegativity between the atoms. So we're going to take a range about 0.4 to 2. So from 0.4 to 2. If it's within that range, it's considered polar. And here we're going to arrange HH, SH, CLH. This one's the most polar because it has the highest electronegativity difference, followed by SH, followed by HH, and then you have HF. Immediately with the F, the most electronegative, and H, immediately that's your answer, first one, then HO, then HH. Here, even though you have FF, it's the same atom. We're talking about electronegativity difference, and here we do not have a difference, so this is the least, we leave it aside. We have NF and HF. This N is electronegative, one of the most electronegative ones, the most being NOF. So you have a smaller difference than the HF, so that's why you have this being more polar than this and more polar than that. And we're pretty much done. The atom minus the number of lone electrons minus half of the shared electrons, and of course we'd have to do this again and again for each different atom. So here, like with different bonding, for example this in here, these two will have different formal charges, so you have to do each one separately, but you already know this, so yeah. So the formal charge of the oxygen in the first one, A, is oxygen has 6, like by default, you know, oxygen has 6, so 6 minus, in this case you have 6 lone electrons, so minus 6, minus it's bonding to one, it has one bond, each bond having 2 electrons, so minus 2 over 2, because in the formula that's with half. So that's 6 minus 6, 0, and then minus 1, so yeah, minus 1. Formal charge, this is A, formal charge of the sulfur is, sulfur by default has 6, so 6 minus, and it has no lone electrons, minus its bonding 4 times, or with 4 single bonds, so that's 4 over 2, no, 8, we're talking about electrons, 8 over 2, so 6 minus 4, that's plus 2. So here we have a minus 1, let me just fix it. Here we have a minus 1, and here we have a plus 2. The total charge, if you want to double check your calculations, for example, the total charge would be this times 4, because you have 4 of those oxygens, so you'll have minus 4, and you have here plus 2. Add them, you get minus 2. Now, is the total charge minus 2? Yeah, it is. So we're correct. So let's keep on going. The next one, formal charge of, for me, I'm gonna denote it with O double bond. I'm not sure if this is even valid, but for me, for the sake of the example, I'm just going to define it like this, the notation. Yeah, okay. So it has, how many electrons does it have? The oxygen has 6 by default as a free atom, minus how many lone pairs or lone electrons it has? It has 4, so minus 4. Bonds 2 times, so 2 times 2, because you have 2 electrons in each bond, so that's 4, and it's already half in the equation itself, in the original one. That's 6 minus 4, that's 2, 2 minus 2, that's 0. Formal charge on the oxygen, the one single bonding, will be 6 again, minus, look here, it says it has 6 lone electrons, minus bonds once, so it has 2 electrons over 2, you end up with minus 1. The formal charge of the sulfur would be 6 minus, in this case you have 5 bonds, so keep that in mind. So here you have 6 minus no free electrons, sorry, lone pairs, minus here you have 5 bonds, so it's 10 over 2, so that'll be 5, so 6 minus 5, that will be plus 1, 6 minus 5. And here of course you multiply by 4, and no, not by 4, because you have one double bond, so you multiply by 3, gives you minus 3, and this one's 0, and this one's plus 1, add them, you get minus 2. Again, we're right. Let's keep on going. Third one, you have 2 double bonds, so F, 2 of those. So when we do actually one of them, the formal charge of O double bond, we'll be doing 2, and then the other 2, same way. So you have 6 minus lone electrons 4, minus you have 2 bonds, so you have 4, so 4 over 2, you have 0 again. Same way actually, to be honest, and you just, to be honest, they are the same. They are the same pretty much. You don't change. 6 minus, again having 6 electrons, minus it bonds once, so 2 2, so minus 1, and then the sulfur, formal charge of the sulfur is 6 electrons, has 0 lone pairs, minus this one is special, it has 6 bonds, so 12 over 2, making 6 minus 6, making 0, and I can already see this is pretty much the lowest. Let's zoom out just to see. So these are all of them. Yeah, these are all of them. This one has the double bond and the single bond. Yeah, this one is the latest one, other than the one we just finished. So minus 1 plus 1. This one's way higher. We already have plus 2, so ignore. Minus 1 plus 1. And over here we have 0 0 minus 1. This one is better. So C is the best so far. So let's keep on going. Below are the Lewis structures for blah blah. Predict the most probable one. So same way, in the same manner. So you have H, C, triple bond, N, O. Actually, I don't need to draw it, just immediately. Form a charge of, in this case you have to do each one. So hydrogen would be 1 minus 0, no lone pairs, minus its bonding with, it has one bond, so 2 over 2, so that'll be 0. and then formal charge of the carbon, that will be 4 minus, here you have no lone pairs, so 0, minus you have 4 bonds, so that's 8 over 2, end up with 0 again. Formal charge of the nitrogen has by default 5 electrons, minus lone pairs has 0, minus it's bonding 4 times again, so 8 to this is 5 minus 4, this is plus 1, and the formal charge finally of the oxygen is 6 minus, has 6 lone electrons and minus bonds once, so 2 over 2, you get minus 1. Formal charge, total charge I mean, 0, which is what we are expecting. Formal charge of hydrogen, nothing to change, same here, same one, also 0. This one's different. Let's do the carbon. Formal charge of the carbon has 4 minus 2 this time, 2 lone electrons, minus it bonds only 3 times, so that makes 6 over 2. So that's 4 minus 2 minus 3, which gives you a minus 1, and then you have a formal charge of nitrogen, again having 5 minus bonds, no, first of all the lone, you have 0, minus bonds 4 times, so 4 times 8, so that's 4 times 2 I mean, that's 8 over 2, again 4, 5 minus 4, that's plus 1, and then you have of oxygen 6. I can already see the answer to this, to be honest, but let's keep on going. 4 minus bonds 2 times, so that's 4 over 2, and you end up with 0. It honestly, to me, it doesn't make sense why the carbon would be more would have the negative rather than the or have the electron over the oxygen, which makes this structure more valid than the other one, even though they have the same numbers, 0 minus 1 plus 1 0, and 0 0 plus 1 minus 1, same thing. The only difference is that the oxygen would make more sense to have the negative over the other one, and thus that's why it's better. So number 24, I really like this one, it's really easy. So they're asking for the optimum wavelength. For this one, you immediately can go like it's the peak, and the peak looks like it's 510, so you're done. If you want to actually get the how do you reach the 510, it's 480 till 520, it's somewhere in the middle, so we go with the midpoint. You get 500, yeah, 500 exactly. However, if you go with the 500, it looks like it's midway between the 500 and the 520. So add the two again, divide by 2, you get 510. And we found the peak. Do you use this or this? They're the same. They're the same. They're just reflections of each other, because you're taking another factor which is the opposite, like it reacts oppositely to it. Rather than increases, it decreases, rather it decreases and increases. So that's all about it. Here we're given the absorbance and we're looking for the for the number of moles. To get the number of moles, we need the volume. We're given the volume, and we need the concentration, and that's what we're looking for using the graph. So we have an absorbance of 0.275. They already drew the line for you. It goes down here and then goes perfectly on 0.05. So it goes perfectly on 0.050 molar. That's the concentration. We have a volume of 20 milliliter. We need number of moles, which only could happen with SI units. That's why we change on the spot. And then multiply NSCV. You get 0.05 times times 20, I mean, times the power of minus 3. So 0.050 times 20 times the power of minus 3, you get 1.0 times 10 to the power of minus 3. And that's the number of moles basically. And yeah. So the hybridization of these following molecules, you have methane. So you draw the Lewis structure like this, and you count the number of sigma bonds. Each single bond is a sigma bond, so you have 4 plus lone pairs, you have 0, so you have 4, and then you just subtract by 1 by default so that you get the superscript of the P. Because you already have an S, so you're only left with one number minus 1. So that's why you do 4 minus 1, you get 3. And this one, look at it, it's a tetrahedral. Tetrahedral with bond angle 109.5, and we have the second example, the BeCl2, and then you put the electrons here, and then it's sp. Here you have a sigma bond, here you have a sigma bond, so that's sp1, because 2 minus 2 plus 0, because there are no lone pairs, minus 1 by default, you get 1, so sp1, so sp. And its shape is, as you can see, it's linear, and you have the bond angle to be 180. Let's keep on going. You have H2O, and with this you have 2 sigma bonds, and considering the lone pairs as sigma bonds, you get 4. I mean, we said we add the lone pairs, so we just did that. So you have 4 minus 1, you get 3, so sp3. In this case it's bent, V-shaped or angular, and the expected angle is less than 109.5 and less than 107.5, because that's for the one before, the one with the 1 lone pair. Here we have 2, so it's less, so 104.5. And then ammonia and a lone pair. This one's going to have 1 sigma, 1 sigma, 1 sigma. We are considering this as a sigma bond, so we have 4 minus 1, you get 3, so you get sp3. This is this is a trigonal pyramidal with a bond angle of 107 nearly. The 107 comes from being less than 109.5 and bigger than 104.5, because that's for H2O or H2O with 2 lone pairs. And we continue. Last one, no, not last one, you have still BF3, electron deficient, because you're talking about borons, so you don't even have to consider in this case the boron. And with that we are left with 3 sigma bonds. You have 3, so that's sp2, because it's 3 minus 1, and sp2 here is trigonal, but this time it's not pyramidal, it's not 3D, it's planar. And lastly we have the CO1, which looks like this, but let's say you don't know. Add octet rule, count 6 times 2 and then plus 2, that's 14 electrons. How much do we have? 4 plus 6, we have 10 electrons. So we want to reach this. We have 10, but we are using 14, so triple bond, cancel 2, you get this pretty much. And with that the hybridization is 1 sigma 2 pi's. I mean, it's pi, but I'm writing 2 pi. Usually sigma, let's say, is in the middle, and you have pi, and here, if you're considering the carbon, which I think is the case here, you are going to say that it has a lone pair. So immediately you say 1, because there's one sigma bond, plus lone pair, that's 1. And they both actually have the same answer because they're both 1 plus 1. I guess that's why they never ask about 1 specifically, because they both give the same answer. So 1 plus 1, they get 2, minus 1, you get 1. So SP. 1 plus 1 gives you the number of sigma bonds with the assumed lone pair bonds, minus 1 because that's how things work, because you're already using an S, so it's subtracted by 1. So you're left with an SP, shape, linear, bond angle, expected bond angle is 180. Pretty much. For this one, the one that's bonded to 3 hydrogens and 1 carbon has an SP of 3, because you have 1 sigma, 2 sigmas, 3, 4 sigmas, so SP3. Now the second one has 1 sigma, 1 pi, 1 sigma, 1 sigma, so that's 3 sigma, 1 pi. You don't care about pi's, you are left with 3 sigmas, so that's minus 1, you get SP2. So SP3 and SP2, and there's no SP, so it's I and triple I. So we're asked to draw the Lewis structures. These are the Lewis structures. Here you have, let's take out those ones. Here you have like that. This is the ethane, so on and so forth. And these are the Lewis structures. You have the shape of this one. The shape would be, looks like a tetrahedral. So you have 2 tetrahedrals fused. And then this one would be the trigonal planar, 2 of those fused, and here you have automatically linear. Now the SPs, they asked about it in the next one, the hybrid orbitals. The hybrid orbital of this one, both C's experience the same kind of hybridization. So you'll have SP3 because you have 4 sigma bonds, each one's like sigma, 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 sigma. So that's 4 minus 1, you get 3. The next one is SP2. Why? Because you have a double bond. One is pi, one is sigma. And you have 3 sigmas, so you have 3 minus 1, so SP2. And then this one is linear. Why? Because you have a pi and a sigma and a sigma. So 2 plus 1, minus 1. Because we're done adding the lone pairs, which don't exist in the first place. And the sigma bonds, you get a total of 2, minus 1, you get 1, so SP. Polar bonds, they're all polar, because is there an electronegativity difference between C and H? Yes. Between C and H again? Yes. Between C and H again? Yes. So these are polar. Now polar molecule is different. What about the net dipole? We would say the net dipole is 0 in this case. So they are 0 because the dipoles cancel each other. But of course, you also have to keep in mind these are 3D structures, so not everything applies the entirety of the case. Sometimes they are polar and you actually consider them polar. So we're done with chemistry. I hope you have benefited from this, and good luck in your exam.
Alright guys, let's move on to chapter 10. This chapter deals with liquids and solids, intermolecular forces, intramolecular forces, and etc. Let's start with the first basic question. In this chapter, I'm just going to be, telling you the answers. I won't be writing much because, the answers are very, very long. Account for each of the following. At 25 degrees Celsius and 1 atmosphere, F2 is a gas, whereas I2 is a solid. In every type of question like this, first you have to think which type. Let me just write this down here. Which types of intermolecular forces they have, and then compare them. So which intermolecular forces do F2 and I2 have? They both have LDF, London dispersion forces. LDF depends on 2 factors: number of electrons and the shape of the molecule. Shape has no relevance in this question, so we think about number of electrons. Since I2 has more electrons, it has a bigger electron cloud which is more polarizable, and that's why the London dispersion forces are stronger in I2, which leads to it having a higher melting point and a boiling point, and that's why at room temperature I2 is a solid whereas F2 is a gas. Part B. Melting point of MgO is greater than CaCl. Thing we can see here is that they're both ionic. When we say ionic, we think of lattice energy. Now lattice energy depends on two things again: size and charge. We should think about charge here more. What's the charge of Mg? Mg is plus 2, O is minus 2. Cs is plus 1 and Cl is minus 1. Since the charges are greater in MgO, the lattice energy is higher. That's why you need more energy or a higher melting point to break down MgO. Part C. Ammonia is very soluble in water, whereas phosphine is only moderately soluble in water. Ammonia is NH3. NH3 looks like this. This NH3 actually makes H bonds. PH3 only makes dipole-dipole bonds. Well, since water as well makes H bonds, as we can see from this diagram, O is a very electronegative atom. That's why, ammonia is very soluble in water because it's able to H bond with water, whereas phosphine is not able to. Silicon melts at a much higher temperature than iodine. Iodine has LDF forces, whereas silicon makes a network solid with covalent bonds. Covalent bonds are way stronger than LDF forces, and that's why silicon, you need a higher temperature to break down the bonds. And that's number 1 done. Let's move on to number 2, part A. I'll give you guys a few seconds to solve and then we'll check together. Alright, let's check together. In the H2SE molecule, the HSE-H bond angle is close to 90 degrees. On the basis of this information, what atomic orbitals of the Se atom are involved in bonding with H atoms? First, let's do a quick revision of what orbitals we know. We know the S orbitals, the p orbitals, the d orbitals, and the f orbitals. This will be important for us. Se, it's in group 6. So this shows us that it has S and P at its highest or energy level. D and F are excluded. What's the shape of S? S orbitals are spherical and P orbitals are dumbbell shaped. And there's 3 orbitals in the p orbitals. There's px, py, and pz, and each of these are 90 degrees apart. So from this we can immediately know that which atomic orbitals are involved in bonding. Those are the p orbitals. Alright, let's move on to part B now. 2 types of intermolecular forces are present in liquid H2SE are LDF and dipole-dipole. Compare the strength of the LDF forces in H2SE to the strength of LDF in liquid water. Now, they are stronger in H2SE. Why? Se has more electrons than electrons in oxygen. Because H2 is common, so we cancel them out. And Se is below oxygen, so it has more electrons. And the explanation is the exact same as before. It has a larger electron cloud. It's more polarizable, and that's why it's stronger. Compare the strength of the dipole-dipole forces in liquid H2SE to the strength of dipole-dipole in water. Okay. Well, this time, the dipole-dipole forces are stronger in liquid water compared to HSE. Why? Because O is more electronegative. The greater the difference of the electronegativity, like the bigger the arrow, if you can know what I mean, like the magnitude, the stronger the dipole-dipole forces. In fact, H2O has a special type of dipole-dipole force known as the H bond, which is the strongest dipole-dipole force. Whereas H2SE does not have that, that's why it's stronger. Let's move on to number 3 now. I'll give you guys a few seconds to solve. Alright, let's check it together. So we have 3 isomers of pentane. So I'll just quickly draw them. I hope you guys remember from last year. If not, I'll just quickly do a quick revision. Let's see, N-pentane is basically 5 carbons and hydrogens. I'm not going to draw the hydrogens. Each dash represents a hydrogen next to it. This is N-pentane. 2-methyl-butane, it has 4 carbons and dash here, and then a carbon here with 3 hydrogens, and the same as for the rest. And 2,2-dimethyl-propane, I'll draw here 1, 2, 3, carbon here and carbon here with arrows for the rest. And yeah, so we've drawn the structural formulas. All I have to do is write H for each of them, right? This is 2,2-dimethylpropane, and pentane is this, and 2-methylbutane is the bottom one. On the basis of molecular structure, identify the isomer that has the highest boiling point. Since these are all hydrocarbons, they only have LDF. As we said earlier, LDF depends on number of electrons and shape. Since they all have the same formula, number of electrons is out. Only shape matters. Well, the answer is actually N-pentane. Why? We should know that the straighter the chain, like this is a straight chain. This is straight, but then you have one branch. This is straight, but you have 2 branches. The straighter the chain and the less branched it is, the stronger the force is. Because if you think about it, like another molecule of N-pentane is able to bond more easily. For example, these are dashed lines are the LDF forces. Those are able to bond more easily because if you think about it, if it's a linear structure, they can approach each other more closely and form a greater number of induced dipoles than the other isomers, which are more compact, right? So the distance will be greater, and that's why, like, since N-pentane is the most linear, it has the strongest LDF forces, which leads to a higher boiling point. Alright, let's go to 4 part A. Structures of the 1-aminopropane molecule, which is here, the left one, and the propane molecule are shown below. 1-aminopropane is soluble in water, whereas propane is not. Account for the difference in solubility. Okay, I'll give you guys a few seconds and then we'll check. Alright, one thing we should immediately notice, propane is non-polar. It has LDF forces only. Propane is actually, 1-aminopropane is actually polar because of this area mainly, and it has LDF and H bond because N is very electronegative. So we can say that since 1-aminopropane is polar, it can form H bonds with water, and propane is non-polar, that's why it can only form London dispersion forces. From that we can say that it is soluble in water because it is capable of forming the H bonds, and since propane is non-polar, it cannot form such strong bonds, and that's why it's not soluble in water. And that's it. Let's see part B now. We have again structures of diethyl ether molecule and butanol molecule, and we have the boiling points, and we should say why the boiling point of diethyl ether is lower than butanol. I'll give you guys a few seconds and then we'll check. Alright, let's check. First, we should see immediately that both are polar. Alright, since this has the oxygen here, or actually no, diethyl ether. I mean, both are polar, but butanol is more polar if you can think about it that way. But one thing we should notice is the oxygen diethyl ether is not bonded to any hydrogens. So H bonding does not exist. But here it's bonded to an hydrogen, and that's why H bonding exists. Now a substance with an H bond obviously is stronger than a substance with no H bonds, even if it has dipole-dipole interactions, since H bonds are the strongest dipole-dipole interactions, and that is why you need more energy or a higher boiling point to boil a substance with a H bond, and that's the reason why you need a higher temperature, because it has H bond. Now part II is a little interesting. The normal boiling point of Br2 is higher than the normal boiling point of HBr. Account for the differences in normal boiling point based on the types of intermolecular forces. In the substances, you must discuss both substances in your answer. I'll give you guys a few seconds. Alright, first we should draw both substances. So we have a Br bonded to a Br. This is Br2, and we have an HBr. we should clearly see, this has a dipole, so it has LDF and dipole, whereas this only has LDF. But somehow this is still greater than this. So what we should say is the London dispersion forces in BR2 are stronger than the London dispersion forces and the dipole-dipole interactions in HBr. This can be explained as BR2 has more electrons than HBr, and since more electrons increases the strength of London dispersion forces, and that is why it has a higher boiling point, because it has stronger forces. And that is the answer for part B double R. Part C now. CO2 melts at 181 Kelvin, whereas SiO2 melts at 1883 Kelvin. Account for the differences in melting points. You must discuss both of the substances in your answer. Alright, since we are talking about melting, both are solid. We should know that SiO2 is a network solid. So it has covalent bonding between each molecule. Whereas CO2, when it's a solid, it has discrete molecules, so like a CO2 here, a CO2 here, which each have LDF. They do not have covalent bonds. And since LDF is much weaker than a covalent bond, that's why it melts at a much lower temperature. Because LDF forces are relatively weak compared to covalent bonds and can be broken at a much lower temperature as compared to covalent bonds. And this is consistent with the fact that SiO2 has a higher melting point. Let's do the grid questions, number 1 and 2. We'll check them together. I'll give you guys a few seconds. Alright, arrange the following molecules in increasing order of boiling point: HF, HCl, HBr and HI. Obviously HF first, greater than HBr. Oh wait, sorry. It's increasing order, so it's lowest first. It's HBr first, which is HCl first, less than HBr, less than HI, and that is less than HF. Why? HF forms hydrogen bonds, which are the strongest. HI, HBr and HCl all have LDF and dipole-dipole. Now the dipole-dipole forces are relatively the same, so those are ruled out. We look at the LDF. Since iodine has more electrons than bromine, which has more electrons than chlorine, that's why HI has a higher boiling point as compared to HBr and HCl. Reason being, since it has more electrons, the LDF forces here are stronger than HBr's, which are stronger than HCl's. And that is the order. That's the reasoning for the order. Let's move on to number 2. Identify the major types of intermolecular forces that exist between the following molecules. CH4, very easy, LDF. It is a hydrocarbon. NH3 forms H bonds. We're talking about the major here. CO2 is LDF, because if we draw it, C double bond O, the dipole actually cancels out, so it's LDF. It's non-polar, and HCl is dipole-dipole. Because if we draw the structure HCl, there's dipole, and it doesn't cancel out. And those are the answers. Section 10.4 now. Compare the two types of alloys using diagrams as necessary. So we'll just give you a few seconds to solve, and then we'll check together. So there are two types of alloys. So I'll just quickly draw like two squares. Okay. So both types of alloys are homogeneous mixtures. We cannot see any difference, right? Like we cannot see, oh, this is a different atom than this atom. We cannot see them. With metallic character, so sometimes both substances inside are metals, or sometimes it's majority metals with some non-metals. So the first type of alloy is substitutional. And the second one is interstitial. Right. Now let's assume these are certain X metal, right? All of them are the same size, like this, blah, blah, blah. Now let's choose another color here. Let's call this red. Wait. How do I? Never mind. Let's call this non-metal, 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 or another metal, for example, which is the same size. So when some of the initial atoms are replaced by other metallic atoms or non-metallic atoms with the same size, of similar size, then those are substitutional. Interstitial, however, is when you have some host atoms and you have other particles, non-metal, metal, whatever, but they fit in the interstices or the holes between the host atoms, and these atoms are usually are always smaller than the host atoms. That is when you have an interstitial alloy. So these are the two types of alloys: substitutional and interstitial. So substitutional is when you put other atoms that are of similar size in the mixture, and interstitial is when you put smaller atoms than the host in the holes between each atom. Alright, the last question of the basic questions of chapter 10, phase diagrams. So I will just give you guys a few seconds, you guys can solve and then we'll check together. Alright, let's check it together. They want a phase diagram. So I'll draw the phase diagram here. So the phase diagram is actually pressure versus temperature. And pressure is always in atmosphere, and temperature, let's call it in degrees Celsius for instance. Kelvin also works. This is 0. Alright, so now let's just call this point F, and now let's call this A. This will be our triple point. Now you will have a negative slope here, right, like this. Yeah, now this is, let's call this B. I'll explain every single thing. C, and this corresponds to 0, this corresponds to 100, this gas, liquid, and solid. Okay, what is this? Basically, this we'll call it E and D. Now we'll explain. Basically, a phase diagram shows how different pressures and different temperatures influences the boiling and melting point of any substance. So at A, this is called our triple point, and this is like the intersection between all the lines AB, AD, AC, and AE. Alright, AD is the solid liquid equilibrium. So basically, when do we know which equilibrium, solid, liquid, solid, gas, etc., is what states are on both sides of the line. So let's call this AD, solid, liquid, equilibrium. AE on the other hand, as you can see here, AE, it has liquid on the top, gas at the bottom. So it's liquid, gas equilibrium. And AF, where is F? Oh, AF. AF, you have a solid here and you have a gas here. So when the pressure is really low, it's going to be a gas, is solid gas equilibrium. So these lines represent, like, at what temperature or at what pressure change will ice become water, or will ice become water vapor, or when liquid water will become water vapor. Now it says, part B says, and the critical point is here at the top. Point E is known as the critical point. Alright, how does the melting point of ice vary with pressure? If we see here, melting point is when solid becomes liquid. As we see, the melting point here is it's actually negative because B is 0. Let's call this -5, and 0, let's call 10 degrees Celsius. As we see, if pressure increases, so if we go up, the melting point actually decreases since AD has negative slope. And that is why when the pressure increases, if we go up, we are actually going to the left on the temperature axis, and that shows that our melting point decreases. So if you want to see the relationship between melting point and pressure, we have to go along the solid liquid equilibrium. If we think about boiling point, you have to go along the liquid gas equilibrium, and if you think about the sublimation point or vaporization point, you have to go sublimation point, you have to go along the solid gas equilibrium, and that's how a phase diagram works. Okay guys, let's move on to chapter 11, properties of solutions. We'll start with the first question in the course revision sheet. A sample containing 10 grams of sugar with a given molar mass was dissolved in 100 grams of water. A says calculate the mass percentage of the sugar in the solution. B says find the mole fraction of the sugar in the solution. And C says given the final volume of solution is 102 cubic centimeters, calculate the molarity of the sugar in the solution. I'll give you guys a few seconds and then we'll check together. Okay, let's start checking. First, we want the mass percent of sugar in the solution. Well, let's think of what's the formula of percentage by mass. Well, it's equal to the mass of what we want, in this case the sugar, over total mass total, right? So now we have 10 grams of sugar, but we do not only have 100 grams, it's 100 grams of water plus 10 grams of sugar, so 110 times 100%, giving us a total of 9.1% approximately. B. Calculate the mole fraction of sugar in the solution. So we want X of sugar. The symbol we use for mole fraction is X. Well, this is N of sugar, or whatever we're looking for, over the total number of moles. As we know, it's mass over molar mass. So 10 over 342 over, we have moles of sugar and moles of water, so 10 over 342 plus 100 over 18. Let's calculate it on our calculators. So we have 10 over 342 over 10 over 342 plus 100 over 18, and we get an answer of 5.24 times 10 to the minus 3, and there are no units. That's our answer for B. Now let's move on to part C. Let's read what it says first. Given that the final volume of the solution is 102 cubic centimeters, calculate the molarity of the sugar in the solution. What is molarity? Molarity of, I'm just going to call it S. Well, that's equal to the number of moles of sugar, or any of the solutes we're talking about in this case, over the volume of the solution, which is equal to the total volume. Well, we had calculated it before, the number of moles, which is 10 over 342, and we know now that it's 102, but it's cubic centimeters, so we make it into liters or decimeters cubed, which is this. Simplifying, we should get an answer of around 0.287 molar, and that's number 1 complete. Let's move on to number 3, which is the next question. An HCl solution is 30% HCl by weight and its density is 1.1 grams per milliliter. A says what's the molarity and B says what's the mole fraction. I'll give you guys a few seconds and then we'll check together. Okay, let's start. First, we have to think of what does it mean 30% HCl by weight. Let's assume we have a liter of the solution, or 1000 milliliters. Let's split it. What's 30% of 1000? 300 ml or grams of, or wait, sorry about that. First, we have to find the mass of the solution because it's 30% by weight. So for that, we need to do 1.1 times 1000, which is 1100 grams. So now we have to think of it this way. Now what's 30% of 1100 is 330. So you have 330 grams of HCl, and what's the rest? It's going to be water. So that is 770 grams of H2O. Now that we have that, now we can find our required to find, which is the molarity. The molarity, as we had said earlier, is equal to of HCl is the number of moles of HCl over the volume of the solution, which is 330, which is the mass, over what's the molar mass of HCl? It is 36.5, and since we had 1000 milliliters, it's 1, and we should get an answer of 9.04 molars. Let's do part B now. We want the mole fraction of HCl, I believe. Yes. Well, this is simply the number of moles of HCl over the total number of moles. So it is 330, which is the mass, over 36.5 over 330 over 36.5, and we had a 770 for the water over 18, right? And we should get an answer of approximately 0.174. And since mole fraction has no unit, we put no unit. Now let's move on to the next question, which is number 1 of a different section. Consider the enthalpy of solution formation of solid NaCl in the water. List the 3 steps of formation of the solution at the atomic level. B says express the algebraic value of delta H solution in terms of the delta H values of the 3 steps. So let's start with part A. I'll give you guys a few seconds to solve. Okay, let's check. So we have 3 steps. I'm just going to label them 1, 2, 3. Now, if this comes in written, we have to talk about it how the sheet talks about it. We have to list how, every single step in the way it is. I'm just going to, write them in chemical way. So step 1 is the solute particles, which is the Na plus and the Cl minus, because if you remember, ionic solids dissociate in water, expand. So it kind of becomes like this. Na plus gas becomes Na aqueous. Na plus aqueous. And this is an endothermic reaction. So we have to add energy here. Happens. And this we call it delta H1. So what the sheet says is expanding solute particles, and it's an endothermic reaction. And we call this delta H1, and this is very obviously greater than 0. Right? The second one, expanding solvent particles, and again the energy change is endothermic. Now where is this dissolving? In water. So the H2O is expanding, okay, the solvent particles, so each H2O particle is expanding, and this is, we call this delta H2, is a delta H of the second step, and this is again positive. Now what's the third step? Attractions between solute and solvent particles. So let's think of it this way. We have an O and an H. And as we all know, dipoles exist, which are like this. Since this is the negative part and this is the positive part. Since this is slightly negative, it tends to attract to the Na plus, because opposites attract. And if we think of it the other way around, the oxygen is bonded to 2 H's, which are again slightly positive. These tend to attract to the chlorine ions. So these are attractions between solute and solvent particles, and this is an endothermic reaction. This we call delta H3. And this we have listed all 3 steps of formation of the solution at the atomic level. Now part B, express the algebraic value of delta H solution in terms of the delta H values of the 3 steps. Okay, B. They want delta H solution. It is very simply delta H1 plus delta H2 plus delta H3. Now if you want to go beyond and explain more, we can say that delta H1 and delta H2 are both positive and delta H3 is negative, because this is endothermic and this is exothermic. And we can also say that the sign of delta S solution depends on the magnitudes of H1, H2 and H3. If H3 is greater than H1 and H2 combined, is going to be negative, and if H1 plus H2 is more than H3, is going to be positive. Very simply. We'll continue on later. Let's move on to the last question of chapter 11. Answer the following questions which refer to 100 milliliter aqueous solutions of, we have 4 solutions given, I, II, III and IV. A says which solution has the lowest electrical conductivity, explain, and B says which solution has the lowest freezing point, explain. So I'll give you guys a few seconds and you can solve. Okay, let's check. Which solution has the lowest electrical conductivity? As we should easily see, most of these solutions are ionic solutions. These tend to dissociate upon being dissolved. So when they dissociate, they dissociate into ions which conduct electricity. So let's just draw the formulas. Or let's just, draw the formulas. NaCN dissociates into Na plus and Cn minus. So we can see this works. MgBr2 dissociates into Mg2 plus and 2Br minus. C2H5OH will skip, and HF partially, let's just draw a small arrow there, H plus and F minus. We can easily see NaCN dissociates, MgBr2 dissociates and HF dissociates partially, but at least it dissociates. C2H5OH is an alcohol and does not dissociate at all, so our answer here is C2H5OH. Since it is a molecular, it is a molecular compound which produces no ions when it dissolves in water. Since there are no ions, it does not conduct electricity. B. Which solution has the lowest freezing point? Explain. Now, when we have impurities in the solution, freezing point tends to decrease and boiling point tends to increase. We'll keep this in mind. And let's actually just look at the equations I have written for part A. Now no need to assume, we have given, let me do this in red, that we have 0.1 molars of every solution. Okay. Now let's draw the rest in blue. When we dissolve 0.1 molars, let's go with alcohol, the ethanol first. It's very easy. 0.1 molars of ethanol are dissolved. It does not dissociate into anything. 0.1 molars are left. HF, we have 0.1 molar here. 0.1 molar, 0.1 molar, leading up to 0.2 molars. Okay, it has a little more. So its freezing point will be lower than ethanols. Here you have again 0.1 and 0.1 leading to 0.2. So it has the same level of impurities. MgBr2, again Mg2 plus has a 0.1, but Br minus has 2 in the coefficient. The ratio is 1 to 2, so it dissociates into twice, 0.2, leading this to have 0.3 molar of impurities. So that is why MgBr2 has the lowest freezing point, since it dissociates into the most. It has the most impurities, which is 0.3. And that's it. We're done in chapter 11. Alright guys, let's move on to chapter 12, chemical kinetics. So now in this chapter, we deal with, rate laws, reaction rates, etc. So let's look at the first question. Consider the following reaction N2 plus 3H2 to give 2NH3. We have a long given paragraph. I'll give you guys a few seconds to read and solve and then check together. Alright, let's check together. So let's just write the reaction up. N2 plus 3H2 to give 2NH3. Okay, let's call this the initial and then the final. And it is, let's see, 30 minutes. So 30 minutes. Alright, so we had 6 moles of H2 and 4 moles of N2, and obviously we'll have 0 here. And now after 30 minutes we have 5.1 moles of H2, 3.7 and 0.6. They're asking us to find the rate of reaction in terms of the variation of the concentration. Now since it's a 1 decimeter cubed vessel, 6 moles is 6 molar, so we have the concentrations anyways, m. So now how do we find the rate of reaction? Well, it's the change over the time elapsed. So let's, for example, do N2. The change is, it's technically 3.7 minus 4, but we can't have a negative, so we'll take the absolute value, which is 4.0 minus 3.7, 0.3 over 30 minutes. We don't care about the unit of time. Since minutes was given, it'll be molar per minute. It is 0.010 molar per minute. This being for N2. Let's look at H2 up. It was 6 minus 5.1, so it's 0.9 over 30, giving us 0.030 molar per minute, or it's mole per liter per minute, right? Because since mole per liter is molar, so we can use that unit as well. Let's move on to NH3 now. The change is final minus initial. Final is 0.6, initial is 0, so it is 0.6 over 30, giving us 0.020 molar per minute. Now one thing I would like you guys to notice here is the answers are related to the coefficients. Since, see, if the coefficient of N2 is 1 and the coefficient of H2 is 3, you can see that the answer of H2, the rate of reaction, is 3 times the answer of N2. So a trick to be used in the exam is, if you can find the one with the lowest coefficient, if you can find the answer for the the chemical with the lowest coefficient, we can find the rest. So for example, to get NH3, we have to multiply the N2 rate of reaction times 2, and it is the fact. H2 we have to multiply by 3. So this is a quick trick one can use in the exam. Let's move on to the second question. It's a fill in the blanks question. So when the following reaction takes place in an isothermal sealed container, H2 plus I to give 2HI, and we have the rate log given to us. It's fill in the blank. So the rate of the reaction blank, while the rate constant is blank when some hydrogen gas is added. So if we're adding hydrogen gas, so if H2 increases, what happens? Since it's directly proportional, the rate increases. So basically the rate of the reaction increases. But think about the rate constant. Does increasing this have any effect on K? The constant is, that's why we call it a rate constant. It has to be unchanged. So the rate constant is constant or unchanged. Unchanged is a better word to use here. And this is section 12.2 done. Let's move on to basic question 1 for section 12.3. Alright. For the reaction 2x plus y to give z, the following results were obtained. We can see here, 3 experiments are done and we have the concentrations and we have the rates. Part A says what's the rate law of the reaction, and B says calculate the rate constant. So I'll give you guys a few seconds and then we'll check together. Alright, let's check together. For to find the rate law in terms of y, I'm going to consider experiments 1 and 2. Okay? Since x is constant, it has no effect on the change in rate. Y doubles, so let's just put a times 2 here. What is the change in the rate? It's being multiplied by 4. So from this we can get that R is proportional to concentration of Y squared. Now there's a mistake in the sheet. In the answer sheet they say that X decreases by 3 times between experiments 2 and 3, because we have to take an experiment where Y is constant, and that happens in 2 and 3. They say that X decreases by 3 times. So either this is supposed to be 0.1, let me just put that 0.1 there, or we assume that it is 0.3. I'm going to be doing both scenarios, but then in the end I'm going to use the sheet's answer, just to have that consistency. Let's assume it decreases by, it's unchanged. First let's assume this is 0.3. Let's assume that. If it is 0.3, Y is constant, X is constant, but the rate decreases by a factor of 3. So what that tells us is that X has no effect on the rate of change. So we can say that R is proportional to X to the power of 0, which is 1. So it has no effect. But according to the sheet, X decreases, and it's just a typo here. So let's assume it's 0.1. Now since this is dividing by 3, division by 3, and this is also being divided by 3, what happens is R is directly proportional to X, changes in X. So what's the rate law? Part A. Rate is equal to K into X into Y squared. And that's part A done. B. Calculate the rate constant. For this question we can use any single part, but I prefer using experiment 1. Simple. The initial rate is 2.4 is equal to K into 0.8 squared into 0.3. Simple math. We get K is equal to 12.5. But now the hard part comes. What's the unit? Well, since this is molar per hour, so let's assume this is molar per hour. And here we have molar, but we're squaring it. So this is molar squared and this is molar. So we have a molar squared, and let's call this unit X equals. These have to equal, right? This cancels, this cancels. So the molar to the power of 2, when we divide, it goes down, right? So it is molar to the minus 2 times hour to the minus 1. The hour is unchanged, and that's a unit. And that is our answer for part B. So for these kinds of questions, the hardest part would be trying to find the unit. So you can either do something like this, or there was this formula that said if R is the overall order of the reaction, the overall order is found by adding the power. So 2 plus 1 is 3. R is equal to 1 minus, the unit is 1 minus R for M. So if R is 3, 1 minus 3 is equal to minus 2, and this is the same thing here, minus 2. So this is another formula that one can use. Alright, let's move on. Okay, we have this reaction H2 plus Br2 to give 2HBr. We have lots of data, so let's solve it together. We'll give you guys a few seconds and then we'll check together. Alright, let's check together. Now we have to find the order of the reaction with respect to H2, and we have to justify our answer. So we want something where Br2 is constant, so we can be completely sure that only H2 is causing any changes. And experiments 1 and 2 provide such a scenario. We can see that H2 is doubling in concentration, and we can see that the rate is in fact doubled. The rate is doubled. So since it's doubling, and since this, let's just write it here, this is doubling and this is doubling as well, then R is directly proportional to H2. There's no powers involved, so it's a first order reaction. Okay, now let's consider they want Br2 now. So we want two experiments where H2 is constant, which is 2 and 3. Let's see. Br2 is being halved. And what is happening to HBr? The rate of the reaction is also being halved, as we can very clearly see. So again, it is a first order reaction. So the rate law, rate equals K H2 into Br2. That's it. Now what are the units of the rate constant? They haven't asked us to find the rate constant itself, just the units. So I think we should remember that formula right now, that M or let me just write that this way, K is equal to whatever blah 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 molar to the power of 1 minus R and time to the minus 1. And since the time is, let's see, it was given in seconds, so we can immediately write second to the minus 1. Now what do we write? What is the overall order of the reaction? It is 1 plus 1, since the powers are 1, which is 2. 1 minus 2 is minus 1. So we can either write molar to the minus 1 times second to the minus 1, or since we know that molar is actually moles over liter, if you flip it, because if this is to the power of minus 1, this leads to liter over molar, we get liter over molar times second, and this works as well. Molar per second. Let's move on to part E now. Predict the initial rate of the reaction if the initial concentration of H2 is 0.003 and initial concentration of Br2 is 0.0005. Okay, that's a big number. So let's see. For this one, I feel like we should be using experiment 1. I'll tell you why. Our rate law said that rate is equal to K H2 Br2. Now some of you may be thinking, we have to find K and then substitute. But in fact, there's a much easier way to do this, which doesn't involve us finding K. Well, what we can see immediately that the concentration is the exact same. So the rate doesn't change because of any change in Br2. Only H2 is changing. And H2 is changing by a factor of 3. So the rate also changes by a factor of 3 because, as we have seen here, the rate is directly proportional to the concentration of H2. So in fact, the rate 2, which is the new rate, is equal to 3 rate 1, 3 times rate 1. So it's 3 times this number, which would give us something like 1.092 times 10 to the power of minus 11 with the unit. Molar minus 1, or actually no, molar per second, molar per second. And that's your answer for part E. I'll give you guys a few seconds to check and then we'll move on. Alright, let's move on. Again, this is another rate question, so I'll give you guys a few seconds, solve it, and then we'll check together. Alright, let's check together. So for the reaction 2x plus y to give 2z, the initial rate was studied and the following results were obtained. We have experiments 1, 2 and 3. Immediately, without thinking, we can see that experiments 1 and 2 have x constant, so any change in rate is due to y. But the rate isn't changing, so y changing has no effect on the rate. That's why the rate is directly proportional to y to the 0 or 1, so we don't put it in the rate law. Now for x, we can immediately see that when it doubles, the rate in fact is being multiplied by 4. So what this tells us, in fact, is the rate is directly proportional to x squared. Because if this is doubled, then 2 squared is 4. So the rate is equal to 4 of the initial rate. So we can write rate is equal to, k is always going to be there, into x squared. And that's our answer. Alright, let's move on. And if you want, you can write y to the 0, but since this is 1, this cancels out. Number 2. For the reaction 3a plus 2b to give c, the following partial orders were obtained with respect to a and with respect to b, it's true. This question comes a lot in the homework, so I guess we must be remembering, this question. So let's find the overall order. Or let's write the rate law instead. Rate is equal to k, the concentration of a to the power of 1, because that's the order, and b to the power of 2. I said something about R. Does anyone remember? It is actually the overall order of the reaction, which is the sum of the powers, which is 3. And this will help us in the formula. Since they've given us that this is the formula, this is the unit we have to use, second minus 1 will always remain constant. The formula says it's molar to the power of moles to the power of 1 minus R times decimeter cubed to the power of minus 3 into 1 minus r. Let's substitute. It's moles to the power of 1 minus 3 times decimeter cubed minus 3 to the power of 1 minus 3 and seconds to the minus 1, giving us mole to the minus 2. Minus 3 into minus 2 is actually plus 6, so decimeter to the power of 6, second to the minus 1, and that's our answer. So this is the unit of the rate constant. Now let's move on to the integrated rate law. Alright, let's do question 1. I'll give you guys a few seconds and then we'll check together. Alright, let's check together. So we have this reaction 2x to give x2 was studied. The following results are obtained. We have the concentration of x varying as a function of time. So the part A is asking us show that the reaction is first order with respect to x. So there are two ways to show. Either that the half-life is constant, but it's kind of hard to find out the half-life because they're not showing 0.5 and they're not showing 0.25 in this table, or to show that the graph of ln absolute value of x versus time is a straight line with a negative slope. So you know what, I'm not gonna do all the calculations. You can easily find ln 1 is 0, ln 0.8, you have to get ln 0.6 and ln 0.4 and ln 0.2. If you graph these in a graph, you will get a straight line, and let me just quickly draw that straight line. Since it's the negative line, because all of these answers are negative and this is 0, let's call this the origin, let's call this the time, let's call this ln x. It starts with 0 and it goes down. That is what you should be getting when you draw a proper graph, and using this we can say that this is first order with respect to x, since the graph of ln x versus time is a straight line with negative slope. It has to have negative slope and it has to be a straight line. So that's very important. Part B is the more interesting question. What are the value and units of the specific rate constant, or k? So they want k. Well, there are a few ways to do this. The easiest way being we have to find the slope. How do we find the slope? We can take any 2 points on the line. For instance, we can take ln 0.8, like the slope is equal to y2 minus y1 over x2 minus x1, right? We have x2 and x1, we can have it as 10 minus 0, and we can have ln 0.8 because ln 1 minus ln 1 is 0, and we should get a negative answer, and the answer we actually get is negative 0.02. Negative 0.0223. But this is not the final answer. Why? Because if we remember the actual formula of the formula of the line, what's the formula of the line? Y equals mx plus p, right? And how we represent this in terms of ln x is actually ln x is equal to minus kt plus ln of the initial concentration x0. Since we are finding k and we have found the slope, but the slope is actually minus k, so what we have to do is k is actually 0.0223 and it's a second inverse. Why is it second inverse? Because you're multiplying by time, which is actually in seconds, so the seconds cancel, and this is your answer. Alright guys, let's continue with chapter 12. We had stopped at number 2 last time, so let's continue with it. The half-life of a radioactive chemical is 10 hours. A sample of the chemical with a mass of 10 grams was left in the lab. How long will it take for the sample to decay to a mass of 1.25 grams? I'll give you guys a few seconds and then we'll check. So there are multiple formulas to solve this. But personally, there's a very easy way to do this. It's like a counting method. We can see that 1.25 in fact is like, if you keep dividing by half, we actually end up at 1.25. I'll show you what I mean. 10, after one half-life it's 5, after another is 2.5, and after another it's 1.25. So half-life 1, 2, 3 half-lives have passed. So it's 3 times 10, which is 30. So it's 30 hours. You can use this method, or you can use, like m equals m0, half to the n, and then n times t half to get the time elapsed. But, you can also use this method. 3 part A. The radioactivity of a radioactive material was measured at different time intervals and was found to be as in the table below. So we have the time, the activity of the CP or CPM, counts per minute, and the ln of the activity. So they've given us ln activity. They want us to plot a graph of ln activity versus time and find the value of k. Okay, so let's solve it. Again, if we draw the graph, there shouldn't be a negative x-axis because time can't be negative. We should get a number or a graph that looks like this. Let's assume this is 8.99. We should get something like this. So it's a straight line with a negative slope, which shows us it is first order reaction or decay. Now they want us to find the value of k. Let me just remove everything and then we'll have a white space to work with. Okay, find the value of k. There are many ways to do this, but personally there's a very easy way. We can use ln x or ln anything is equal to minus kt plus ln initial x0. So we can in fact say 8.80, I'm using the second one, into minus k and 3 hours have passed plus 8.99, and in fact k is simply 0.063, and the unit is hour to the minus 1, because if we do hour to the minus 1 times hour, the hours cancel out. So this is the answer. Now we have to find part B now. B. Use the value of k to find the half-life of decay progress. Since we had gotten a straight line with a negative slope for ln activity versus time, it's first order, and first order reactions tend to have the formula t half or half-life is equal to ln 2 over k, which leads to the half-life being approximately 11 hours. So it's ln 2 over 0.063, which is 11 hours. Alright, let's move on to question 4. So I'll give you guys a few seconds to copy and then we'll move on. Okay. The rate of the reaction 2x to give x2 was studied. The following results on the concentration of x were obtained. It says show that the reaction is second order with respect to x. So we'll just solve it. This question actually is a very easy question. Reason being, they are telling us that the reaction is second order. So we don't have to, experiment. We don't have to find the ln of this and then, see if it's a straight line with negative slope, blah, blah, blah. They say it's a second order. So immediately what we should do is we should make another row which says 1 over absolute, the concentration of x. And we should, use our calculators to get all of these values. And when you draw the graph of 1 over x versus time, where this is time and this is 1 over x, absolute concentration of x, we should get, let me just check, yes, something like a straight line with a positive slope. So whenever we have a straight line with a positive slope, it is a second order reaction. And the straight line positive slope should be with the graph 1 over the concentration of x versus time. So they've told us that the order is, the reaction has to be second order. So without any doubt, we do this, and if it works, then it is second order, and it should work because they say show that. So when we get a graph that has 1 over x versus time and it's a straight line with positive slope, it's a second order reaction. That's it. Number 5. I'll give you guys a few seconds and then we'll check. Alright, let's check. For the reaction 2p plus q to give r, the initial rate was studied and the following results were obtained. Show that the reaction is zero order with respect to q. So we have to find two experiments where P is constant, so we can find what effect Q has on the rate. Experiments 1 and 2, P is constant, so P has no effect. Q is in fact doubling, but the rate is constant, it's not changing. So R in fact is directly proportional to Q to the power of 0. That's why the reaction is 0 order. So since the concentration of P doesn't change and Q is in fact doubled, but the rate is unchanged, and that's why the reaction is 0 order with respect to Q. Let's move on to number 6 now. The half-life of 55 chromium is 2 hours. The delivery of a sample of this isotope from the reactor to a certain lab requires 14 hours. About what mass of such material should be shipped in order that 1 milligram of 55 chromium is delivered to the lab? Okay, how do we solve this? There are many ways. I personally prefer like a way that is not exactly consistent with the formula, but we can do it, quickly. In the written, I would advise you to use the formula. The half-life is 2 hours, but we need 14 hours to deliver, so 7 half-lives pass. So we have 7 let me just cancel that. We have 7 half-lives. What is the definition of a half-life? A half-life is the time required for the mass of the substance to halve. So if we are reversing the thing, we have to double the mass. So in fact, isn't it 1 times 2 to the power of 7? So, it's doubling 7 times. So 1 becomes 2, 2 becomes 4, 4 becomes 8, 8 becomes 16, blah, blah, blah. And in fact, it should become 120 again. It should become 1 times 2 to the 7, which is 128 milligrams. And if you check this mathematically, it makes sense. If we have 128 milligrams, it becomes 64 after 2 hours, 32 after 4 hours, 16 after 6 hours, 8 after 8 hours, 4 after 10 hours, 2 after 12 hours, and 1 after 14 hours, which makes sense. So it's 128 milligrams. SR90 or strontium-90 has T half of 29 years. How long does it take for 80% of a sample to decay? Okay. So how does this work? The way the sheet talks about it is not really good. It deals with, if it was a multiple choice question, but if it was written, it doesn't make sense at all. Because the logic doesn't make sense. The logic makes sense, but we don't get an exact answer. Let's assume we have 100 grams of strontium. If 80 decays, how much is left? Obviously 20. So if you use the formula m equals, m0 times half to the n, we get, so 20 is equal to 100 half to the n. So in fact, 0.2 is equal to 0.5 to the power of n. How do we get this n? Well, we should remember what logs and lins are, because in this case, n is equal to in fact log 0.5.2. What does this mean? So what is the value of n that if we do 0.5 to that power, we get 0.2. So if you use our calculators, we get, log 0.5.2, something like 2.322. So there are 2.322 half-lives taking place. And we know that, let's call this time actually. There are, the half-life is 29 years. So 2.322 times 29. I'm just using rounded answers. In the exam, use exact answers. So 2.322 times 29 is in fact 67.3 years. So this is how long it's going to take for the 80% of strontium to decay. Now what the sheet does is in fact assumes. So let's say you had 100 grams. After half-life it becomes 50. After another half-life it becomes 25. This is very close to 20. So only 2 half-lives have passed. So it's 2 times 29, which is 58 years. But in fact this answer is off by approximately 10 years. So that's why you can either use this to estimate if the answers are really far apart and you don't have time, and it's a multiple choice question where they don't care how you solve it, but in a written you should use the method I've shown. Alright, let's move to the grid questions now. The decomposition of a certain chemical X2O is first ordered with a constant of 1.4 times 10 to the minus 2. Determine the half-life of the decomposition. That's part A. I'll give you guys a few seconds and then we check together. Okay, this is a first order reaction, so the formula is very obviously T half is equal to ln 2 over 1.4 times 10 to the minus 2, giving us an answer of approximately 49.5, or to two significant figures, 50 seconds. B now. The initial pressure was 6 atmosphere. How long will it take for the sample to decompose and reach a pressure of 0.75 atmosphere? The same thing that goes with mass goes with pressure. The pressure has to halve. We can use my counting method. So 6 becomes 3 after 1, becomes 1.5, and becomes 0.75. So it takes 1, 2, 3 half-lives. So in fact the time is 3 times 50 approximately, or 150 seconds. And that's how long it will take for it to decompose to reach 150 seconds. Alright, let's move on to section 12.5, reaction mechanisms. So we have a given mechanism for a reaction 2NO2 plus Cl2 to give 2NO2Cl, and we have two steps, a slow and a fast step. Okay, knowing that the rate law was determined experimentally to be R equals K NO2Cl2, deduce whether the mechanism is acceptable and justify. I'll give you guys a few seconds, solve, and then we check together. Alright, let's check together. There are two conditions to make sure that the reaction mechanism is an acceptable one. First, the steps have to add up to be the original equation. So let's see, the Cl cancels, we get 2NO2 plus Cl2 to give 2NO2Cl. This matches the reaction, so condition 1 has been fulfilled. The second condition is that the slow step, the rate law of the slow step or the rate determining step has to be the same as the rate law of the reaction itself. So let's see. And one more thing to know, that in the mechanism steps we can get the rate law by seeing the coefficients. So for the step 1 we actually get R is equal to K is always going to be there, and O2 to the power of 1 because the coefficient is 1, and Cl2 to the power of 1. Is this the same? It is, and that is why this mechanism is acceptable. For the justification, you just say, it is an acceptable mechanism since the steps add up to give the reaction and the rate law is consistent. Number 2, there is another mechanism for another reaction. Very simply, they want the catalyst and intermediate. What is a catalyst first? A catalyst is a species or any substance that is consumed in a step and then produced in a later step. Where is this happening? If we look at F2 is consumed in step 2 and produced in step 3. It's being regenerated, as we say. So F2 is the catalyst. And how you specify? You just say, it is consumed in step 2 and produced in step 3. Intermediate, however, is the complete opposite. It is first produced and then consumed. Cl here is a good example. It is produced in step 1 and consumed in step 2. So Cl is the intermediate. And that's 12.5 done. 12.6 now. Explain how heating increases the rate of the reaction. I'm not going to write the answer. It's a very long answer. I'm just going to read it out. So heating speeds up a chemical reaction mainly because it increases the kinetic energy of the reactants. So one thing we should know, if we remember, many reactions have an activation energy, and most of the times they're usually lower than them. So they have to increase the energy, and when they reach this threshold energy, only then are some products formed that are at a lower energy, thus are more stable. So heating in fact helps push the energy of the reactants. It helps push them up so that more and more collisions are effective collisions that are at this energy level. And in fact, in fancy words, that is what the answer says. So a greater percentage of the starting reactants possess enough energy to react, i.e. the threshold energy. So heating increases the frequency of the effective collisions. And another reason that it increases the rate of the reaction, if heating increases, as we all know, kinetic energy, or the average kinetic energy, is directly proportional to the absolute temperature. If you increase the temperature or heat, kinetic energy increases. And because kinetic energy increases, more and more particles collide, and that's why the rate of the reaction increases. Okay, let's move on to 12.7, which is the last section required. We have two basic questions, so we'll just do them quickly. I'll give you guys a few seconds. Alright, let's check. We have methane gas which reacts with bromine to form dibromomethane and hydrogen bromide as represented by the equation above. The following mechanism has been proposed. A says is CH3Br, which is here and here. Catalyst or an intermediate? Justify. Immediately we can see it is consumed then produced. It is produced and then consumed, so it is an intermediate. Why? Because it is produced in step 3 and consumed in step 4. Identify the order of the reaction with respect to each of the following according to the mechanism. Okay. Always, we determine the order of the reaction from the slow step, which is the rate determining step. So we actually get R equals K CH4 into Br dot. But if we see the question, they expect us to find in terms of Br2, which is not even in the reaction. For this, we look at the fast equilibrium. As you all remember, there's something called K equilibrium, right? And what is K equilibrium? It is Br dot squared over Br2. So now we have Br dot in two reactions and we have in two equations and you have Br. So what we can do is you can find Br dot in terms of K equilibrium and Br2. How we can do that? So Br dot is in fact the square root of K equilibrium times Br2. How? I just cross multiplied and took the radical. Substituting, we get R is equal to K CH4 into this, the radical, right? Let me just erase so I can continue. The square root of a constant is another constant. And when we multiply two constants, we get another constant. So I'm just going to write rate is equal to K prime, which is in fact K of the K1, which is K1 of this equation, times the square root of K equilibrium. Okay, this is what I've done. Into CH4 to the power of 1 and Br2 to the power of half. Because I had square rooted it, right? And to take it out of the square root, it has to be to the power of half. So the order of reaction with respect to CH4 is 1 and Br2 is half. And that's it. Let's do the last question of the basic and grid questions, number 2. The gas phase decomposition of nitrous oxide has the following two-step mechanism. Step 1 is N2O to give N2 and O, and step 2 is O plus N2O to give N2 and O2. Write a balanced equation for the overall reaction. Very simple, we just have to add up. O cancels, 2N2O, this is part A, to give 2N2 plus O2, and that's part A. B. Is oxygen atom a catalyst or an intermediate? It is produced then consumed intermediate immediately, because it is produced then consumed. Had it been a catalyst, it would have been consumed then produced, regenerated. C. Identify the slower step in the mechanism if the rate law for the reaction was determined to be K into N2O. Justify your answer. We should know that the rate of this the rate of the overall reaction has to equal to the rate of the slow step. One of these steps is slow, so it's either this or this, right? Let's take the rate law of the first step. R is equal to K into N2O, because that's the coefficient, and for this one is R equals K into O. This is definitely wrong, it's this one. So step 1 is the slower step. And with this, we've completed chapter 12. Thank you.
Chapter 13, number 1. You have a quantity of gases at a 2 decimeter cubed vessel, and you have a set number. So this is, and you just have to find the equilibrium law for this reaction. So it is products over reactants to the power of their coefficients. So SO3 squared, they have to be gaseous or aqueous, and O2 power 1 and SO2 power 2. That's the equilibrium law reaction. Calculate the value of K for the following. You just have the number of moles and you divide them by 2. So for SO3 it will be 20 divided by 2, which is 10. So 10 squared over O2, which is 4, you divide by 2 times 2, and SO2, which is 10 divided by 2 times 5 squared. And this is 50, 100, the answer is 2. C. Calculate the value of K for the following reaction. SO2 half SO3. So since we found this to be 2 and this is just half of this equation, it's 2 power half, which is equal to root 2, which is around 1.4. And B, it's 2 times this, so K power 2, which is 2 power 2, which is equal to 4. Grid. A sample containing 2, this is the ice table. So 2 mole, 2 mole, 10 mole. So 2 meters, this is 1, 1, and 5. Concentration, C equals. So ice and H2, I2, HI, 2HR. So here you have 1, here you have 1, and here you have 10 over 2, 5. And then you have to make sure of which direction it's going. So you do 5 squared over 1 times 1, and that's 25. So since there is more of the products, the system is to the left. So this becomes minus 2x plus x plus x. Because there's more products, so it will shift to the left. Then this becomes 1 plus x, 1 plus x, and 5 minus 2x. Then you just equate the equilibrium constant to the equilibrium law. So 5 minus 2x over 1 minus 2x squared, this is also squared because the coefficient equals 10. And you solve it, and you get H2 to be 1.36. Obviously you find x first, then do 1 minus x, and then you do 5 minus 2x to get 4.29. The next one, a sample containing 4 moles, introduced into 4, so it's 1 of each. Equilibrium K, calculate the equilibrium. This is ice table again. So 1, 1, nothing, nothing. Ice. Minus x, plus x, plus x. 1 minus x, 1 minus x, x, x. So the equilibrium law is x squared over 1 minus x squared, because product times product over reactant times reactant, and all of them are to the coefficient of 1. So you equate this to 4, and you get 0.3333 and minus 1. And since minus 1 is not possible, because x can be minus, because it's a concentration, so it has to be positive, you take this. So H2 and CO2 end up being 0.33, and this ends up being 0.667, which is 1 minus 0.333. And make sure this is actually 1 over 3, not 0.0033, because a you change this. Sorry for that. Kp for Na, so pressure, and this is C, so you don't count it. So it'll be NH3P times HCl B equals 0.01 at a particular temperature. What are the partial pressures? You just do square root of that, of 0.01, which is 0.1. Number 3, you have carbon solid, carbon dioxide gas, to give 2CO gas. And they just react, you monitor the total pressure, and then as you see here, they're the same, so this is equilibrium. So total pressure equals to 4.2 at equilibrium. And they said partial pressure of CO2 is 0.82. And all that's contributing to the pressure are the gaseous ones, which are here, CO and CO2. So to get the one for CO, you do 4.2 minus 0.82, and you get 3.38. So that's I. Equilibrium constant, you do gaseous only to the power of coefficient for products over reactants. So CO squared, P, and CO2 P. So 3.38 squared over 0.82. And you put in the calculator and solve, you get 14. If a catalyst was added place, what would be the final pressure of the gases? Catalyst just speeds up the rate. So if you see here hours, instead of it reaching at 4 hours, it might reach it at 2 hours. 2 is just an example, it's not an actual value. Isomers of butane exist in equilibrium. Once equilibrium was reached, N-butane was found to be 5 times 10 power 5. If the volume of system was increased to double of its original, what will be the new concentration? It will be the same, but just divided by 2. Sorry, divided by 2, because C equals M over V, so divided by 2, it will be the same. So 2.5 times 10 power minus 5. 27.9, 10.5 liter. What is the initial molar concentration? 27.9 over molar mass, that's M divided by 10.5, which is 0.0156. What is the initial molar concentration? That's what we got. Equilibrium constant expression. So they're all gases, and you do products, concentration of products, AsF3 over AsF5. That is the equilibrium law reaction. So then, equilibrium established, 30% of the original have decomposed. Calculate molar concentration. It's 0.7, because 0.3 decomposed, so 0.7 remains, times 0.0156 times, and you get 0.0109. Using molar concentration, we calculate the value of the equilibrium constant at 1.5. So, like we found in part B, we found AsF5 to be 0.0109, 0.0109, and the other one is simply 0.15010.156 minus 0.0109, squared, because there's two of them. And you solve it, you get the answer. Here, 2 moles was placed in 1 liter, so it will be 2 molar, as you can see here, and it ended up being 1.6. So 0.4 was used. So if you look at here, 0.2 of this will be produced, 0.2 of this will be produced, because 2 to 1. Write the equilibrium law. It will be gaseous moles, or aqueous, Br2, over HBr squared. So the coefficient. What is HBr at equilibrium? You look here, it's 1.6. Although in the answer sheet, it shows it to be 1.8. So when this is something wrong they did, it'll hopefully be correct in the exam, but you never know. Determine equilibrium concentration of H2. Will be, since according to the answer sheet, 1.8 was left, 0.2 was used. So in this ratio, 0.1 of each will be produced. So this is 0.1 molar. Make a sketch that shows the concentration of H2 changes. So it was 0 at first, and then slowly it increased to 0.1 and was constant. So imagine that line there was 0.1. Calculate the value of the equilibrium constant. It's Kc over, so H2 was 0.1, Br2 is 0.1, HBr is 1.8. Put on the calculator and you get it. As for P, it's this. As for Kp, it'll be the same as Kc because they're all gaseous. Yeah, they're all gaseous, so it doesn't really change anything. The ratios will be the same, so everything cancels out at the end. But if it wasn't the same, if it wasn't gaseous, then Kp is equal to Kc. So what you got into R delta T delta M. So the number of moles that changed multiplied by the temperature, and R is the constant 0.082. Grid questions. A sample containing 6 moles, 3 decimeter, and you normally have this. So when this happens, it's best to do, it's always most likely going to be isotable when you have this equation. So 6 divided by 3 is 2, so 2, 2, and then nothing, ice, and coefficient is 1, minus x, coefficient is 2, plus 2x. So here, 2x, 2 minus x, 2 minus x. So you will put products over reactants, and you equate it to 25. So 2x squared over 2 minus x squared equals to 25. So an easy way is to 2 square root, and it becomes 5. And then you just solve by bringing this up, equate them, and you get x. And once you get x, which is 1.43, you have to pay attention to what they're asking in the actual exam. So HI, it's 2x, so 2 times 1.43, which is 2.86, and H2 and I2 is 2 minus 1.43, which is equal to 0.57. Number 2, sealed container, initial pressure 16 and 12 atm atmospheric, total pressure was 24. Calculate the value of Kp. So again, this is sort of like the ice table. 16, 12, then nothing. Then minus 2x, minus x, plus 2x, 2x, 12 minus x, 16 minus 2x. Then power of coefficients. So 2x squared over 16 minus 2x, 12 minus x equals 24. Oh, sorry, no. This is wrong. It's not, this is how you calculate Kp, but how you get the x is you equate all this to 24. So 16 minus 2x plus 12 minus x plus 2x equals 24. So 2x cancels out, and this becomes 28 minus x equals 24. X is 4. So 2x, which is equal to 4, that's for NOCl. Sorry, 2x, where x is 4, this is 8, then it's 12 minus x, that's equal to 8 as well, and then 16 minus 2x, which is also equal to 8. So all species are 8. So makes it simpler. So 8 squared for NOCl, 2, over Cl, 8, times NO, 8 squared. So 8 squared and 8 squared cancels, you get Kp to be 1 over 8. So 0.125, take significant figures, 24, 2, so 0.13. NO and Cl2 were introduced, 10 atmosphere, 6 atmosphere. At equilibrium, pressure of Cl was 2 atmospheres, so ice table again. 10, 6, nothing, minus 2x, minus x, plus 2x. So 2x, 6 minus x, 10 minus 2x. So 2 atmosphere, so equals 2, x equals 4 from this. So you get this to be 8, you get this to be 4, and you get this to be 2. So 8 squared over 2 times 4 squared. Sorry, times 2 squared. And the result is 8. Because all this is 8, so it cancels out. This is 2, one of the 8s. Le Chatelier's principle. So SO2, SO3 equilibrium, closed container, predict the effect. Increasing temperature, the system will try to decrease it, so it will use it up, so it will shift towards the endothermic side, so it will shift to the left, so SO3 decreases. Reducing volume, so increasing pressure, because PV is constant, because N and temperature, nRT, this is a constant, this is a constant, this is a constant. So pressure increases, it will shift towards a lower number of moles, so it will shift to the right, SO3 increases. Catalyst is added, nothing will happen because it's already at equilibrium. If it wasn't at equilibrium, then it will just reach it faster. It will not affect the concentration. Number 2. What is the effect of adding NaOH to an equilibrium containing saturated? So by adding this, you're increasing OH minus. So you're going to shift it more to the right, and you'll have more of CuOH2. So having more of CuOH2 means you'll have more solid, so solubility decreases. And another way of thinking about it is, since Cu2 plus, this is the way to think about it, sorry, is OH minus, 2OH minus, plus whatever. So OH minus increases, so it will shift to the right, and this will decrease, so solubility decreases because more solid is formed. So the more basic the solution, the more CuOH2 produced, solid. What is the effect on percent yield of raising pressure? It will shift to the less moles, so this side, so NH3 will increase. What is the effect of the percent yield of raising temperature? Raising temperature, it will try to decrease it, so it will use the temperature in the endothermic side. So since this one is endothermic, it's exothermic, it will shift to the left. So percent yield decreases because less NH3. Reaction 1. For reaction 1, write the expression Kp. It will be gaseous moles of product times gaseous moles, P times XO P over H2O P. That's for Kp. Or how you're supposed to represent it is P and H2, like that, not like H2. For reaction 1, will the equilibrium constant increase, decrease if temperature rises above 298? If it rises above 298, so you're adding more temperature, it will shift towards the endothermic side, so it will shift to the right, and since it's making more products, Kp will increase. Calculate the value of delta H. So you look here, you see XO, there's XO here and XO here, and this one is just shifted, it's on the other side, and we have X solid here, 1, X solid here, 1, and we have XO2 there, and H2 cancel, H2O cancel. So it's basically you just add these two up, but they're shifted to the other side. So 1, 3, 1 plus 4, 1, and then minus the whole thing. Determine Kp3 in terms of Kp and K2. So since they are all, it's just adding them, but adding the reverse of them, it's just power minus 1 for each, times power minus 1. So K, P prime, K, P double prime. So it ends up being 1 over K, P prime, K, P double prime. And that is it for the grid questions of 13.6.